Welcome to the second day of UPSLA at SPLASH'23. It is my great pleasure and honor, I have to say, to welcome now our keynote speaker of today, Joe Hellerstein of UC Berkeley. He is the Jim Gray Professor for Database Systems at UC Berkeley. And his work focuses on data-centered systems, and in this space he covers, I would say, all topics going from low-level system topics up to programming abstractions. And his work has been recognized by so many awards that I really cannot list all of them, but I want to mention, of course, some of them. The ACM Sigmod Code Innovation Award, which is awarded or given for innovative and highly significant contributions of enduring value to the development, understanding, and use of database systems and databases. He's an ACM fellow, he's a Sloan fellow, and he didn't get 1 or 2 Test of Time awards, but 6 of them. The Fortune magazine has included him in the list of 50 smartest people in technology. The MIT Technology Review has included his work on cloud programming to the list of 10 technologies that are very likely to change our world. And he has done also a lot of contributions to the tech industry. He has funded several startups, I know at least of 2. He is a faculty fellow of Sutter Hill Ventures, was director of Intel Research in Berkeley, and technical advisor of several startups, and also established tech companies. Do you want to hear more? I do have at least 1 item more beyond all those that I mentioned. He is also a pretty good trumpet player, as far as I can judge, as someone that has no idea about, likes music, but does not do music myself. I have been very amazed and following his work for several years at the intersection between databases, database systems, distributed systems, and programming languages, and the talk he will give today, as the title says, basically is also in this space. So without further ado, please join me in welcoming Joe here on stage with a big applause.
Thank you, Mary. You can take that.
Yeah. Oh, you have it. Yeah.
Thank you so much, and thank you so much for having me. It's a real honor to have been invited to speak to you. Thanks for getting up and attending. It's my pleasure to be here. So this is joint work, as most of my work is, with just brilliant, wonderful people who I won't have time to really devote to today, because their work is what I'm going to be talking about. Most of these folks are people at Berkeley, with the exception of the people in the gray box who are employed by Sutter Hill Ventures, and my postdoc, May Milano, who's on her way to the faculty at Princeton, but is still at Berkeley. Okay, there's this story we tell in computing, at least in the system side of computing, that with every new architecture comes a programming environment that unlocks the potential of that architecture. And this story kind of goes back to the Ritchie and Thompson Turing Award and the fitness of Unix and C to the mini computer. But you can think about programming libraries and languages and environments that have been developed or accompanied each one of these platforms that allowed developers to build software that was well suited to these platforms. What's interesting is that there's a platform that's as old as the iPhone that really doesn't have its own development environment, and that platform is the cloud. Strangely enough, we're mostly still programming the cloud in sequential languages that were designed long before the advent of widespread distributed programming. And as I'm sure you're all aware, essentially every program you use now is a distributed program. When you're on an airplane, this becomes painfully evident, right? Your Microsoft Word is a distributed program. Everything is in some way interacting with multiple computers these days. And the question is, how can we make it easy for people to program the cloud in ways that, like with the iPhone and the whole idea of there's an app for that, that would allow developers who maybe aren't interested in the platform, they're interested in the applications, to foster the kind of innovation that the designers of the platform never even expected. And of course, the challenge is that distributed programming is very hard. You have to deal with all the issues of parallel programming, as well as the latencies and failures that happen in distributed systems. So then you have consistency issues and partial failure issues and fault tolerance issues. The rise of auto-scaling as a way of making cloud systems cost-efficient only makes this more challenging because the software you write needs to be able to grow and shrink while it's running. It's not like we ship executables anymore. We ship these things that are kind of breathing and living. So it's all very challenging. And frankly, today's compilers and interpreters don't answer the questions that programmers in these environments have to deal with when they have bugs. And so can we do better? I think this is one of the biggest questions in computing, and I've been slowly beavering away at it with my students for quite a while, and it's somewhat embarrassing how long it's taking us to make progress in some ways. I feel very humble about the problem because it's certainly taking my team a very long time to make progress, but we feel like we are slowly but surely making progress. You might ask why a database person like me is even working on this. What do I know about programming languages? Never took a class in programming languages, know very little about them really other than as a fan and a user. But the inspiration really comes from the roots of my own field. So this is Ted Codd, who you may or may not have heard of in your field. He won the Turing Award way back in 1981 for his work in the late 60s defining the relational model of databases. And I think a modern way to think about Codd's innovations were that he was a person who really said that specification should be formal. Think of formal relational languages like the relational calculus. And implementation should be automated by software. And the important thing about this is that implementations can change and adapt over time while the specification remains unchanged. And so when you think about this, he's sort of evolved in some ways. He's passed, of course, but I like to think of the analogy here. Relational databases, as Codd envisioned them, were invented to hide how the data was physically laid out on disk drives, and then how the queries over that data would be executed. And when you think about the vision of what the cloud should be, it was invented to hide how all computing resources are laid out and how all computations are executed. And that flexibility to change the execution is very endemic to this idea of elastic auto-scaling systems. You really want your programs to change while they're running, even though the specification remains the same. All right, so this is why I felt like many years ago that database folks might have something to say in this domain and should get smarter about programming languages and how they're designed and how people use them. So I did some work on programming languages. We have a formal language called Daedalus, which is a distributed data log, which is what we use for much of our formalisms. We had an earlier language called Bloom, which may or may not have wafted past your attention about 10 years ago. The Hydro project is our current project and a much more serious effort. I will say that before we started this project, though, I had students doing systems work. They just wanted to build the kinds of systems that these languages would make possible. And so I'm going to use one of those pieces of work as motivation and as a sort of running example in this talk. And it's a system that's a key value store. So it's a kind of database that just stores, it's like a distributed hash table, if you will. Okay? And for me, this is like the petri dish of distributed systems, or the hello world of distributed systems. But it's a lot richer than hello world. It's got problems in it. So algorithmically, it's trivial. But it forces you to focus on questions of data consistency, questions of performance, and questions of fault tolerance. And there's a wide range of ways you could deploy this to make it elastic, fault tolerant, and so on. And so we had a series of papers that my student Chenggang Wu won a bunch of awards for, actually wonderful work, on this system called Anna. Anna is the name of the world's fastest hummingbird. It's actually the fastest animal on the planet for its size. And it was tracked at UC Berkeley. The ornithologists at Berkeley measured its speed, so that was why we chose the name. So I don't want to go through all these charts. Anna scales linearly, super smoothly across cores and then across machines. So the top chart just shows it scaling linearly. It's extremely fast, even under contention. Many writers trying to write the same key on multiple threads, or if you will, multiple cores. We don't really use threads. And it can be hundreds of times faster than the state of the art. So in this community, perhaps the Intel thread building blocks library is something you're familiar with. We can be 700 times faster than Intel TBB on these highly contended workloads. Other systems were either faster or more cost effective. And with this, we can provide stronger consistency guarantees than many of these systems, and actually pluggable guarantees. You can choose your consistency model by plugging in an appropriate semi-lattice into Anna, and we'll talk more about this during today's talk. I would like you to focus particularly on the bottom right chart. This is why our performance is so good. In Anna, we spend 90% of our time, even under contention, on what's called good put, on doing actual good work, so on doing puts and gets, whereas all of the other systems we measured spend most of their time just retrying atomics. We didn't do any lock-based systems. They would show a similar behavior. So these systems are spending all their time coordinating and none of their time doing good work under contention. Anna is always putting and getting nearly all the time, which is why it scales so beautifully. Anna was handwritten in C++ by Chen Gang, who's a wonderful developer, and his implementation is correct by assertion, as many such implementations are. It's right because we say so. And you know, that was validating for the design pattern, of course, and we'll talk more about these lattice-based design patterns, but it's not, you know, proper programming languages work, and it's hard to translate across other programs. So the question is, can we make this kind of work easier and more reliable so that anybody can launch things into the cloud very easily? Okay, and with that, I'll give you an overview of kind of what we're doing in Hydro. The long-term goal is to build a language stack, very much an analogy to LLVM. We're very inspired by LLVM, also by Halide, which was the work my colleague Jonathan Reagan-Kelly did. And the idea, of course, is to have optimizations, particularly targeted to our environment, right? But also guarantees for correctness of the code. And the correctness guarantees we want are not the traditional compiler guarantees, they're distributed systems guarantees. I want distributed consistency to be guaranteed, right? Things like that. I want fault tolerance to be guaranteed. So what can a compiler do for me in that environment? And you know, the usual goals you might think of, it should be fast, so particularly interested in low latency because these distributed systems are often interactive services. It should also be flexible. I've tried selling a language. Bloom was an effort to sell a language a decade ago. That was very painful. I don't recommend it. I didn't try very hard, to be frank, but also no one paid attention, so it didn't seem worth trying. Instead, very much in the spirit of LLVM, we want it to be polyglot. We want to have multiple language surfaces on top of our compiler stack using an IR type approach. And then we want it to be cost effective in the cloud. We're now measuring dollars, not just performance these days, yeah? And so we had a vision paper on this some years ago, 2 years ago. Okay, this is the general stack, the envisioned stack for Hydro. So at the top, we want to support many languages. So we're even looking at taking sequential code when we can and trying to turn it into distributed systems, but also distributed programming patterns like futures and actors and functional or logic programming allow many of these languages to bloom, if you will, on top of our framework. And below that, of course, we're going to need some sort of internal representation. So we're tentatively calling this Hydrologic. This is a language that does not exist, but it has a very nice name. And the idea of getting from the outer languages into Hydrologic is a problem of synthesis in some sense. My colleague Alvin Chung is the person who developed what you may be familiar with as verified lifting, and we're taking some of his techniques and have had some success already in that space. But what we're going to focus on today is the single core IR, okay, so a lower level of the system, which is Hydroflow, which is a quite mature now, I mean, mature, it's about 2 years in, but we're building real things out of Hydroflow. And then under that, this gets deployed in the cloud. So the focus today will be on Hydroflow. It's a Rust-based internal DSL, which of course we then pass to LLVM. LLVM generates a binary. We call such a binary a transducer, which is a word I got from my theory friends, which is you can think of a system that takes inputs from the network and puts outputs onto the network. So it's just a fancy word for a executable that's in a networked environment. Many transducers makes a distributed system. There's no reason in Hydroflow for the transducers to be the same. They can be if you want a single programming, multiple data kind of environment, but they can also be heterogeneous transducers talking to each other over a network or over shared memory. Okay, so Hydroflow is an IR and a compiler, and of the folks in the group, these are the folks who've most worked on Hydroflow. Okay, so with that introduction, then let's get into the body of the talk. So it's got about 4 chapters. I'll take you through the IR so you get a sense of it. This is a shared nothing data flow. That's a database systems term. The only thing shared between transducers is a network or some sort of communication channel. So no shared memory, no shared disks. just network communication, all right? So you can set aside all your concerns about shared memory in this talk. There isn't any, okay? And that allows us to reason in a very nice way. It also allows us to get the kind of performance we saw with the ANA benchmarks. And then we'll talk about how we compile Hydroflow. It's a proc macro-based Rust library, and what kind of performance we see. I'll go a bit into the formalisms, which frankly are still work in progress. We were debating them over email on the way here. I decided not to present this as finalized work because clearly it's not, but I'll tell you where our heads are at. And then I'll talk about some of the results, if there's time, a level up from Hydroflow. It's sort of more the hydrologic level of how we optimize across transducers. Okay, let's begin with the transducer IR then. So it's a graph specification language, and Hydroflow, in essence, is a data flow programming model. It's a human programmable IR. It's embedded in Rust. So this is very much in the spirit of the IRs for LLVM and Halide. We want an internal language that's really a compiler target. It's mostly, we think, in the future, not going to be programmed by people. But if you're the kind of person who likes to get in and make the system really optimized, it should be in a human readable and writable syntax, okay? And that's what we'll look at today. Please keep in mind, if you don't like the syntax, we don't really expect you to use it in time. I use it, our team uses it, which will write papers, but the hope is that a compiler would be generating this code. Each transducer, as I said, is intended to run on a single core of its own. All right? And this is essentially a typed data flow graph type of language. And so there'll be statements like this one at the bottom, and you can think of them as data flow graphs like the one on the right. We can auto-generate these graphs so you can look at your programs visually. We'll see a few examples. And it's not a surprising data flow language. It's very much like other functional and data flow languages you've seen before. This is just screenshots from our auto-generated docs from Rust. These are all our operators. I'm not going to walk through them, but you'll see maps and filters and flattens and folds and stuff like that. Okay, so this is pretty familiar. Certainly not my intention to walk you through this. Again, it's a low-level language. Some of these operations are compiler target kind of fusions of multiple operators in one for efficiency, for example. So they're not very interesting, some of them. Let me take you through an example of how to build a key value store using data flow. It's desperately easy. All right? So this is a picture, sort of an abstract picture of a key value store that runs on a single transducer. Data, rather commands really, come in from the network. You can think of these as put requests or get requests to this hash table, this key value store. We demultiplex them, so the puts go one way, the gets go another way. And really the core of a key value store is just a database join, where whenever there's a get that comes in, we want to look up and see if there are any puts that preceded it that match on key. And that's it. So you can think of this as a streaming join, equi-join, if you will, of gets and puts. The puts get stored in the hash table of the join. The gets flow through and send their output to the requester back over the network. And we'll implement this now in the Hydroflow IR, and it's almost as simple as this picture. So here's the actual Hydroflow IR syntax. We can have a source stream, which we're going to do deserialization on. We're going to demultiplex it into the puts and gets, and this is the way we write this down. And we can assign this subflow a variable name. We'll call it network receive. And then we can keep building on this. So we'll call the outputs of network receive down the put channel, puts, and we'll call the outputs of network receive down the get channel gets. And those brackets that follow the operator, the put and get bracket, are just the enum types that are in this KVS message with adder enum. Okay? So there's one output for each enumerated type. And then the puts are going to go into the 0th operator of a lookup. The gets are going to go into the 1th operator of a lookup. And then here's the definition of a lookup. It's just an equi-join of the puts and the gets by key. And then the outputs go to the destination. And that's it. That's the program. I'm cheating only a little bit. This is what I'm cheating on. There's a bit of casting, all right, at least in the current syntax, to make sure we understand the types of the messages that are coming in and the types of the messages that we're sending out. This is a working Hydroflow program, what you see on the screen now, that implements a single node key value store. All right? And this is the data flow that's auto-generated by the Hydroflow system to let you sort of look at this thing if you want to see it visually. You'll see the join is the third from the bottom. That demux in the middle is sending the puts and the gets to the two sides of the join. Okay, so how do we make this a replicated distributed key value store? Well, here's the basic idea. We're going to have one more join. And that join is going to hold the names of everybody who's joined the system. So the names of all the transducers, names being, let's say, network addresses, so IP, comma, port. So if you get a peer join command in the demux, one extra kind of message now, we'll put that in a hash table here. And whenever we have to send out a result, a put result, we will do a cross product with that collection of peers, which is to say every put will get sent to every peer. Cross product of puts and peers. Okay? Every put gets sent to every peer. That's simply a Cartesian product or a cross join, if you will. And that's it. And we have to union the messages or multiplex them back onto the network. So that's the change to the program for replication. Now we can run these on many machines for fault tolerance or many threads. Right? For fault tolerance as well as for requests capacity scaling, right? Which is the kinds of graphs we were seeing. This is the code that we had to add to the program. I don't expect you to read it. On the left for the replication, it's just getting the peers, storing them in that hash table, and doing the cross join. In the background, there's one more bit, which is that if a peer gets a put, eventually it has to gossip it to everyone through that cross join, and that's what you see at the bottom. The entire data flow for the program is on the right. So it's 2 screens worth of code and one big picture. That's really an implementation of that ANA system that I described. Okay, so there's more power in this IR than I get to show. So we've got a new sort of language above it, just a little bit of a functional syntax that's been implemented by my student Shadaj Ladad, which he built a staged programming library for us to do this, because that's the kind of thing Shadaj likes to do on the weekends. So he's quite a developer. So we actually, as a result, have Hydroflow type syntax that is beautifully integrated into Rust using staged programming. So all of the goodies in your IDE work. So it really feels like you're programming Rust the whole time and you're getting all your type hints. It's a powerful language. It has all the recursion and so on. It supports cyclic graphs as in Datalog, and we allow negation-style reasoning using stratification, if you're familiar with that, much like Datalog. So we can do universal quantification. We can do familiar things from functional programming like folds. And these are all operators that you can think of as requiring their entire input before they produce any output, right? A fold, you have to get all the input before you produce the output. And this is very analogous to negation and Datalog, if you're familiar with that. And we can do that. We can actually do it with cycles through negation, which is usually considered not meaningful, but the way we do that is we separate things by time. And this is semantic work that we cleaned up in Daedalus many years ago. So there's one clock, one notion of time on every transducer that marches forward sequentially. And I encourage you to look at the docs if you're curious about the IR further. Okay, let's talk a bit about compilation and performance for this IR. So, you know, I had to live through all the years of MapReduce and whatnot, and the truth is batch processing data flow is really not very hard. Okay, and we do that, but event handling with extremely low latency is much more demanding, and that's what we set out to do when we built Hydroflow. And one of my master's students, now one of my programmers, Mingwei Samuel, is kind of a Rust guy and really thought about this pretty hard, and he has this lovely model of what he calls in-out tree partitioning. So you get a data flow graph, and we're gonna break it into these kind of trees that have ins and out operators, or if you wanna think about it, pull and push operators. And so Hydroflow, remember, it's a Rust crate that generates Rust code from graphs, right? That's the idea of the language, uses proc macros. So what we're gonna do is we're gonna take a graph like this one, we're gonna partition it into ins, which are pull, and outs, which are push. And we're gonna partition this into multiple of these in-out trees. And then we're gonna give it to Rust, and Rust is gonna inline the heck out of it. And it's really, really high performance. So think of this, I'm sorry, I went a little fast. This is a Hydroflow program for graph reachability, classic classic recursive program in Datalog, if you will. And this is how we turn it into an in-out tree. You pull from the left, you push to the right. So you can think of there's a sort of an iterator or a control at the top that's pull, 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 push, 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 pull, push, pull, push, pull, push. And it's trivial to inline this, right? Pull, push is just do the things on the left followed by the things on the right in a single thread. Okay, so you give this graph to the Rust compiler of this pull-push tree or in-out tree, and it inlines everything. And so it's extremely fast. Most of the competing sort of data flow systems, if you think of timely data flow also implemented in Rust, every stage of the operation is a function call. And so we're able to get much better performance than some of the sort of competing libraries on these kinds of programs. So it's really one inline function per in-out tree. Okay. Of course, there's more than one of these in-out trees in a program, and between them we're going to need some buffering, and that's what these sort of handoff operators are. So we're going to stitch a full graph into a cycle, essentially, of in-out trees. All right, this is a reminder of the slide we saw before. The question is, can we match this handwritten C++ in ANA? This was one of our goals 2 years ago when we set out to build a compiler, was to match the performance of ANA, because it was the fastest thing we'd built in my group in this style, and faster than other systems that it was competing with by quite a lot. And so we took essentially the code you saw on the previous 2 slides, and we deployed it on virtual machines that were very like the virtual machines that the ANA paper ran on. So on the left is the original ANA benchmark in C++, 2018. On the right, very similar instances. We're now in GCP, but we picked some sort of modest nodes there to match the performance. And you can see, again, the linear scaling. And the y-axis is about the same. I've tried to make the graphs line up. And so you can see that we're getting about the performance that we got with ANA with this high-level specification. Right? So we're starting to see that the raw performance of this compiler can match handwritten code that was really tuned to be very fast. So this is, I was super happy when we started getting these graphs. I felt like it should be doable, and indeed we were able to do it. Let me talk a bit about types and consistency analysis. This is part of the correctness goal of the project. So one of the key challenges in distributed systems is replica consistency, right? We want to ensure that distant agents that are running asynchronously, whether it's across threads or across the globe, agree or will agree on common knowledge. And the classic example is just simple data replication. I'm replicating keys in my key value store, or I'm replicating cache lines, or I'm replicating memory addresses, yeah? And the classic thing is, how do you know that your different participants agree on some mutable variable x? So in this little illustration, we have this couple, and they agree that x is love, and it's very lovely, but they're separated across the world. They have this shared knowledge. But time passes and things happen, right? And it's quite possible that they come to different conclusions without being able to communicate. So now they're not able to communicate, and unfortunately the person on the left thinks x is now poop. And it's going to cause all kinds of problems, because as they continue to compute with their assumptions, they will come to make very different decisions than perhaps they should. And in systems, sometimes we talk about this as split brain, right? The system now has split brain, and we shall never be able to make sense of it or put it back together. Now, this is all very nice, but it's also very old school in a sense. This is very what I call 20th century computer science. We're worried about reads and writes, very low level of semantics, like too low level, far too low level. What we really want to do is make sure that our program outcomes are shared across the distributed system. However cleverly we can do that, and maybe we can tolerate reads and writes being inconsistent for a while, as long as we can guarantee that our program will produce the right output. Right? I mean, most of the tricks that are played in systems are of that flavor, but they don't tend to be general to language analysis. They tend to be some sort of, in a special case, if I do this read and that write, it's going to work out. So we want to generalize this in a programming language and a compiler. Now, the classical solution is to just use coordination anytime that a reader and a writer or two writers can conflict. And what essentially we achieve is a global total order of operations, right? Something like linearizability, okay? And this is implemented at various levels of the stack in different ways. So on a processor, you might use atomics or critical sections. In a distributed system, you might revert to distributed protocols like Paxos or two-phase commit. And at every scale of the system, if you make this decision, you fail. It is just go slow. It's the go slow switch for computing, is to do coordination, right? And we saw this with the ANA benchmarks. These, the Intel thread building block library is lock-free, but it's not atomic-free, which means that when you have contention, it just retries and retries and retries and is doing 90% of nothing and 10% of good put. So this is expensive at every scale, and we really want to avoid coordination when we can. That's the game. So the big question is, when should we use coordination, and why should we use coordination, right? At some sort of high level. So when do I need coordination? And it turns out when I was starting to ask this question 10, 12 years ago, there wasn't an answer in the literature. The answers were very unsatisfying. People would say, well, you need coordination to avoid, when multiple parties are contending for a resource. Okay, but really, why do I need coordination? That seems very circumstantial, right? Here's a situation where multiple parties are contending for a resource. You can't be in the same place at the same time. I get it. But there's other solutions to this problem, right? This is a solution to that problem. Yeah, this is the Oakland maze. It allows things that should be in the same place at the same time to not be in the same place, right? By using some clever and very expensive engineering. But it's possible. So I want to ask the question of when do we really need to coordinate, right? Give me a theoretical argument for when we need to coordinate and when we don't, okay? So this is a theory problem, so we got to go to the whiteboard and think about it. Suppose you understand everything about your program semantics. Which programs have some coordination-free implementation where your favorite genius programmer could figure out a way to build it that doesn't use atomics or doesn't use Paxos? And which programs, it doesn't matter how clever your programmer is, there's no way they'll be able to implement it without coordination. And this is a computability question. I give you the language construct of coordination. What can you do with it, and what can you do without it? Right? So what is that green line that separates the coordination-free program statements, declarations, from the stuff in the red that is the rest of the programs? And it turns out there's a very simple answer. So this was a conjecture I had that better theoreticians than I proved, which is that monotonicity is the bright line between things that can be coordination-free and things that cannot. So a distributed program has a consistent coordination-free distributed implementation if and only if it's monotonic. And so we call this the CALM theorem, consistency as logical monotonicity. And there's a series of papers, mostly first authored by a guy named Tom Ameloot, who was a grad student at University of Hasselt in Belgium. And these are beautiful papers, very clever. I tried to explain them in sort of plainer terms to the broader community in CACM a couple years ago. So if you'd like to learn about the CALM theorem, this is a place to start. And then you can go read Tom's papers for the proofs. Now, as a constructive way to stay inside the green circle, a nice way to think is algebraically. And it's much easier to think about for most programmers as well than thinking about logic programming and monotonicity. So we've started to think more in an algebraic frame. Because it's a lot like functional programming, frankly. You've got operators, you string them together. It looks a bit like data flow or functional programming. And the key algebraic construct in this environment, which many of you probably are familiar with, is the notion of a semilattice. So a semilattice is a set and a single operator, all right? And that operator just has to be associative, commutative, and idempotent, okay? And so, the cool thing about lattices, if you haven't seen them before, is every semilattice corresponds to a partial order. X is less than or equal to y, if and only if x plus y is y, that y absorbs x. All right, and this corresponds to pictures like the one on the right. This is the classic set-subset lattice in what's called a Hasse diagram. So this is just a containment graph of the different points in this lattice. Okay? And because we have partial orders in our algebra, we're compatible, we can get to the top of this lattice, if you will, through many routes. So different nodes can go in different orders or different batches of tuples. Think of associativity as batch independent. I don't care what batch of messages you send me now and what batch you send me in a minute and what batch you send me later, it's associative. Commutativity is order insensitive, right? I don't care what order these things come in. And then idempotence is duplicate insensitive, right? So we can climb this lattice in many different sequential orders, which means different machines can run in different orders with different batching and still get to the same result. Right? So this is the flavor of a thing we want, so it's intuitive that this works. And the connection to monotonicity is that what we're doing is we're going up in the lattice's partial order. This plus operator can only climb the lattice. You never go down again. Okay? And because you never go down again, you'll eventually kind of converge towards the top of the lattice. We'll talk more about this in just a minute. Right, but this is a way to stay inside the green circle. It's actually not even all of the green circle, it turns out. But it's a happy place where we can construct programs in the green circle, so that's good. And so what we really wanted, as we said, is to get consistent answers from consistent data. So suppose the answer to our program wasn't at the top of our lattice, it was somewhere in the middle. That once we got all the data from everywhere, we were going to land at this point x comma y. Okay? How would we agree that that's the end of the program? How would we agree that that's the answer across our nodes? Again, we could use coordination. We could use an agreement protocol like Paxos so that everybody in the system would say, yes, indeed, I got x, y, and no further. We're done. So that's one way to do it. But it's coordination-full. We don't want to do that. So when is it consistent to read without coordination? Only at the top. So at the very top of your lattice, whatever it may be, this is a very small lattice, but at the very top of your lattice, you can't get any bigger, right? Because you're at the top. And at that point, if you locally know you're at the top, you know everyone else will eventually get to the top. You can send your outputs to the user confident that everyone will agree with you, which is nice. But if it's a very big lattice, like all subsets of a gigantic set, you'll never get to the top. It's ridiculous. Like, how many database queries return the entire database? It's silly, right? And so what we're going to want to do is we're going to want to apply things like monotone functions that take us down to smaller lattices from bigger lattices. And I'll show you how to do this in just a second. But the idea is not to get to the top of some giant lattice, but instead to map ourselves into a nice small lattice that's the output of the program we really want. So here's a program that you really want. It's the program to find a pair of matching socks. Okay, so this is the matching sock lattice. We're going to assume you only have 4 socks. But the cool thing about this, if you know right, is how many socks do you have to pull from the drawer to get a match if there's 2 colors? 3 socks. Very good. All right. So if you think about it, this is the matching sock lattice on 4 socks. And what we want is the true-false lattice, really. Do I have a pair? So I want a function that will take me from the matching sock lattice to the, yes, I've got a matching pair of socks lattice, true or false. What is that function? Well, we can label the things that map to false and the things that map to true. And it's monotone, right? Everything above the green line is true. Everything below the green line is false. And that monotone function has pair. We know it's monotone because you can see, I mean, in the picture, it's obvious that it's monotone. But this is a monotone function from the sock lattice to the Boolean lattice. And that's how we're going to do computing in this coordination-free environment. We're going to need to get to the Boolean lattice via some monotone functions so that we can get to the top of a nice small lattice. It doesn't have to be the Boolean lattice. It could be another finite lattice that you usually end up at the top of. But this is a standard example, is to have what's called a threshold function that gets you into the Boolean lattice. And it must be monotone. If we had a red circle somewhere above that green line, it would be terrible because we wouldn't know if we were done again. We'd get over the green line, and then we'd say, uh-oh, what happens if we get to the red circle? Right? So it has to be monotone. That's what's going to allow us to cast this to the Boolean lattice. Clear? OK. And so what is Hydroflow going to be? Well, it's going to take lattices and use them in a couple different sort of clever ways. One is that we're going to give you coordination protocols. So first things first, if you want to do coordination, if you have, for example, a program that's not in the green circle, you have a red program, you should be able to implement it in our language. And the only way you'll be able to do that is if you have distributed coordination. So we ship with implementation of Paxos, which I'll mention in a bit. We also have a lattices crate that comes with the Hydroflow implementation. And the lattices we have are composable so that you can build up lattices of lattices of lattices, which is what we did in the Anna paper. So rather than writing clever lattices like the folks who work on CRDTs might do, where a clever PhD student makes up a lattice you've never thought of, we're simply going to compose very simple lattices to create richer structures. So the causal consistency lattice from the Anna paper is up on the right. It's a map lattice of a key and a max integer lattice, nested inside of a pair lattice with a value lattice. That's the values you're storing, nested inside of a map lattice with a key. All right, and I won't go through all this, but these are all very simple lattices that we compose together to get something pretty rich, which is causal consistency. Other things in distributed systems that are classic, so this is kind of a vector clock implementation, but you can get lots of other kind of classic things you want in a distributed system by composing very simple lattices. And in fact, Shadaj, who's the guy who implemented the stage programming, has a lovely paper at last year's UPSLA about synthesizing these kinds of lattices from sequential code. Right? Because these are correct by construction lattice compositions of very simple lattices, it's great for synthesis. The synthesizer can start putting together all these composite lattices and then checking if they're correct, if they do what you want. All right, so we have this lattice crate. We have a collection of functions or operators that can apply functions like maps and folds, and they can either be monotone functions or non-monotone functions. If they're monotone functions, we can talk about the program continuing to be coordination-free, right, as we saw with the sock example. And then we're going to have some data flow types and properties, which is where we have some work in progress that I want to share with you. So here's a little snippet of Hydroflow as a graph. And the question is, what are the types of the edges? So what is the type of the data coming out of each one of these ports on these operators? And so what we'll say is that everything is a sequence of some order. And the order is sort of happenstance or unknown. So we'll kind of make up or scolomize, if you like that word, a name for each one of these operators. This is the order A. Okay? So this is a sequence of type T with the order named A. And its properties are that the batches of this thing are coming in randomly. So we can't say how this stuff will get associated. Right? You might get 3 things this tick and 12 things next tick. We don't know. So it's randomly batched. And it may contain duplicates because it might be coming over a network where there's retries. Right? If you look at the second edge down, though, we've casted this into a lattice L. And so the type is now a sequence of lattice points. Right? Think of the circles in our diagrams before. And this map happens to be a monotone function, so the output of it is still a sequence of lattice points. It's actually still an L in this example, but it might have been in another lattice. And the properties have been inherited. We're still random batch and duplicates. And then there's a fold. So if I tell you that we're going to replicate this program, and on one machine we'll do a fold, and on another machine we'll do a fold, and things are coming in random batches, 5 things here might get folded, and 12 things here might get folded. Very clearly, the answers don't have to be the same, right? There's going to be inconsistency if you have networking upstream of fold. Okay? And that's a sort of easy thing to check through some transitive closures of these types, right? So if you have a random batch input to a non-monotonic operation, you'll get non-deterministic output. And you get a sort of red edge out of there. Okay? So that's the kind of analysis we're going to do to make sure things are all monotone or they're not. And when they're not monotone and they're downstream of networking, you have a problem. All right? So here's another example. All I've changed here is that this, the source now is local. So this is an iterator, not a network source. So if you look at the topmost box, it's source iter, not source stream. And this has properties none. So it's not random batched. It's the whole batch comes in the first tick. So every machine that runs this program will generate the same iterator with the same outputs. And so you can see that the properties are not random batch. The properties are none. And when we get to this non-monotone fold operator, it's cool. Because everybody's going to run it on the same sequence, the same order of the same data with the same batching. And so it should distribute just fine. So even though we're using a non-monotone fold operator, because it's not downstream of networking, we're good. It's not randomly batched. Okay? Similarly, if we had an operator that wasn't fold, but was something like a lattice merge operator that's associative, commutative, and idempotent, then we can be downstream of the network and we're still good. Because this is batch insensitive, right? We're associative, which means we don't care about batches. So replacing the fold with a lattice merge, we have a program that, again, can be replicated safely without coordination. This is the flavor of analysis we want to do. Okay, and if you look at the Hydroflow graph that comes out of the ANA key value store, there's no red in it. It's all green. And so just at a glance, we can see this is eventually consistent. You can replicate this across machines, and you will get eventually consistent outcomes from this program. Okay, so it's kind of that simple for monotonicity analysis. But it's in the type system and these little meta properties that we're playing with. Okay, I have a little time to talk about the future, if you will, of the project, talk a little bit about optimizations across transducers. So we're going to move up the stack a little to hydrologic. Okay, so think of this as a global programming model now. I'm going to do a specification that's going to run on however many transducers I need. I'm the programmer, I don't have to think about that. Except that hydrologic doesn't exist yet, so we used our old language, which is Daedalus, which is a distributed data log language. Okay, so we're going to imagine that we have a single machine that runs over time, and that's what Daedalus is for. It's a data log with time, essentially. And these kinds of languages can be analyzed for many properties, monotonicity being one of them, so we've just seen monotonicity analysis. But also we have things like functional dependencies from database theory that will let us know which attributes of the data determine which other attributes. So if you think about a hash table, the key determines the value. If you know what key you've got, you know what's in that hash chain. And if we partition our data on the same key across our machines, we can shard our program or partition our program, and it will remain correct in its union of outputs. So we can use this functional dependency theory to co-partition the state across the different machines through the data flow. And you have to work to make sure the partitioning works all the way through the data flow. Another thing we can do with a language like Daedalus is use rich database theory ideas on data provenance to understand how results get generated, why they get generated, and to do rich debugging of bugs, because you can see the full provenance of your outputs. And a theme here is that in distributed systems, the hard part's the data. It's the state and the messages. Things that we traditionally solve in a traditional compiler are not the distributed systems problems. They're problems we're going to solve with LLVM at the bottom of the system, right? But these distributed systems problems are going to be data problems. And so it's perhaps not surprising that using these kind of database type techniques is helpful. So some years ago, my student David Chu wrote a proposal to do an automatic optimizer for fancy distributed protocols like Paxos. Remember, Paxos is a coordination protocol. It is not in the green circle. It is the thing that allows you to be in the red circle. It's very coordination-full. It is coordination. But he claimed that he could use some of our techniques to optimize this. It took him about 3 years. The first paper is now appearing at Sigma in the spring. So it took a while because he had to learn Datalog and Paxos and Rust, all of which are hard. So what are the challenges in optimizing these protocols? Well, of course, the compiler is not going to understand Paxos. There's all kinds of global invariants. I mean, it's very few people understand Paxos, much less compilers. Every time I teach it, I have to reread it. And there's a lot of global invariants that are implicit in these things that aren't really spec'd out. And so how can we prove that if we generate a variant of Paxos, it's correct? If you go to a conference like PodC or even SOSP, you'll find new Paxos or new coordination protocol variants every year, and they're very clever. They're too clever for a compiler to figure out correctness. The equivalence of Paxos outputs to these programs' outputs would be very hard to prove. And indeed, nearly inevitably, there's a paper the next year that says, we found bugs in the protocol. It's just, the literature is like that. It's very tricky, and there's a lot of edge cases. So what we're going to do is something much simpler that should be appealing to compiler folks, which is we're going to do very simple local transformations, where each local transformation is proven to be equivalent from the input to the output. And we're going to do like trivial transformations that come straight out of query optimization for parallel databases. One is to take a program like this component C on the left and break its data flow into 2 different threads that communicate over an asynchronous channel. We call that decoupling. This is like refactoring your program into different subgraphs and having the subgraphs compute over the network. And then the other thing we're going to do is this partitioning I was alluding to before, where you take a component and you hash partition the state and the messages so that each node is responsible for a partition of the messages and the data. Okay? With these 2 simple transformations, we had a paper some years ago. I actually don't have the citation. I think it's VLDB 21. I had a student, Michael Whitaker, who did this by hand. So again, handwritten in Scala, correct by assertion, okay? But he was able to show that he could take simple multi-Paxos, and without any of the fancy stuff that's in all these other papers, just using these basic ideas mostly, he was able to get performance that was about as good as these very complicated, often buggy protocols. The hard part in systematizing this, though, to sort of, we call this auto-Whitaker, because we had to make Michael Whitaker automatic because he got his PhD and left, didn't have him around anymore. And the hard part was when can you apply these transformations correctly to these data flow programs? So that's what David's been working on and what this first paper is about. And indeed, we get graphs of the sort we were hoping to get. This is a latency by throughput graph, and the way to read these is, when things start to curl backwards, they have saturated. So they're not getting better throughput without sacrificing latency, right? So when these curl backwards, you've sort of saturated. And what you're seeing here is this pink curve here is what Michael was able to achieve in Scala with his compartmentalized Paxos paper. And what you see in blue is just Hydroflow using these rule-based optimizations I showed you in the previous slides. So we took a simple Paxos implementation in Daedalus. We applied these rules systematically to that program, and we got this performance. The yellow curve is sort of just bragging about what Hydroflow can do, because this is actually taking all the tricks from Michael's paper, including ones that can't be achieved with those rules, and rewriting the program to use those tricks. And in that case, what we're just seeing is that Rust and our compiler is faster than Scala. So the yellow curve is the same logic as the pink curve. We get a little bit better throughput latency. But the blue curve is fully automatic optimization in the sense that it's just rewrite transformations. Now, really, David's only halfway there. That is, the rules are proven correct, and they can provide the wins, but it's not automatic yet. He applied those rules by hand. Each time he applied it, it was correct, but he chose which rule to apply where. So what we still need is a cost model for an objective function, for an optimizer. We need to be able to say which of these transformations are better than others, and then a search technique to find the optimal rewritings in this cost space. And this turns out to be very similar to query optimization or to e-graphs, depending on where you grew up. I'm happy to have Max Wilsey joining us at Berkeley, because it turns out that classic query optimization and e-graphs are if they're not isomorphic, they're damn close. They're really, really close. So we're working this out, but we're using Max's egg library to implement the optimizer for this stuff. Okay, I'm going to wrap up. We have a set of other open questions, which perhaps in the interest of time I will skip because we're nearing the top of the hour. But the design of HydroLogic is one of them. We want to support specs for performance SLOs like cost, latency, and uptime. And there should be facets to this thing, like what consistency level do you really need for which API? And do you want to layer in some kind of security of various kinds? And the Hydroflow Plus language that we're tucking in there may help. this auto-scaling fault tolerance bit of the project is an interesting open set of problems. And then, how do we translate from these libraries down to our IR of hydrologic? And we've got our first results last year at Uppsala. There's more to be done here. I think some of these will be easy. Like I think actors are pretty much the same as transducers. And futures, I think we can handle very neatly as well. Final thing I'm going to say is that, in this picture, right, the hope is that you program in one paradigm and we translate it to our IR. And this became much more realistic to us with LLMs in the past couple of years. We really now think it would be easy to translate these programs into Hydroflow. I could get ChatGPT to do it. It's just, of course, the question is it correct, right? But I believe this is exactly what declarative specification has come to be, is it's going to be this narrow waist between the generative AI, the green goo of AI, if you will. So this is unformed, kind of messy code generation and reliable building blocks. And what's needed is a formal language in between, one that we can render to humans so they can eyeball it quickly. This is not a programming language design goal that's been traditional. I want a language that's easy to read. No one's ever going to write it other than a computer, but it's got to be really easy to read. I think that's going to be one of the key challenges in this environment for programming languages. And then, of course, we need to translate it down to formalisms for correctness checking. Right? And declarative specification as this narrow waist between the two is going to be, I think, a very lovely way to do this without overfitting the implementations down below. All right, that's all I prepared for today. Thank you for your attention. And I love to geek out about this stuff. I'll be here all day. So if you're interested in distributed programming, please corner me. I'm here to chat. Thanks.
Thank you very much, Joe, for the very interesting and amazing talk. And I am sure there are questions in the audience.
Yes, in the back.
So, microphone. Okay. It's good to run.
Yeah, I was just wondering, this looks a lot like propagator networks. I was wondering if you've ever looked at the research that was done in that field, and if there's, what are the differences could you learn anything from them? Or
I don't know about that, so I'd love to learn more. Maybe we can talk afterwards.
Absolutely.
Yeah, great.
Okay, so maybe.
Hi, thanks for the talk. Are there any special, let's say, optimization or affordances that you can make in the case of cloud computing, where you have a better controlled safety and security and failure model, as opposed to general distributed computing?
Interesting. I think where that would tuck in is in trying to meet specs for fault tolerance. So if you told me, you wanted this to be up 99% of the time with this much latency, I would need to reason about such things. Honestly, we're not quite there yet, and it's a little easier for me to think about everything being independent failure, but of course that's not true. So what you're proposing is a very controlled form of correlated failure, I guess you could think, or correlated non-failure. And my hunch is that that's all going to go into some kind of model for quality of service or SLOs, and that's the place where the boring part of machine learning is applied. You learn a model, it works pretty well, you give a guarantee to your customer, and you get so much money, because you really are learning about correlations. But I think perhaps what you're pointing out is we can know something that we don't have to learn there that might make the problem easier, and that seems feasible to me, but we haven't done any work there yet, yeah. It might be that those are just models you just learn. We'll see.
Hi, thank you for the talk. You had this slide about data flow properties and types. Are you aiming at targeting a specific set of fixed properties like randomness, or are you also aiming to support like application-specific properties like invariants, and then you could maybe check where they get lost in the lattice, for example?
Lovely question. So this is the sort of thing the reason that this is work in progress. I don't have a clean answer to that yet. We haven't even settled on the core properties that we want. We don't want to admit a full sort of SAT-solving kind of problem here till we get what we like, and we're sure that it can be done efficiently. After that, I mean, I think it should be sort of, it's the usual transitive property assertions. I don't know that we'll have anything clever to say, but opening the box, it seems to me, then opens us to full verification, which It's not something we'd like to do in the core of the system, certainly, but it's very natural. And a very clear analogy to things like taint propagation from security. Yeah. Thank you.
Joe, thanks for the talk. I have a few questions regarding, often when you're building these kind of large-scale distributed systems, the distribution of the data comes into play, right? You have to think about how often will a particular kind of operation happen, and that should control it. If you finally want performance, it has to control how you partition things.
Indeed.
So where in this framework do you see that coming in? Yeah.
Great. So two places. It comes in two forms, and we did this in that second Anna paper sort of by hand. I mean, it was an auto-scaling system, but replication and partitioning. So you want to do replication for proximity, for geo-proximity, so to reduce latency, and of course for fault tolerance. And you want to do partitioning for absolute system scaling, right? So a data item might not be available at every node because that node can't hold everything. And so those are the simple levers that I think allow you to do this. And then again, it's a bit of a performance measurement kind of thing to adjust those levers. And in Anna, what we did was we used the key value store to hold its own metadata. So you would publish performance results into certain keys, and that was a way to propagate information about system performance through the system, and then it would adapt itself by reading those keys and looking and seeing how it was doing. And then one can ask the usual system performance questions of, how do you do with different workloads and so on. And again, this is a workload prediction problem that's probably well suited to simple machine learning models, which is the kind of thing we did in our Anna implementation, but it was very custom. So I think as a toolkit builder, we'd like to make those boring systems papers that are doing little scheduling tricks or little adaptation tricks, that should be libraried out so programmers can train and borrow those models. And I think that's a maturity aspect of the project we're not at yet.
Have you done any work on sort of upgrading the data flow logic transducer by transducer, sort of versioning the actual program itself, and sort of anything you might be able to do there and changes to the program you could do and distribute in a sort of replicated way?
Wonderful. I think there's a couple of questions there that I'm not sure I'll successfully unpack on the fly. There's a software versioning question, obviously, and a network protocol versioning question. And then there's a live distributed system kind of rolling migration question in there. And there's a lot of conventional wisdom from people who've been building these systems. And I believe there are tools in the environment that help with that, but we have not yet incorporated them here. And there's at the bottom, I had a thing called Hydrodeploy, which I blithely asserted exists. It's very primitive right now, and I think there's lots of interesting sort of systems work to do there. And I don't have any new ideas there yet, but I think there is quite a lot of work to do there, so it's a great question, yeah.
Thank you for the very interesting talk. I wanted to ask, you showed this data flow definition of the ANA KVS or something similar, and that implies that there is a notion of data persistence to your data flow. And I was just curious, how do you know what data to persist between data flows?
Yeah, so in the spirit of this being a low-level IR, it's specified expressly in the operators. So the operators have type parameters for whether they're static, which means the data is persisted across ticks, or not. So folds and joins, all the stateful operators, all of their input ports can be specified as static or tick. And you do this by hand because it changes the semantics of the program. Yeah, so it's part of the specification. I elided that a bit on the screen, but in those joins where I had a can on the left and no can on the right, they were static, comma, tick. Yeah, very good. And of course, data persistence is the whole problem at some level. So that's why I work on this. Over here.
Sophia.
So you whetted our appetite by talking about a specification language, and then you didn't show us anything. I was wondering...
Lovely. I love such a question. That's great.
But please tell us a little bit, and in particular, in this specification language, do you want to say things like this part needs to be sharded? Do you want to say this output can be off by the 10 latest inputs? Do you want to talk about these things?
Wonderful. And those were two very different things. So that was a lovely question. So absolutely, I did not show you a formal language, and I'm happy to be called out on that. I would encourage you to read the Daedalus paper, or papers. There's many of them. They have a model theoretic semantics for the language that is, quite nice. And that language is robust. It does not include the things you're describing. So on the one hand, it doesn't talk about implementation at all. It's a data log type language. So it doesn't say anything about sharding, but it admits the possibility that sharding could be there by having a notion of space. So things can have addresses. Your second question was, things like, can we allow this to be missing the last 10 items or something? As a data person, I'm rather skeptical of such things. I think the right specification is probably something about the values in the data, not the number of items. So distributed systems people like to talk about staleness, but they usually mean it only in terms of number of updates. And I'm much more interested in the content of the data. So is it off by epsilon, right? And so that's a question of what's the values that you're updating, how are you changing things? I think it's very interesting to think about this in a kind of probabilistic programming model environment. What could be the possible outcomes of an uncontrolled or a stale program? We're not doing that today. So we're mostly interested in exact consistency so far, or being able to flag that you don't have exact consistency, and then you have to reason about what that might mean for you. So we don't have tools for helping you figure out how inconsistent might you be. Yeah, but the former one about the sharding, I think, is a lower level than Daedalus. It's in the Hydroflow model. Yeah, yeah. Thank you for that lovely question. I appreciate it.
Okay.
Just a quick one. What are the workloads where the system doesn't do well at all?
Great. I think a lot, there's an analogy to, we came at this out of query languages. So, for example, low-level algorithms, implementing quicksort. I challenge you to do it in a language like Datalog. It's quite horrible. It actually, my impression is it can't be done. We ended up building a sort of extra control syntax to get quicksort to come out. You say things like, the thing to my left shall be smaller than me. Right? That's what sorting is in Datalog. And it does not lead to quicksort, it leads to bubble sort if you do semi-naive evaluation. So those kind of algorithmics seem to be very poorly suited to these languages. They also are not the kinds of things typically I find distributed systems people worrying about, but I wouldn't promise that we won't run into them. So it's a great question, yeah.
Okay, we are actually 3 minutes above the time, but I will dare to ask a last question myself, like any plans, or are you already doing it, kind of automatically finding out where you need coordination? You said that you provide Paxos, for example, implementations as libraries.
Yeah.
But is the developer then supposed to find out where to use them, or any automated reasoning?
Sure, yeah. So that, that sort of green edges in the graph picture with the case where there's a red edge, yes. The red edges are where you need to coordinate if you want consistency. And so right now we're not sticking Paxos in for you, but that's just a macro. And so we're not doing it automatically, but the programmer could easily do it using a macro anywhere they see a red edge. What's a little more challenging is to prove that your implementation of Paxos restores consistency. Can you prove that Paxos is doing its job? Is my implementation of Paxos indeed going to produce the same outcomes in the same order on every node? I would like to do that. I feel like that's doable, but we haven't done it yet.
Thank you very much again. Thank you for being here with us today. Join me in saying thank you.
Thank you.
Okay. Good morning. Welcome to the session on type systems. Our first talk will be Ellen, who will tell us about reference capabilities for flexible memory management.
All right. It's nice to be here. I'm Ellen. I'm coming to you here at Uppsala from Uppsala University in Sweden. I'm here to talk to you about reference capabilities for flexible memory management. Okay. I just want to say that this work is part of a larger project called Project Verona. It's a Microsoft project, and we have the end goal of creating a new programming language for cloud infrastructure. So let's get started. So in modern programming languages today, we seem to have this balance between memory safety on one hand and the amount of control a programmer gets with regards to memory management. So, for example, we take Java. Here, memory management happens completely automatically, which is, of course, very convenient for the programmer. They don't have to think about it. On the other hand, this lends itself very poorly to the kind of domain-specific optimizations that we all know and love. For example, if we have a resource that we know that we're not going to use anymore, we can't tell the system in some way that, okay, please free this resource immediately. We end up with a situation where this resource can take a considerable amount of time to actually get deallocated. On the other hand, we have languages like C++, where memory management happens completely in the programmer's control, which, of course, on one hand gives the programmer opportunity to make these kinds of optimizations, but we open a whole can of worms of introducing perhaps memory bugs in our program. Somewhere in the middle, we have languages like Rust, where the type system is able to reason about object lifetimes. So as long as we stick to the safe portions of Rust, we are sure that resources will be freed as soon as they're not used anymore. On the other hand, Rust kind of limits the expressibility or what data structures we can actually express, at least in the safe parts of the language. So what actually tends to happen is that people either need to write unsafe code themselves, or they need to at least use libraries that has this unsafe code. So what we wanted to do with this work was to kind of explore the space to try to keep the safety aspect of Java, but also give the programmer more control over memory management. So our system is called Regio, and we had set up a few goals for this system. First of all, we want the automatic memory management, since it's convenient and it ensures safety in our program. Second, we would like to have some kind of localized memory management, so that we are able to reason locally about what objects are used and what's not used, like currently in our program. This gives us a more predictable, or hopefully a more predictable, memory management overhead. Finally, we want a mix and match memory management strategy, so we're able to choose for a portion of the heap, for example, that it's supposed to be traced. Maybe another portion is supposed to be reference counted, and so on. Finally, we wanted our system to be as simple as possible to use, we've already seen with languages like Rust that people have difficulties when trying to learn them and reason about them because they're more complex than the earlier languages like C and Java and so on. And it's kind of a whole different dimension of reasoning. So we wanted to keep our type system as safe as possible. So what is Regio? We can imagine that we have some kind of heap. We have objects and references between them. The first restriction that we put in place is that we divide our heap into regions. So what this means is that each object is contained in exactly one region. Our second restriction is that we disallow certain shapes of this region graph. So all the regions form trees. So for example, here we could remove these two edges and end up with a tree-shaped region graph. Next up, as you can see here, we're kind of moving between the regions in last in, first out manner. So we basically have explicit open and exit operations, and we need to do this entering and exiting in a last in, first out manner. And this is to give access to or give our program access to different parts of the heap. Depending on where we are in the heap right now, we get different access permissions instead as well. I'm going to explain these terms shortly, but we have the closed regions, which are the gray ones. We have the the active regions, which is the yellow one. And then finally the suspended regions, which are the red colored ones. And we do all this to enable this localized memory management. Finally, we enforce this statically using a reference capability system. So we basically tag each reference in our program with some additional information to allow us to reason about what relation, like the objects it points between has. All right. So closed regions are not part of this region stack that you saw earlier. This means that our program has no read or write permissions at all inside this region. We can still move the incoming pointer to this region around in our program, and we can also like drop it, for example. But we have no actual access permission inside the actual region. If we move on to the active region, it's on the top of the stack, of this region stack. And we have both read and write permissions. Specifically, we're allowed to allocate and deallocate memory freely, or the program has permission to do this. Next up is the suspended regions. So they are part of the region stack, but they're not on the top of the region stack. Here, the program has read permissions, and we are also able to alias from region frames higher up the stack. So for example, this reference here is permissible, but it's read only. So what do we actually get for all these, from imposing all of these restrictions? So when reasoning about liveness, we can see that for the suspended regions, liveness depends on the program frames and also, of course, the region local heap references and this incoming reference. But since the but since this region is read-only and these additional references are, like the red ones in this picture, are lifetime bounded, we can reason that we don't need to care about this region from a memory management perspective, since liveness won't be affected until we actually return to having this region as active. For the closed regions, we only have the local heap references and this incoming reference. Since the local heap is not mutable, the entire liveness situation boils down to this single incoming reference. Like, does that exist or not? Yes, and finally, liveness in the active region. Since we can mutate the region, we need active memory management. But basically, this boils down to a local property, liveness, that is, because we only have the local program frame and everything else is kind of region local. So liveness is a region local property. So in the end, we get a situation where this active region basically decides where we are able to mutate. And we can move this kind of window of mutability around in the heap in this fashion, in this last in, first out fashion. And we get we can reason about only the currently active region when reasoning about mutable state and memory management. So to give you some idea of what we imagine that you could do with this, imagine that we have this large region with a lot of objects in it. And imagine that we need to kind of restrict the amount of memory management overhead and kind of try to keep it as low as possible. In this figure right here, you can see that we're able to split this big region up into several smaller regions. And then, depending on the region, like the internal structure in the region, we as programmers can choose to have different memory management strategies in all of these. So for example, in one we could have tracing, in another one we could have reference counting. So to go back to the kind of goals of our system, we do get automatic memory management. We get localized memory management since each region is memory managed separately, and also we can reason about the overhead and a bound for the overhead in terms of the size of the currently active region. Finally, we get this mix and match property. Since we're able to choose freely whichever memory management strategy we have for each region. These properties basically boils down to this topology invariant that we have in our paper. I'm not gonna go through it in detail right now, but please read the paper if you're interested. So where does this leave us in terms of this whole picture that I showed earlier? We believe, at least, that we're able to kind of retain the safety properties of Java, for example, but still give more control to the actual programmer in terms of reasoning power and actual implementation level stuff. There is more stuff in the paper. For example, additional features like immutability and changing the region entry point. We have a description of the whole type system with reference capabilities, also comparisons with other systems, code examples, and finally a formalization and soundness proof. Furthermore, there's going to be a talk later today about a concurrency model that we have that we imagine can be combined together with Regio in order to get a very concurrent, yes, in order to enable a very concurrent program. All right, I think that's about it. So thank you for listening.
Okay, we have time for a couple of questions. If you have a question, please come up to one of the mics in the aisles here. So.
Hi, Jonathan Aldrich, Carnegie Mellon. Really interesting system. I think for me the biggest question is, is this practical for writing programs? Can we structure programs the way that we need to and make them work? Can you give me the intuition for why you believe this will be, will match the way people want to program?
We're working on an implementation right now, so hopefully we'll get something up and running that people can try to use. We do have some kind of code examples in the paper as well of a system that it's basically like a small server that handles requests. So I urge you to maybe read that if you're interested, and maybe we can talk a bit more later, if that's okay.
Thank you.
Okay, and one more question.
Is there any sort of region inference, or is it just the region management itself is a explicit operation?
At the moment, there is no region inference. No. Okay. So you have to write out region creation explicitly.
Do you think that the region inference algorithm could be devised that's still compatible with the whole system in principle?
Yeah, definitely. That's for sure an interesting kind of future direction.
Okay, thank you.
Okay, I'll have one more.
When you create a new object, does it go in the region you're currently executing into?
Yes, exactly. So when you allocate an object, it's always created in the currently active region.
So is there a way to move objects between regions, to merge regions?
Yes. No, sorry. There is an operation, I think I forgot to mention it, to merge regions. So it's basically, if you have a closed region, you can merge that into the currently active one.
Okay. Let's thank Ellen again then. Here we go. Okay. Now, Will tell us about a grounded conceptual model shift for ownership in Rust.
All right. Hello, everyone. My name is Will Creighton. I'm a postdoc at Brown, and this is joint work done with Gavin Gray at ETH Zurich and my postdoc advisor, Sriram Krishnamurthy. By the way, I'm on the job market, and Gavin is applying for PhD programs. So if you like what you see in this presentation, come talk to us. All right, so Rust is a language for safe systems programming that is popularizing the idea of ownership types to get memory safety without garbage collection. So if you have a program like this that uses a reference after it's been invalidated, that is unsafe. And if we try to compile it, Rust's borrow checker will flag it as a problem. Cannot borrow V as mutable because it is also borrowed as immutable. So great. Rust is a smashing success story of PL theory transfer to practice. Time to move on. But no, it's not that simple. In survey after survey, we find that ownership and lifetimes are the hardest part of Rust to learn. They actively turn people away from the language. And so if we want to make Rust accessible to a broad audience, then we need to make ownership types easier to learn. And that's exactly what we did, but in a more systematic way than just inventing pedagogy out of thin air and hoping for the best. Instead, we wanted to first understand the misconceptions about ownership that Rust learners had, then use those misconceptions to become the basis of a new pedagogy to address them, and then finally compare the pedagogy against a baseline to evaluate whether it makes a difference. And now let's walk through each step. So first, we wanted to understand misconceptions of ownership. And our orienting principle was to create a test of ownership, like an exam you could give to a learner. And to start constructing a test, we needed a set of problems that represented common situations involving ownership that are difficult for learners. So we looked to Stack Overflow. We analyzed the most frequent questions about Rust to find the ones related to ownership. And they looked like this. Is it possible to return either a borrowed or owned type in Rust? And out of this question, we extract a simplified code snippet that represents the situation. So here, this makeSeparator function wants to return a reference to a string and stir. But in the if branch, it returns a reference to an owned string on the stack, which is not safe. And for each of these snippets, we ask 3 questions to mirror each stage of reasoning about ownership. So first, what error would Rust give for this program? Second, if Rust allowed this program to compile, what is an input that would violate memory safety, if one exists? And third, how would you idiomatically fix this function? And we ask people to justify the latter 2 answers. Now, these are open-ended questions. There's not one correct answer. But for this problem, I would give this as a correct answer. Default does not live long enough. To violate memory safety, we have to call this function and use the output. And a simple fix is to change the output type to an owned string instead of a reference. And in total, we found 8 of these snippets that correspond to these categories of ownership errors. I won't go through them all, but if you've worked with Rust before, they should all sound familiar to you. With 3 questions per snippet, we have a total of 24 questions that form the open-ended ownership inventory, with the term inventory coming from the idea of a concept inventory that's used in education research. And so once we constructed this test, we recruited 36 Rust learners who had recently finished reading The Rust Programming Language, which is a popular open-source Rust textbook. We had them answer a randomly selected subset of the inventory. And afterward, we manually read through all the responses and started to look for misconceptions. So what kinds of incorrect errors did people give to these questions? And overall, what we find is that learners understand ownership syntactically and not semantically. And so what I mean is that learners can successfully predict the compiler's error message in 64% of cases, but they can only write a valid counterexample in 31% of cases, and then only justify it in 15% of cases. And so here's just a concrete example from the data. Like, we have one task that uses this code where you have a struct self with 2 fields, self.getCurve borrows 1 field, and then this code tries to mutate another field, self.scores. And this is actually safe. This program is rejected due to the incompleteness of Rust's lifetime analysis. And here's one participant's response. They correctly get that there is a compiler error and they understand where it is, but then they attempt to provide a counterexample when none actually exists. And when they go to fix this function, they just throw a .clone on the scores vector, which is totally incorrect. It modifies a copy that gets immediately thrown away. And this is indicative of a deeper trend, where learners' syntactic understanding of an error led them to struggle down the line when trying to fix these functions in practice. And so after observing this data, we felt that what learners needed was a more robust mental model of the foundational concepts of ownership. Specifically, what kinds of undefined behavior are prevented by the borrow checker? And to a first approximation, how does the borrow checker work? Like, why does the Rust compiler reject programs that are safe? And the crux of the issue is the level of abstraction in the conceptual model that we're giving to learners. So the highest level would be like, Rust prevents memory errors. Lower level, maybe Rust enforces aliasing XOR mutability. Below that, Rust uses lifetimes to understand aliasing. And we can keep going. So a formal model describes how outlives constraints relate to alias sets. And then ultimately, a fully concrete conceptual model would literally be the source code of the borrow checker. And what we saw is that learners have a very abstract mental model of ownership. And we think they need a somewhat more concrete mental model. Like not all the way, but something concrete enough to explain the relevant behaviors. And just a note on the terminology, I'm using the phrase mental model to describe the model that exists in people's heads, and the phrase conceptual model to describe the model that exists in abstract formal space. And pedagogy is the thing that turns a conceptual model into a mental model. So we designed a conceptual model of Rust that could explain undefined behavior in the dynamic semantics and unsoundness versus incompleteness with regards to the static semantics. And we reified these models as compiler plugins that can automatically generate a visualization of a Rust program under each model. I'll show you what that means. So this is the visualization we generate for the dynamic semantics. It can take a program like the one you saw at the beginning, where we invalidated a reference to a vector, and it can visualize the state of the stack and the heap at multiple points in the program. Notably, if a program encounters undefined behavior, like reading a pointer after it's freed, we can capture that error and visually represent it. The design is pretty similar to other box and arrow diagrams people have made for C and so on. I'm not going to dwell on it too much. But one interesting detail is that we are executing Rust programs that don't compile, which seems a bit weird. And under the hood, we're using an interpreter for the control flow graph intermediate representation in the Rust compiler called MIR, which we configure to ignore borrow checker errors initially and then interpret the program until something bad happens. But in terms of pedagogy, the idea is that this conceptual model is sufficient to illustrate what it means for a program to have undefined behavior. But it isn't so detailed as to talk about registers, calling conventions, things like that. Just detailed enough to convey the essential concept. Now, the more novel idea is the static semantics. So here's our other diagram. And the idea is that we can visualize the change in the state of the borrow checker after each line. And we communicate that state through the metaphor of permissions. So this example is almost the same as before, except this code is actually safe because we swapped the order of the print and the push. And now we'll walk through it. So we create a vector v with elements 1, 2, and 3. And the little box on the right tells us that the variable v has gained 3 permissions: read, write, and own. So v is readable, like you could get its length. V is writable, you can add an element to it. And v is ownable, meaning you can move it or drop it. And on the next line, we make a reference num equals and v2. You'll notice this little orange dot, which indicates the expected permissions for an operation. So creating an immutable reference requires read permissions on v, which we have. And in terms of the borrow checker, this operation removes write and own permissions from v, which is because we can't mutate or drop v while this reference is live. And it also creates permissions for num, the reference, and star num, the data accessed through the reference. Because it's immutable, we only have read permissions on star num and not write permissions. Once num is no longer used after the print line, then v regains its write and own permissions. And this shows the idea of non-lexical lifetimes. So the transfer of permissions is related to the live range of a reference and not just syntactic scopes. Finally, we're allowed to push to v on the next line, and v loses its permissions once it's no longer used. And so at a high level, the permissions model provides a concrete way to explain how the borrow checker works without getting into all the details like liveness analysis and lifetime polymorphism. And here's a rough intuition for how it's implemented. We define a permission error on a control flow graph G if some place P needs a permission, like W, at some instruction I, and P is missing that permission at I. And this can be derived from a judgment that comes out of the borrow checker, which we call access error. And the derivation is that Access error has a bunch of premises that talk about liveness and reads and writes and conflicts. And our inference rules just shuffle around the judgments, so the entailment proof is quite simple. You can think of permissions as rephrasing the proof generated by the borrow checker in terms of our model, in terms of permissions. All right, so we have our executable conceptual models of Rust's static and dynamic semantics. But as I mentioned, we still need a pedagogy to convert that conceptual model into a mental model. As a base, we forked the Rust programming language, which I mentioned earlier, and we completely rewrote its chapter on ownership using the diagrams like you can see in the screenshot. This is a live public link at rust-book.cs.brown.edu if you would like to check it out after the talk. Put your phones down. All right, so finally, we needed to evaluate whether our new ownership pedagogy actually helped Rust learners. And the basic idea was to run an A/B test. To evaluate Rust learners' understanding of ownership, we used the ownership inventory we developed earlier, but this time it had multiple choice questions, with the key idea being that we based the distractors on common incorrect answers given by participants in the formative study from earlier. To recruit participants, the authors of TRPL graciously agreed to insert this advertisement into the main Rust book where it still stands today. This ad drives about 400 people per day to our experimental fork of TRPL. Then the procedure was that we first added the inventory to the baseline TRPL. We collected participant data for about 6 weeks, and this gives us the control condition. Then we deployed our new ownership chapter, fixed some bugs, and collected data for another 6 weeks. Between those two periods, we had a total of 342 people who completed the entire inventory. And our main result is that compared to the baseline TRPL, the permissions pedagogy improves scores by an average of 9%, which is a normalized effect size of D equals 0.56. So hey, look at that. It's a demonstrable improvement in learning outcomes directly attributable to our intervention. I think that's pretty exciting. And if we dig further, we can find that there were statistically significant improvements on 10 out of 18 questions in the inventory. In particular, the improved questions were primarily either the ones about picking counterexamples or the ones about fixing the code, and not the ones about identifying the compiler error. And we see that as a promising sign, because those were the two kinds of questions we really wanted to help people improve on. There are some threats to validity we discuss in the paper, but I think it's fair to say that our work is helping people better understand ownership types in Rust. To conclude, Rust is cool, but can we do this for other languages? Absolutely. So here's going to be the essential ideas I think you should reuse from this talk. So one is mixed methods analysis. Quantitative data from surveys and Stack Overflow provide a nice way to filter down signal from noise. And then qualitative data from like open-ended exams gives us rich substance to analyze usability and learnability. Another is concept inventories. Targeted multiple choice questions with good distractors are useful in both the formative and summative stages of research to find misconceptions. Modern languages are hugely complicated, and so we have to consciously design conceptual models at the right level of abstraction. And conveying a conceptual model becomes so much easier when you can show and not tell how it works. Conversely, designing your compiler so it can be visualized makes my life a lot easier, just so you know. And finally, A/B testing is great because you can evaluate your ideas with a ton of people by leveraging the resources they're already using rather than needing to continually recruit participants for individual user studies. Okay, that's all I have. Thank you for listening, and let's go make our programming languages easier to learn.
Okay, if you have questions, please come to microphones in the aisles.
Hi, thanks for the great talk. Do you think that there are differences in the types of misconceptions people have if you're thinking about like experienced programmers who are learning Rust versus novice programmers who are like Rust just happens to be their first language? And do you have any like commentary on that kind of thing?
Yes, so In particular, there's both are they experienced or not, but also what languages they've used. The experience of learning Rust, if you know C or C++, is very different. And in practice, we find that people who know C or C++, they understand undefined behavior really well because they see it every day, right? And so they go, oh, mechanisms that mirror the R-safe practices, it's very intuitive to them. But an important factor we've also found is more than half of the people learning Rust are not proficient in a systems language, or at least self-report as such. So I think that's one of the challenging things in designing these resources is you do have to consider the background, but we also have to be practical about who's learning the language, and you can't just target, say, people who already know something about C or C++.
Thank you. This was really a fantastic talk, like really, really fantastic.
Thanks.
I wanted to ask, how did you come up with this conceptual model? Did you just invent it ex nihilo, or do you also have a methodology for coming up with these things? I mean, the ones which work well. Right.
So we came up with the permissions model. Essentially, we were trying to, it was a very iterative design process. I can show you screenshots of 15 different lifetime visualizations that we didn't end up including, and we kept trying to think about it from different perspectives. Ultimately, our guiding principles were, can this particular conceptual model explain the phenomena we care about? And the two phenomena were, when there's an ownership error, can it highlight that error and explain it? And when there's incompleteness, can it give an explanation as to why there's incompleteness? So one notable thing we did not do, you'll see in a lot of other visualizations, is have a visualization of the live ranges of variables as like lines that run through the program. And that was also partly motivated, that was motivated by the fact that those aren't actually fully necessary to explain the phenomena we cared about, but also those are difficult to generalize to cases where lifetimes are nonlinear, which does happen in some of the examples we include in the book. So short answer is, a couple guiding principles to say we need to have something sufficient to explain this, plus just many iterations on trying out different visual encodings and seeing what worked.
Thank you.
Okay, sorry, but we don't have any time for questions. Let's take those offline.
Thank you.
Thank Will again. See, look there.
Yeah, it's on there.
Yeah, that's what's going to be mirrored. Yeah? Okay. Okay. Now Manu will talk about inference of resource management specs.
Okay, hi everyone. This is work that was primarily done by the first two authors, Nargis Shadab, my PhD student, and Preetham Gaurath, a postdoc at Microsoft Research in India. I'm giving this talk due to many unfortunate visa issues, but Preetham, the second author, was the one who prepared these slides, and I believe she's on the job market this year. Okay, so today I'm going to cover the following. I'll give a quick overview of some recent work we've done on a resource leak checker that works for both Java and C#, and it's kind of different than other tools in the space in that it's based on these resource management specifications at method and class boundaries, so we get some very nice properties from that. Then I'm going to talk about the main focus of this work, which was on inference of these resource management specifications. I'm going to talk a little bit about our experimental evaluation, and finally conclude. And I'll note many times in the talk and now that there's not going to be a lot of the technical details here. I really encourage you to read the paper to find out the full story on this work. So let me start with the overview. So what is a resource leak? Well, in Java and C#, we're talking about resources. We mean kind of finite resources in the system that you have to manage explicitly. So we're not talking about memory that is garbage collected. We're talking about things like file handles and network sockets, resources where you have to explicitly release them, say in Java by closing a file handle. So a resource leak occurs when a programmer fails to explicitly close this finite resource. And this can lead to a lot of problems, right? Resource starvations, system slowdowns, crashes, and it's really quite a bad problem because it's hard to test for. Often this manifests only when you've deployed into production and run for a week and all of a sudden things are going slower and you're not sure why. So it would be great if we could effectively statically detect these types of problems. So in recent work that was published in FSE 2021, we developed a resource leak checker, a pluggable types approach to finding resource leaks. In that work, we implemented this in the checker framework for Java, and subsequently it was implemented for C#. The resource leak checker uses a lightweight and modular and sound approach to preventing resource leaks. And the kind of cool thing here is that you can detect resource leaks without doing whole program alias analysis. So that's what makes it lightweight. But we do need these resource management specifications to understand how responsibility is being shared across method boundaries, and also in certain cases, what kinds of aliases are arising that are relevant here. So these specifications are great because they let us do incremental and modular checking very easily, and they improve the quality of the warnings that we can give in this checker. But someone has to write these annotations. We did it for the previous study, and we found that particularly for large legacy code bases, it was a lot of work, right? So this work that I'm talking about today was motivated by reducing the overhead for developers of manually adding these annotations. And with this inference system, now you can run this resource leak checker in a fully automated fashion. You can run it on an unannotated code base and get fairly useful results out of it. So after I tell you more details about the system, I'm going to show you some of our results where we compared between handwritten specifications and the specifications we're able to infer, and also just seeing how well does the resource leak checker run out of the box if we combine it with inference but don't do any manual annotation ourselves. So let me illustrate what's going on with this checker with a small example. So this is a code snippet, and it's actually fine. There's no resource leak in this code snippet, and the resource is up here. It's this SQL connection that needs to be closed. So let's see what's going on and why this code is free of leaks. So as I mentioned, our checker relies on some form of annotations to understand which alias is going to be responsible for closing a resource. And the annotation I'm going to focus on in this talk is one we call owning. Now, we've heard lots of great talks about ownership. I want to distinguish our notion of owning from the much stronger notions that you see in a language like Rust. Here, what we have is something we call lightweight ownership, and it's basically just a hint to our checker as to which alias is going to be responsible for closing this resource, but it does not restrict in any way how you can create aliases in your program. So here, and this is using a C# syntax for annotations with the square brackets. Here, the owning on the declaration of getSQL connection says that whoever calls this getSQL connection method is responsible for closing the returned resource. And down here in close connection, the annotation says, if you pass me a connection, this method will take responsibility for closing it. Okay? So those are the annotations. And based on this, we can see that this example is safe, right? This method creates a SQL connection, but it's going to transfer the obligation for closing it to the caller. And then this caller right here is able to satisfy that obligation by calling close connection. And we know that that works because we see this annotation on the parameter, and we can separately verify this method on its own that it takes care of that obligation to close the resource. So the other nice thing about having these annotations is compared to other systems, we can kind of give errors in more appropriate places. And in this example, the fact that we have this owning annotation here means we won't warn inside this method that you didn't close the connection. And you may think, well, of course you need something like this, but there actually are pretty common heuristic checkers out there for Java that don't even do this. And so they give you a lot of noise in the reports. But here, let's say you deleted line 11, we would be able to give you the error at this program point and say that here's the connection, and this method is responsible for closing it and didn't do anything about it. And there are many other types of annotations that I'm not going to get into detail, but they're very important. I encourage you to see the paper for more details on these. But we have annotations for wrapper types. So if you're storing a resource in a final field, we can support that. We can support aliasing between different objects that manage the same resource. And this is all critical for effectiveness in practice. Okay, so as I mentioned, annotating legacy code to work with our checker is a hindrance for adoption. We have our own personal experience here where we looked at some fairly sophisticated Java programs like Zookeeper and Apache Hadoop. And we spent several weeks trying to puzzle through the protocols and annotate a moderately sized program. And in the end, to be honest, we kind of gave up. And we said, we can't figure out everything that's going on in this program. What we're going to do is try to add annotations when they're using resource types in standard libraries. But if they have their own wrapper types, we threw up our hands and said, we're not going to try to figure this out. And so, given that we were highly motivated to do this, I'm not sure a developer who we're trying to convince to use our tool will be very convincible. So that's the main motivation behind this inference technique. So let me talk next about what's interesting at a high level about our inference technique. So this is not a straightforward problem because these resource management specifications have to capture multiple interrelated properties. So which alias is responsible for closing a resource? What are the obligations that need to be satisfied on different types? And when do we have aliases where it's fine to close a resource via either one of them? So we needed an inference. These are all interrelated. We needed an inference technique that could kind of simultaneously infer all these types of annotations. Another thing, the second bullet is key here, is that we found that we wanted to employ an optimistic approach to inference. So perhaps unsurprisingly, very often when you're applying our checker to an unannotated legacy code base, there are bugs, right? So we're never going to be able to find a set of annotations that makes it past the checker. So the question is, where should we put the annotations? And we tried to do it in a way that matched what appeared to be the developer's intentions. And that helps a lot because then even though it doesn't pass the checker, you get error messages in more appropriate places than if you were very strict and only inferring annotations that would be verified. So in the paper, you can see how we formalize the inference algorithm as a set of inference rules. It's using a data log style syntax, and then inference can be viewed as just applying those rules to a fixed point. And we have two different implementations of this. As I mentioned before, we implement inference for both Java, based on the checker framework, and in CodeQL for C# code bases. So what I'm going to do here, rather than going through all the rules, is trying to illustrate some properties with a single example. So why this optimistic approach is useful, and then I'll show you one of the rules and how it works. So here's our example. It's a cleanup method that takes in a socket, and then what it does is it does some shutdown routine to disable operations on that socket, and then it closes it. And the problem here is that while it seems clear that this method was intended to always close this socket, it may not do so, because this shutdown routine called on line 3 might throw an exception. And if that happens, then close will never be called, right? So if you took a more standard approach to inference, you would try to focus on what can we infer about this method that is true of the code that's there right now. And if we stuck to that approach, we would not infer any annotations for this method because we would say, hey, it might not actually close that socket, so we better not put in an annotation there because that's not going to be verified. But this is actually not the right thing to do for this code. Maybe intuitively, it seems when reading this code that there was an intent here to always close this socket. And if we don't infer an annotation there, what that leads to is confusing error messages for the developer elsewhere in the code, right? Maybe cleanup is called in 10 different places, and the checker will treat that operation as if it's not doing any cleanup at all. So you'll get 10 different error messages at all those call sites, rather than a single error here in this method where the real problem is. So the optimistic approach aims to mirror the developer's intent. So here we infer an owning annotation on this socket parameter, and that's going to lead to an error, but it'll lead to an error in this method, which typically is the right place to fix this. So let me show you the rule that infers this owning annotation quickly. So, and you can see all the rules in the paper. It's of a data log style, like I mentioned. So here we see that the type of this parameter is T, it's a socket, and we have built-in models of the standard libraries that says there's an obligation on sockets, you have to close them. And here's the interesting part, we check whether there exists a call to close in this method, right? So we don't check that it happens on all paths. We say if there exists a call to close, we're going to infer this annotation because in our experience, it's very rare for a method to conditionally close a socket and then sometimes leave the responsibility for somebody else. So as I mentioned, there's many more rules in the paper. Please go see the paper for more details. Okay, let me briefly cover some results from our empirical evaluation. So the first experiment that we did was we had done handwritten specifications beforehand for several benchmarks. So the top 5 benchmarks here are C# code bases, and the bottom 3 are Java code bases. So we wanted to run our inference and see, can it infer the annotations that we wrote by hand? And we had pretty good results, I think. 82% recovery rate in open source C# projects. That's these two. 74% in open source Java projects. And actually for the proprietary C# microservices that we looked at, we were able to uncover 100% of the handwritten annotations. We don't have a proved explanation for this. We suspect that that code was under more rigorous code review and maybe structured more in a way that's more amenable to this kind of checking. In terms of why we missed annotations, they were reasons that were, in my opinion, kind of weird code. Like there were classes where there were multiple different methods that might release the resources that were public, and we picked the wrong one. So that we missed the right annotation there. There were places with an abstract class that had fields, and subclasses were managing the closing of those fields. We don't have techniques for supporting that right now. So that explains roughly the reasons we missed annotations. The next thing we did, as I mentioned before, was let's see what happens when we take an unannotated code base, run inference, and then run the checker on the result. So first we compared the number of warnings that we saw. NS is no specifications, so just running the checker, and this is with inferred specifications. And you'll notice that the number of warnings actually goes up in many cases. And I want to argue this is actually a good thing. This is because our inference is discovering new obligations that actually need to be checked. And so it's, again, giving you errors in the right place. So for example, here, with my original example, it will give you an error in the right place due to the inference. Finally, I wanted to talk about the warnings. We triaged a sample of the warnings and tried to look at what was going on. So the true positive rate here is 28% for C#, 19% for Java. And this may not look very high, but it's very close to what we saw in previous work. And without getting into details, if you look at most tools out there, they don't do much better than this. The percentage of incorrect specifications was quite low. And finally, there were some missing specifications. I'm happy to talk more about this, but there were some common cases, non-resource types in C#, and mutable fields in Java. I don't know, we need some help. I'm happy, please come help me. We're trying to figure out how to handle these better. We don't have a good way to specify how they're doing, so we don't do well. So that's what I had today. I just wanted to show you that if you look at our manual annotations, we got lower quality warnings because we didn't have the energy to actually go through and annotate everything. But if you look at the inferred annotations, we actually got better warnings in the right places, and we're actually able to detect some new bugs in these benchmarks that even after the manual annotation before, we couldn't find them. So that's it. These are our contributions, and everything is open source. So I encourage you to go and check out the resource leak checker for either of these languages and the inference. Thank you very much.
Okay, if we have any questions, please come to the aisles quickly.
Hey, so this is super cool. And I'm wondering, what would you say is sort of the key insight in being able to go from sort of like the formal calculus to how do you relax things for inference, right? Because in some sense, you're taking a step back from sort of like the traditional inference approaches to sort of capture developer intent. What's like the big step that's maybe like a step removed from just resources?
That's a good question. I don't immediately know how I can generalize this. I mean, for our case, it was, if you look at the rules in various places where you would check that something always happened, it was taking a for all to a there exists. But I don't immediately know for other properties or other type systems how that would generalize. I'd love to brainstorm about it more.
All right, cool. Yeah, I mean, that was kind of the answer I was wondering about. So.
Okay.
Thanks.
Do we have time for another question or no?
Very quickly.
We can take it offline. Thanks.
Okay. Let's thank Manu again. Okay, and now Francesca will telling us about soundness proof for big step semantics.
Okay, so thank you for the introduction and thank you all for being here. So what I'll present today is a joint work with Riccardo Bianchini, Paola Giannini, and Elena Zucca, and it is about the study of type systems and operational semantics for resource awareness. So let me start from the very beginning. So when we reason about programs, there are typically two approaches. So the first one is the extensional approach, where we basically focus only on aspects related to the input-output behavior of programs, while the other one is the intentional approach, where instead we take into account also other aspects, such as the structure of the code or the computational complexity or resource usage. So as a super simple example, let's consider these three functions. So they are clearly all extensionally equivalent because they all compute the same function, the constantly zero function. But from an intentional perspective, they are clearly different because they use the input parameter in a different way. So traditionally, the formal techniques for programming languages are focused on extensional aspects of programs. Basically, they are interested in describing or approximating the final result of a program execution. And instead, when we talk about resource-aware semantics and type systems, we want to design type systems and operational semantics to reason about those intentional aspects, and in particular to describe or approximate resource usage during the computation. So the main idea here goes back basically to Girard linear logic, and it is based on the fact that to use a resource in a program, we basically need to use a variable. And so if we manage to control variable usage in a program, we manage to control external resources. So, but now the question is, how can we measure resource usage? And the first observation is that clearly, in different contexts, we may need different notions of resource usage. And so, to accomplish this, let's say, this goal, again, adapting ideas from Girard linear logic, we parameterize the analysis on a grade algebra, which basically measures, provides a way to measure the allowed usage of variables. And so what we do is that basically we attach grades to variables to measure the allowed usage. So as I said, this is a grade algebra, so it carries an algebraic structure, which is so it may differ depending on the kind of analysis you want to do, but basically this is some form of ordered semi-ring, so we have an order relation and addition and multiplication with their neutral elements plus some additional axioms, which may vary. And as some examples, relevant examples, we may consider the grade algebra of natural numbers for counting the usage of resources, or the grade algebra for privacy levels, which is basically a distributive lattice to control information flow, or even the grade algebra of non-negative real numbers to measure error sensitivity. And there are many others, of course. So our contributions are the following. So basically, we study resource-aware semantics and type system for a call-by-value functional language with full recursions and equirecursive types. We want to provide this analysis without affecting the syntax of the language, so that the programmer needs not to learn a new language, basically. And our formalization is based on the big step semantics, which makes the specification very clear. At least we hope it is very clear. And also this means that we need to use modern co-inductive techniques to prove type soundness. So let's have a look at the syntax of the language. It is, let's say, pretty standard. It is a call-by-value functional language, so we specify it in a fine-grained syntax, which is standard for call-by-value languages. So basically, we separate the pure code from the impure code. So we have value expressions, which are expressions which cannot raise computational effects, so it cannot diverge in this setting. And these are variables, recursive functions, pairs, and unit constants, and other. And instead, impure expressions provide standard constructs. So we have constructs for injecting values and for sequential composition. We have function application and pattern matching constructs. So coming to the semantic side, so these are the judgments. So we have two judgments, one for value expression and one for the impure expression, but they are pretty similar. And they may look a bit weird, but instead they're pretty natural, because the key idea is that the evaluation happens within an environment which maps variables to their values and to a grade which specifies the allowed usage of that variable, or if you want, how many copies of the value are stored within that variable. And the key idea is that we do not use simultaneous substitution during the evaluation, but rather we substitute variables one at a time. And here the intuition is that basically using a variable means substituting it by its value. So as we will see, when we replace a variable, we will decrease its current amount by a certain quantity to track the fact that we are using it. And last, also the evaluation arrow is labeled by a grade, which basically specified how many copies of the final value we are producing. And this is because, intuitively, resource consumption depends on how many copies of the result we are producing. So if we want to produce 10 copies of the final result, we will consume more resources than when we produce 3 copies, for instance. So let's have a look at a couple of rules just to illustrate how the semantics works. This is the most important one, which is the rule for the variable. So how can we evaluate the variable? So we just look at the environment and we replace the variable by its corresponding value. But since we want to produce R copies of that value, we have to decrease the current amount of the variable by at least the grade R. So as you can see, resource consumption is fully non-deterministic, so we only provide the lower bound to resource consumption. And the other thing which is important is that if we do not have enough resources, so we do not have enough copies of the variable, we cannot apply this rule, and so the computation is stuck due to resource consumption. This means basically if we need to produce 10 copies of a value and we only have 3 copies of that in the environment, we cannot apply this rule. Another rule which is quite interesting is the rule for the application, because it shows the interaction between recursion and resource consumption. So to evaluate a function application, we need to basically first evaluate the first argument, producing a recursive function, S copies of the recursive function. Then we evaluate the argument, producing T copies of it. And then we have to evaluate the body of the function, but in an environment which is extended by the argument of the function and the function itself, because the function is recursive, may be recursive, and so it may need to call himself during the evaluation of the body. And as you can see, so in the environment, the parameter is added exactly with the grade T, which is the number of copies we have produced of that value. But the function is added with a grade which is not exactly S, but slightly, let's say, less copies of the functions are added to the environment, because some of the copies we have produced are consumed to perform the current function call, basically. So here we are calling the function, so we are using it, and so some of that copies must be consumed here. Again, everything is fully non-deterministic, so we do not give many constraints on the resource consumption. So to see what happens on a, let's say, concrete example, even if it is quite simple, let's consider this simple function, which basically consumes the resource, the external resource y, and then recursively call the function on the input. So this clearly is expected to diverge. And to see this, we try to build an infinite derivation using our roots. So we start evaluating the body. So we first consume the variable y, and we decrease its corresponding amount in the environment. And then we evaluate the function call. And to do so, we extract all the copies of the function from the environment. We extract all the copies of the argument from the environment. And we perform the function call. So we start evaluating the body in the extended environment. And as you can see, we have to consume a certain amount of the copies of the function. So this process clearly can go on forever, but to do so, we have to, basically, at each step, this imposes an equation which must be satisfied to be able to build the infinite derivation. And this equation clearly has a solution only if the initial grades of the function and of the external resource y are intuitively infinite, because we have to use them infinitely many times. Okay, that's all I wanted to say about the semantics, but let's have a quick look at its type system. So the type system is, types are defined by, are co-inductively defined by these productions. And so we use co-inductive types to have a simple way to encode basically equirecursive types. And we have two productions, one for plain types, which are the standard ones, so arrows, the tensor, and sum, and the unit type. And we also have graded types, which basically are types decorated with a grade, which specify the allowed usage of the values of that type. Look also, it is important to notice that the, let's say, plain types, type constructor are applied to graded types because we have to specify the allowed usage also of components of more structured types. And another important thing is that the arrow types has also a third annotation which specifies the recursion grade. So in the type, we say basically how many recursive calls we expect, or in which way we expect the function is recursive. So if that grade is 0, the function will be not recursive. Otherwise, we expect this grade to be infinite because we have to over-approximate all possible recursive calls. And the structure of the typing judgment is this one. So I report it only for expression, but the one for value expression is the same. So basically, this says that the expression E produces a final result which must be used at most in R mode or with grade R, or at most R times. Think of it depending on the kind of application you are using. And to do so, uses external resources x1, xn, according to the specified grade in the context, which are R1 and Rn. OK, so just a couple of typing rules. The rule for variable, so an important thing to notice is that these typing rules are substructural because, let's say, we are inspired by Girard linear logic, so we don't have a top-down approach, but rather a bottom-up approach, if you want. And to type the variable, the context contains only the variable we are using. Sorry? OK. We have only the variable we are actually using because no other external resources are needed. And instead, for typing more complicated term, we have to combine the contexts using the algebraic operations of the grade algebra structure extended to context in the standard pointwise way. OK. Type soundness. So it is well known that in big step semantics, we cannot even express type soundness because we cannot distinguish between stack and non-terminating computation. And so to be able to prove a type soundness result, what we do is we rely on recent results, and we basically apply a canonical construction which allows us to explicitly model divergence in big step semantics, relying on generalized inference systems, and provides us a standard proof technique, a co-inductive proof technique for type soundness in this extended semantics. And in this way, we can express the type soundness property in a pretty natural way. So we say that if a configuration is well typed with grade R, then the configuration evaluates with that grade to a final result, which may be either a value with an environment or divergence. And this means that there exists a computation which is not stuck due to resource consumption. So it is a soundness may result, which is because let's say the resource consumption is fully non-deterministic, but it is standard in resource semantics. So that's all I wanted to say about this work. If you're interested in more details, let's check the paper. Concerning future work, what we are currently investigating, so the grades, as I described you, basically give an approximation of the local usage of resources in a term. But in many cases, we may need a way to specify assumption that the term need on how the environment uses the same resources. And we are investigating the possibility of using grades to specify such assumptions. And this would hopefully lead us to a common generalization with uniqueness types, which are quite used in the literature. So that's all I wanted to say. Thank you for your attention.
Okay. Okay, if we have any questions, please come to the mic in the aisle. Yes? Here on the two sides. Okay. Yep, go ahead.
Hello, thanks for the nice talk. You presented a call by value calculus, and you know the thing is that with something like call by push value, the idea is that you could get semantic for free, basically for both call by value and call by name, and also it has a nice presentation as a linear polarized calculus. So I wonder if you look into extending this to call by push value, and if you foresee any difficulties.
Oh, so actually, we haven't looked at the call by push value strategy yet, at least, but for sure it is an interesting perspective. I'm not really an expert on that field, but it may be possible. So the honest answer is I don't know, but I'm really interested in discussing it if you want.
Okay, thanks.
Thank you.
Okay, and one more question.
Yes, thank you for the talk. I'm over here on the other side.
Sorry.
That's okay. So your cost measure here, or resource consumption measure, is uses of a variable. How would this change? Would it be feasible if I were interested also, or alternatively, in uses of operators? Like I want to know how many floating point additions my code did, or whatever.
So you mean you want to count basically the...
I want to count operations rather than variable uses.
Yeah, it's more like I don't know. It's more like on the effect side, I guess. So these are more on the co-effect side. At least I don't know. I'm guessing, but to me, so my feeling is that it's more. It's something more like a dual setting, counting the number of operations. But I don't know. It's because I don't know. Where to attach the measure, basically, in the typing context in that way. I imagine this more like an annotation of the old judgments, which says how many.
Okay.
Okay. Well,
thanks.
Let's thank Francesco. And for the last talk of the session, Andrea will tell us about Verus.
Hi, folks. Thanks for the intro. I'm Andrea, and today I'm going to talk about Verus and how it verifies Rust programs using linear ghost types. So first of all, let me clarify what I mean by linear types here. And we're talking about linear types as in Rust. So the Rust linear or ownership-based type system and its borrowing extensions. So as you may know, in Rust, if you have a value like v of type vector here, you're not allowed to duplicate it. If you attempt to do so, the compiler will catch it and reject this code. it may be difficult to write code with just these techniques. So what you can do instead is grab immutable references, as many as you want, to a certain value. Or alternatively, you can grab a unique or exclusive mutable reference to a certain value, like in this parameter here to function g. But if you were to try and pass v as both a mutable and immutable reference, again, we will get an error because we will be aliasing this mutable reference with an immutable one. Okay, now that I've clarified this, Rust, as we've seen, has this sophisticated type system that uses ownership and borrowing. And this enables a type-safe, low-level systems code without the need for garbage collection. We believe this is one of the reasons Rust has gained so much popularity recently. However, even type-safe code has bugs, obviously. And sometimes in Rust, people or programmers need to use unsafe to express certain kinds of programs that don't fit in the linear or ownership discipline of the language. So deductive verification is something that can prove deeper properties about code, as you can imagine. And we'll see how that includes for code that would have otherwise have required the unsafe keyboard in Rust that lets us break out of the ownership discipline. So I'll talk about Verus, our new SMT-based tool for verifying Rust code. And SMT here, we're going to use the solver as a semi-automated theorem prover, like other tools of the same family do. But we'll see how SMT verification can also help us overcome the limitation of the Rust type system, and how ownership and borrowing can make SMT verification easier itself. And does this in two ways. One is simplifying memory reasoning, and the other is using separation logic style techniques. And we're going to go into more detail about those in the talk. We'll do this primarily by example. We'll see how to read and write from pointers in Verus, and we'll use that knowledge to build up a doubly linked list, which you may know is difficult to write in regular Rust. So first of all, though, I want to show you what it looks like to write some Verus. Imagine you're writing an implementation of Fibonacci. You want to verify it correct. You're going to write a specification. So you're going to add a postcondition, and you're going to add a functional representation of what the program is supposed to do. And it's what this spec function Fibo is doing. If we run Verus on this program, we'll get this error. Verus cannot prove the postcondition. And this doesn't necessarily mean that the postcondition is false. It's that we haven't given the semi-automatic tool enough information to prove it. So how do we address this? We're going to need a loop invariant, as in similar tools that you may have seen. And also, we're going to have to address the potential overflow in that addition. And to address that, I'm going to have to add an additional precondition that the result fits in a U64. And I'm going to need a separate proof that I describe here as a proof function. The details of this are not super important. What I want to highlight here is that in this language, we have three different modes. We have exec mode code on the left, the implementation we were trying to write. Proof mode code, which lets us express things like lemma calls and the proof bodies. And spec mode code, which is how we describe functionally what the program is supposed to do. So in Verus, exec mode code can contain proof and spec mode code. And proof mode code can contain spec mode code. So this makes it possible to write programs and proofs in a single language. This is similar to other tools like Daphne F star, where a single language provides facilities for both. And the three modes that we've seen so far, exec mode, proof mode, and spec mode code, are important for linear ghost types. Let me show you how. Exec mode code is the code we want to verify. It's checked for ownership and borrowing. It's regular Rust code that you want to write, and it gets compiled to the final binary. Proof mode code is for lemmas and assertions, and it's still checked for ownership and borrowing, like regular Rust, but it's erased. We don't want it to appear in the binary. And finally, spec mode code, in which we write our functional specification of the program, is a functional language in which copying is always allowed. So we break out of the ownership and borrowing discipline because it's a functional language, and this is an erased mode as well. We don't want it to appear in the binary. So we're going to focus on the fact that proof mode code is checked for ownership and borrowing and how that enables linear ghost types. So Verus, again, uses SMT verification to overcome Rust type system limitations, again, and we'll see how we linear ghost types, and uses ownership and borrowing to make SMT verification easier. And we're going to focus on the fact that it does this by using separation logic style techniques that leverage these linear ghost types. Again, we're going to go through a couple of examples. First, though, let me show you how you read and write from a pointer in regular Rust. We can have a function that allocates a U64 size chunk of memory and gets a pointer. Then we write into that memory. We read from that memory. We deallocate the memory. And then we attempt to read from that memory again. You might notice a problem here. In Rust, we need to mark this block unsafe because we are doing operations for which the compiler is not able to prove safety. And in fact, this is demonstrated by the fact that we are doing a read after free here, so undefined behavior. What can we do in Varus instead? First of all, we don't need the unsafe block. Then we use the PPTR API that we have in Varus, which replaces the raw pointer API, and returns a pointer, which is mainly the actual runtime pointer that can be copied arbitrarily, and a linear ghost permission of type points to here, similarly to here the parallel is to a separation logic points to assertion, if you're familiar. And here in Varus, linear ghost permissions are syntactically marked with this struct marker. So the first important property of what we get back from empty is that the pointer and the permission are associated at the SMT level. So we have an ID associated with both, and we'll see how that helps make sure that we keep them aligned. The other thing we can do is track the value in the memory through the permission. So the permission has a ghost value that says currently the memory is uninitialized. And I should mention the idea I was talking about before is also ghost. It's not something that will appear in the program. So first, let's write into the pointer. We use the put function that critically takes a mutable reference to our linear ghost permission and uses the SMT solver to check that the permission and the pointer are one associated with the other. We are not using a permission for some different pointer. We are using the one that was allocated for this pointer. And this is how we use SMT solving and ownership-based reasoning at the same time to achieve these goals. So once we've done that, we can determine that the value that we have in the memory location is 5. We might read from it, and this time we only need to have a shared or immutable borrow to the permission to be able to do so, and that allows us to take potentially multiple references to the memory location, as long as those are exclusive with immutable ones, or with mutable ones, sorry. And then we can assert that the value comes back that we expect. We can deallocate, as we were doing before, but critically here, we have to relinquish our permission. The API for deallocating requires us to relinquish the permission so that if somebody were to try and read from the memory location using that permission again, we would catch that. And in fact, in particular, it's the Rust borrow checker that catches this mistake. We don't have to go to the SMT solver for this. We get this error very quickly thanks to the borrow checker. And here again, this is enabled by the mode system that I've been talking about. So most of the code is exact mode code, but what I want to point out is that the proof mode tracked annotations is where this tracking of linear ghost permission happens. So when it's initialized, when it's passed by mutable reference, or when it's passed by immutable reference, or relinquished at the end. Okay, so I've shown you a fairly kind of trivial example. People don't really read and write from a single pointer. There's no really real point, but that's to build up to a little bit of a more complex example that hopefully is more interesting. And that's doubly linked lists. You may know that in Rust, it's difficult to write one. And the reason for that is that the cyclical structure of the pointer, of the pointers that you need for a doubly linked list, that doesn't work well with the ownership structure in Rust. So what can we do instead in Varus? Well, we're going to add a linear ghost field to the doubly linked list data structure. And this is, again, a ghost field, but it will be treated linearly. And that will store a flattened representation of all the permissions we need for all the fields, for all the elements in the doubly linked list. How do we access the list? Let's say we want to access the list from the head. We're going to read the head and access the permission that we need, that gives us the ability to read from it. And this operation would repeat to access the further elements in the list. Okay, so we have seen how linear ghost types lets us represent memory permissions and express programs like doubly linked lists that would have required unsafe in regular Rust. Linear ghost permissions also, or linear ghost types, also allow more interesting programs, which I don't really have the time to go through in the talk. They can reason about interior mutability, for example, and this is a situation in Rust where the contents of a certain data type X can be modified when we only have a shared reference to it. And this is complicated by the fact that in our VC generation for efficiency, immutable reference is always treated as immutable. Linear ghost types, with the techniques that we've seen so far, also helps us deal with that. And there's other techniques that we can employ to implement things like memoization behind an immutable reference. And more details about this are in the paper. Additionally, linear ghost types also enable more sophisticated techniques for reasoning about shared memory concurrency. The details are way too much to go into the talk, but the high-level idea is that this lets us write protocols that allow different parties, different threads to exchange these permissions that we've seen so far, and that allows us to implement things like concurrent FIFO queues, thread-safe reader-writer locks, and things like this, and bigger, more complex concurrent systems. The techniques that this builds on are also reported as part of previous work on linear Daphne in this OSDI paper that I'm mentioning. There's also going to be a talk on Friday by Travis Hans on the separation logic underpinnings of some of these techniques. So I presented Verse and how it verifies Rust programs using linear ghost types. We've seen how SMT verification can overcome the limitations of the Rust type system. And now ownership and borrowing can make SMT verification easier by using separation logic style techniques with linear ghost types. And also, and I didn't have the time to go into detail in the talk, by simplifying memory reasoning. In addition to this, Verus focuses on efficient, lightweight verification condition encoding. We want to make sure that Verus is able to scale to extremely large programs or to very large programs. And for this, we need to make sure that the tool is fast, responds fast, and lightweight encoding is critical for that, alongside the simplified memory reasoning afforded to us by the type system. And finally, in the paper, you'll find the formalization that talks about the mode system, how it interacts with lifetimes and with first-class functions, and how permissions mediate access to the heap. Finally, Verus is open source. You can find it on GitHub. It's actively developed. The author list you saw at the beginning is only a subset of the people that are working on it right now. We have a getting started guide, so if you want to try it out, I encourage you to go on that website and you'll find the guide. And with that, that's all I have. Thanks for listening.
Thanks for a great talk. Did you encounter any uses of unsafe code that you couldn't translate into the sort of track permission system where maybe the ball checker still is too restrictive sometimes to express that?
That's an excellent question. I don't think we have found situations in which there were things that you could express with unsafe that were related to the ownership structure. What we cannot represent, because we focus on safe Rust, is interactions with things like hardware, like memory mapped registers. Those are things that we need to axiomatize and then access through a safe API. But I don't think we've encountered situations in which something you could write in unsafe, but you couldn't then translate to our safe API, although the techniques for shared memory concurrency require sequential consistency. So if you're doing more fancy log-free things, those might be harder to express.
Hi, I'm Al Ahmed, Northeastern. This is really nice work. I was wondering if I sort of have a two-part question. I'm wondering if you're familiar with the L3 work that we had with Greg Morissette and Matthew Fluid back in like 2005, 2007, we had capability types in that work where, the capability essentially allows you to think about, strong updates in a safe manner. And your linear ghost types seem very much like the capability types. And we even showed the connection to separation logic. But what we could not do there, because at the time borrowing was not a thing, is handle immutable borrows. So I'm wondering if you have a different predicate from your linear ghost type, which is somehow maybe fractional capability or something that you use for immutable borrows, because
I'm not sure I'm going to be able to answer your question exactly because I'm not that familiar with that work you mentioned.
L3, yeah.
But the relationship with capability is definitely apt. And what I can say is that our understanding so far is that the linear type system in Rust with the borrowing is, if you wish, a different interface to separation logic. So, so instead of needing fractional permissions, we rely on the substructural nature of the Rust type system and how multiple immutable references are kept exclusive from mutable references. And so we kind of use the logic that Rust provides.
But don't you need to reason about the many immutable references? Because those are not linear, right? You can have many immutable references.
You can totally have...
Immutable is separate from mutable, but...
Absolutely, but the immutable reference in the absence of interior mutability do not allow mutation, so we can just treat as functional values. That's the trick. We can just treat them as functional values. And in fact, I guess broadly, safe Rust is kind of a functional programming language in disguise.
Absolutely.
You can treat it.
Yeah.
Thanks for the question.
shows that too. Thanks.
Thanks.
I have got many questions, but I will ask 3 if I'm allowed.
Okay.
So
Ready.
Okay, I'll only ask one then. Do you use, do you prove functional properties or just safety of unsafe code? And one little one attached, do you infer the specifications or do you write them by hand?
Great questions. So Varus is designed to prove full functional correctness of large system software. So I went into the details of how the techniques enable having type-safe access to memory, for example, but the overall goal of the project is to verify large system software and do full functional verification, so verify the correspondence of a large program to a small specification. And to answer the second part of your question, that small specification is something that we expect the user to write by hand. And so we don't infer them. We say if you're verifying a key value store, you're going to have to write a small specification of what a key value store is supposed to do. And then our goal is to provide a proof that the implementation matches that specification. We ask the user to write a specification, the semantics of the doubly linked list. How you'd be able to infer a specification is an interesting question, but not our focus so far. Thank you.
Okay, let's thank Andre again. And let's enjoy lunch.
it's getting stressful. Hello, hello, hello. Can you hear me?
Okay, welcome to the second session on type systems. Glad to be back. And so for our first talk, Chen will be telling us about greedy implicit bounded quantification.
Thank you. Good afternoon, everyone. My name is Chen Cui. I'm currently a PhD student from the University of Hong Kong. Today, I'm delighted to share our work, greedy implicit bounded quantification. This is a joint work with Shengyi Jiang and my supervisor, Bruno Oliveira. Mainstream OOP languages such as Java, Scala, C#, or TypeScript have polymorphic type systems with subtyping and bounded quantification. Take this Java code as an example. It defines a generic method main. It takes 2 arguments of the type S and returns a value of the same type S. The S extends comparable here defines a type variable S and gives a bound comparable to it. We may write the type of main in a formal way like this. Bounded quantification is used to give subtyping bounds to type variables, so the quantifier is only bounded to range over the subtypes of comparable. This is a widely used feature in OOP languages. However, there is little work on type inference algorithms supporting it. Type inference enables removing redundant type annotations from programs and can reduce the burden of programmers. When we write the code, the compiler fills the missing types for us and keeps our code very clean and concise and more readable. Take this code also in Java as an example. It processes a list of strings representing numbers and converts the strings into numbers and filters the even numbers. In this code, we don't need to provide the type annotations when using the function, map, filter, etc. One thing to note here is that the list functions are polymorphic. Here is the type of map function in Java. It introduces a type of parameter R, takes a function from T to R, and returns a stream of type R. By type inference, Java will automatically instantiate R with integer, since the return type of value of function is integer. And it can also infer that S has type string, since numbers is a list of strings. The algorithm will propagate the known type information and conclude that S has type string. Type inference is very important in a modern programming language, but surprisingly, there is little work devoted to practical OOP type inference. Currently, most production compilers like Java, C# use algorithms loosely based on local type inference, and their algorithms are not formally studied, and some problems regarding unsoundness and incompleteness have been found. Scala 2 is based on an improved form of local type inference, namely colored local type inference. Though local type inference is the most widely used techniques for programming languages with bounded quantification, it suffers from some limitations. Next, we will identify these limitations in Scala 2 and compare it with our calculus F sub b. It's worth noting that the implementation of Scala 2 contains some improvements compared to the algorithms formalized with local type inference. It enables more programs to type check. Scala 3 has more improvements, but it has not been formally studied. Scala 2 type inference remains more faithful to the original work of local type inference, so we compare our calculus with Scala 2. The first limitation is no support for interdependent bounds. Local type inference forbids the inference of of type arguments with interdependent bounds because they couldn't find a complete algorithm that deals with such kinds of bounds. Scala 2 provides some basic support for interdependent bounds, but it fails frequently. If we define two identity functions, ID phone is from type B to type A to A, but the bound of B depends on A. Another one is from int to int. In Scala 2, we cannot apply ID phone to ID int 1. Because Scala 2 wrongly instantiates A with bottom instead of integer. B is instantiated to int. It doesn't conform to the bound restriction that B is the subtype of A to A, so it's rejected. In our calculus, interdependent bounds are supported. It type checks the equivalent program below. The second limitation is hard to synthesize arguments. We may define a map function in Scala like this. It has two type arguments, and it takes a function from type A to type B, and a list of A, and returns a list of B. However, when it's applied to an anonymous function, it fails to type check. That is because local type inference requires the types of function arguments to be synthesized first, but we can never synthesize the type of this anonymous function. A workaround is providing type annotations to the function argument, like we can annotate x with int here. Our calculus can type check the program without additional annotations. When the type variable to instantiate appears invariantly in the output type, but the constraints are not enough to decide a unique instantiation, local type inference fails to provide any instantiations. In such cases, Scala 2 still infers a type, but the type can be meaningless. For example, when applying the function second to 1, the constraints are not enough to decide a unique instantiation of A. Scala 2 still infers the type of ID as bottom to bottom, but it's meaningless. ID cannot be applied further. While in our calculus, unification is deferred, and the second one can be applied further. Higher rank type inference is an important feature. It's very useful when we would like to take a polymorphic function as the argument of another function. However, the subtyping relation employed in local type inference is restrictive and prohibits type checking in many programs with high rank types. In this program, K has type int to int, and G is a function that accepts argument with this type. We would expect that the type inference algorithm can implicitly instantiate A with int so that we can apply G to K. However, this fails to type check in Scala 3 due to its lack of implicit polymorphism. Our calculus has better support for high-rank polymorphism. It can implicitly instantiate the type variable A here with int, and the program succeeds to type check. Next, we will start to introduce our calculus. Our calculus extends the earlier work, elementary type inference with bounded quantification. It's a variant of kernel F-sub. Different from local type inference, it employs global type inference, so it's capable of solving long-distance constraints. It follows the similar philosophy as elementary type inference. we only infer easy instantiations and use explicit annotations for hard instantiations. So our system has the implicit instantiation for monotypes. Like the example we showed before, we can implicitly instantiate A with int. For hard instantiations, like polytypes, we use explicit type application to allow users to provide the instantiations. This is the syntax of our calculus. Compared with elementary type inference, the change is that the universal types and the type abstractions now incorporate a bound B to support bounded quantification. These are the declarative subtyping rules of our system. It's based on the previous higher rank polymorphic systems. The difference between our system and the elementary type inference is that we have the variable transitivity rule, and all the for alls now incorporate a bound. These two differences cause problems in certain important properties and motivate us to rethink the question, what kind of type variables should be considered as monotypes? With bounded quantification, if we treat all type variables as monotypes, transitivity breaks due to the variable transitivity rule. Type variables with for alls in their bounds, like the type variable B here, can bridge two for alls types with different bounds, which is not accepted in our subtyping. So in F sub B, only type variables with bound top or monotype bounds are regarded as monotypes. In existing predictive higher rank polymorphism approaches, finding implicit instantiations is greedy. All such approaches rely on the property that monotype subtyping implies the equality of monotypes. This ensures that if the first instantiation works, then it must also work for subsequent instantiations. However, without care, the property easily breaks in the presence of more expressive subtyping relations, like bounded quantification. So in our paper, we present two variants of F sub B. In the first variant, only type variables with bound top are regarded as monotypes. With this monotype definition, the property holds, and we get a sound, complete, and decidable algorithm. In the second variant, type variables with monotype bounds are also regarded as monotypes. It breaks the property. For example, in this context, type variable A is a subtype of int, but A is not int. So this variant is sound, but incomplete. The benefit is that it type checks more programs. Finally, let me conclude the contributions of our work. Firstly, we proposed a declarative bidirectional type system with predictive implicit bounded quantification and predictive explicit type applications. We have good properties like checking subsumption, and we have type safety and completeness with respect to kernel F sub. And for variant 1, we have a sound, complete, and decidable algorithm. Our algorithm employs a work list formulation inspired by previous work. For the second variant, with monotype subtyping, we have a sound algorithm. All the theorems have been mechanically formalized in the Abela theorem prover with about 25,000 lines of code. And we also have a simple Haskell implementation. if you are interested, you can find our implementation proofs and the extended version of the paper by scanning the QR code. Thank you.
Okay, thank you. If you have questions, please come to the aisles. We have microphones up front here. I'll start us off. So you were comparing a lot of your examples to Scala 2 and Scala 3. Yeah. Do you have plans for an implementation for Scala based on your calculus here?
Sorry, I didn't.
Are you going to add this to Scala now?
No. They use different algorithms, so it's hard to adapt our algorithm to Scala. We aim at a higher rank polymorphism system, so that's our target.
Okay.
Hi. Have you considered extending your approach to support, say, dependent types? Is that feasible?
We haven't considered it yet, but if you have some good thoughts about that, we can have a catch up later.
Not really.
Hey, Magnus here. Do you know anything about performance of this system? Do you have reason to believe it would perform well or perhaps not?
I think our algorithms perform well because we don't have backtracking, and we already have a confluence proved.
With respect to target type inference, as it happened with the Java lambdas, does your system compare in some specific way?
I didn't get clear.
In Java, when you have a lambda, the type of the lambda is inferred from the context. It's called target type. So does your system handle something like that, or do you think there is any problem to extend it in that way?
We do support to have some type constraints in the context in the algorithm version of our system. Yeah, so our system would support that, I think.
Okay. Okay, let's thank Chen again. Okay. And now Wenhao will tell us about whether or not we can reduce structural subtyping to parametric polymorphism.
So hi, I'm Wenhao. I'm a PhD student. I'm a PhD student from the University of Edinburgh, and I'm going to talk about something very simple, something about how to encode subtyping as polymorphism. And this is joint work with my collaborators. Some of them are sitting here. Yeah, so we consider structural subtyping, which means the subtyping relation is defined inductively on the structures of types. And one most common usage of structural subtyping is to allow the extension and restriction of records and variants. So this can also be done by using role and presence polymorphism. So since these two features were proposed, there have been a lot of discussions on the similarity and differences between them. For example, in one of the initial papers on role polymorphism, Michael Wand compared his system with another system using subtyping. And he gave some examples that are well-tapped in one system, but are ill-tapped in the other one, and vice versa. So the expressive power of these two specific systems cannot be compared. And later, François Pottier wrote in his thesis that these two features actually complement one another because they are useful in different situations, and it would be great if you have them together. And Andrew Schultzberg, sitting there, commented in Lambda the Ultimate that subtyping is in fact a poor man's through polymorphism. And I agree with him because most basic usage of subtyping can also be done by row polymorphism, and the latter works much better with type inference. And there are still more and more discussion going on if you search it using Google, but there still lacks a formal study on the expressive power of these two features. So we want to fill this gap partly because we are more interested in how to encode subtyping as polymorphism. Okay, so let's start with the simply typed lambda calculus. It has term variables, has lambda abstraction, lambda application, and we can extend it with variant. We write the square bracket for variant. So here we have a variant age. It has the label age with the integer 42, and there is only one label in its variant type. And we have a function getAge. It takes a variant that can either be the label age or the label year, and it calculates an integer from them. So there is an obvious type mismatch between the function and the variant. What we can do is we can extend the calculus further with subtyping. We call it simple variant subtyping. It allows us to extend the labels in a variant. So we have this triangle for the explicit upcast. We can upcast the variant age to a bigger variant type with two labels and apply the function to it. Yes, so this is simple subtyping because we only consider the subtyping of variants. And then later we will also consider strictly covariant subtyping, which means we can propagate the subtyping relation through strictly covariant positions, like the result type of a function. And we will also consider false subtyping, which means we can also propagate the relation through contravariant positions, like the parameter type of a function. So it is well known in the literature that we can simulate this kind of upcast using some destruction and reconstruction. So here we can simulate the upcast of the age by using the Kate split to split it, to destruct it, and construct a new variant with a bigger type with two labels. And this not only applies to simple subtyping, but also applies to false subtyping. It is known as I think the coercion semantics in the literature. Yes. And another direction of extending the calculus lambda variant is to add row polymorphism, which also somehow allows us to extend the variant type. So here we have the variable row, which abstracts over other labels. And we can instantiate the variable row to the label year to add the label year to the variant type of this variant, so we can simulate the upcast. This works well. This gives us a local type-only encoding of the upcast. So the idea is we use, instead of using the variant destruction and reconstruction, we use the type application and the type abstraction. So we first adding the label year to it and abstract it to make it again a polymorphic type. This is important because what we want is a uniform translation. So we need to make sure that every variant type is translated to a polymorphic variant type, including the function parameter of the getAge function. So we need higher rank polymorphism. And we call it a type-only translation because it only introduces some new type abstraction and type application. In other words, it is actually identity after type erasure. And we believe this is very important if we want to compare the expressive power of two type features. Yes, so this is the story for variant, and we have a very similar story for record because they are kind of dual to each other. So here we extend the calculus with record, we write the angle bracket, and we have a record Alice with two labels, name and age, and we have a function getName. It takes a record with only one label and uses the projection to get the name from it. And again, there is a type mismatch, so we need to add subtyping. The record subtyping allows us to restrict the labels in a record to to a smaller one, so we can upcast Alice to the record type with only one label. Yes, and again, we can simulate it by using some record destruction and reconstruction. So we use projection to get the label name from Alice and construct a new record with only one label to simulate the upcast. This is well known. And we can also extend the calculus with presence polymorphism. So here we have two presence variables, theta1 and theta2. They abstract over the presence of the label name and age. Then to remove the label age from the record, we can just instantiate the presence variable theta2 to absent. So this gives us a type-only translation of the record, of the simple record subtyping to presence polymorphism. And it's very similar to the previous type-only translation. We first use type application to instantiate the presence variables in Alice prime, and then you abstract over it to make sure that it is still a presence polymorphic record type. And we also need a polymorphic type for the function parameter, so we need higher rank polymorphism. Yes, so far so good. We have used the row polymorphism to simulate variant subtyping because they both allow some form of extension. And we have used presence polymorphism to simulate record subtyping because they both allow some form of restriction. The natural question is, can we swap them? Can we use row polymorphism to simulate record subtyping? At first glance, it seems possible because for record subtyping, what we want is we want to remove some labels from record on covariant positions. This is actually equivalent to adding more labels to records on contravariant positions. So consider the previous example. We can translate the record Alice to itself, translate the function to a row polymorphic function. So it is row polymorphic, and the parameter has a row variable, which can be instantiated to other labels, so we can extend it. And the function application and upcast is translated by instantiating the row variable of the function to the missing label age with type int. So we can resolve the type mismatch. But unluckily, we want a compositional translation, which is the macro expansion. So, but this translation actually breaks the compositionality because when we are translating the function application, we only know the translation result of the function and the translation result of the argument. So we can only look at some local information. But to know that there is a missing label age with type int, we need to globally look at the whole structure of the original term. And yeah, this breaks the compositionality. And moreover, we formally proved that there is actually no type-only translation from simple record subtyping to row polymorphism. And similarly, from simple variant subtyping to presence polymorphism. And the idea of the idea of the proof of this negative result is to find some good counterexamples and try to define a very general translation scheme for them. And then you can try to show some contradiction. For example, it is contradiction to the compositionality requirement, or it is contradictory to the type-only property or something else. Yeah, but we still have one hope to make the translation compositional. The problem is we don't know that there is a missing label age with type int, but in practical languages, we usually have type inference for polymorphic types, and the type inference knows it. Yeah, so we can just define the translation as the erasure function. We erase all type annotations and erase the explicit upcast. And the type inference automatically infers a polymorphic type for the function. It is a row polymorphic type as we have seen before. And when you are doing the function application, it automatically instantiates the row variable to the missing label age with type int. Yeah, so it works quite well. It works not only for simple subtyping, but also for full subtyping. So this is the calculus with records and the for subtyping. We write the for as the superscript. And to make sure that the type inference is extendable, we restrict the target language to rank 1 polymorphism. So we write the number 1 besides the variable rule. And as a result, we have a similar restriction in the source language. We only have rank 2 records, so we write the number 2 along the record. And the way we define rank n records is very similar to how we define rank n polymorphism. And please check the paper for the details. And we have a similar result for rank n presence, for rank 1 presence polymorphism, and a similar result for variance. So here is the for picture in our paper. I have only covered part of them. So in the paper, we also have some translation of the strictly covariant subtyping and for subtyping in the setting of explicit calculus. And we found it very surprising that the symmetry is broken when you are considering more involved subtyping. Yes, and in the paper, we have proved all the errors in this figure. We have formal definitions and some meta-theories, like the translation preserves types, the translation preserves the operational semantics, and and some proofs of the negative results. Yes. And I think I'll finish. And there is some takeaway. So first, in explicit calculi, we found that even if you only want to encode simple subtyping, you already need some higher rank polymorphism. And for simple subtyping, as we have seen, there is a very good symmetry between the results of records and variants. But the symmetry is broken if you consider some more complicated forms of subtyping. And we have proved that there is no type-only encoding of for subtyping. But for languages like OCaml, it has type inference, so it can actually encode a restricted form of for subtyping. Thank you.
Okay, we have plenty of time for questions. Please come to the aisles if you have a question.
So, I have some principal question, because regarding your first takeaway, you say actually subtyping, even simple subtyping needs higher rank polymorphism, so which sounds like a little bit hard thing, right? But subtyping is everybody knows, every Java programmer knows. So does that mean actually subtyping is the right way of doing things in practice?
Well, I don't know. Personally, I don't really like subtyping, and so that's why I want to encode subtyping using something else. But it is sad to say that even if we only want to encode simple subtyping, we need some very complicated mechanism of polymorphism. But I think the point is, in practice, most simple usage of subtyping actually it's quite shallow. It doesn't have a very complicated structure. So it can be done by some lower rank polymorphism.
Okay, thank you.
Yeah, so thank you for the talk. You said about the translation for records that it was not compositional, right?
Yes.
So does that still hold if you do the translation on typing derivations? It seems the information is there in that case.
Yeah. That's exactly the way that we do translation. The translation is defined on the typing. No, it is only defined on the on the bottom typing judgment of. How to say? Yes, it only defined on the bottom typing judgment of the term. But I don't think if you have the for typing derivation tree, you can have a compositional translation, because it seems not so clear to how to get the missing label from the derivation tree. Maybe you need some very complicated algorithm to retrieve this information.
Yeah, okay, I'd have to look at it in detail. Thank you.
Yes, okay, thank you.
Your talk offers an interesting point of view of subtyping, in the sense that it focuses a lot of a half of subtyping. And in many languages, we think about subtyping most as the behavior may change between two subtypes more than just, yes, you can have more methods. Is there a terminology that you have encountered while doing your research to distinguish those two kinds of subtyping?
Yeah, well, I'm not sure, but I guess what you mean is nominal subtyping, which is like the classes structure. Did you mean that? Yeah, so here we consider the structural subtyping, which is the most common example is the record invariant. You are just define the subtyping relation on structures. Yeah, but I'm not sure. I don't think nominal subtyping can be encoded only using something like polymorphism. You may want to have some constraints like qualifier types or the type classes in Haskell to encode that.
Okay. Okay. Well, let's thank Wenhao. Okay. Now Edward will tell us about reference immutability.
Hi, my name is Edward. Oh, sorry. My name is Edward, and I'm going to talk about some joint work with my PhD advisor, Andre Lotek, on reference immutability, hopefully simple, and system F sub. I apologize a little bit because I caught a bit of a cold this morning, so if I cough, sorry about that. So why am I here today? So pure functional programs are great because they're easy to reference, they're easy to reason about, and maybe this is a bit of a bad place to talk about this because this is OOPSLA, but don't worry, side effects are useful. Mutation is great. If we were to build a compiler, like one phase you might write in your compiler is like something like a semantic analysis phase, where you might want to collect a set of procedures in a map so that you can work with them later. And you probably want to build this symbol table of strings to procedures imperatively, because I'm not smart enough to do this pure functionally. I don't understand monad types really well. So mutation is often handy, but some mutation is bad. For example, in code generation, I've built my symbol table, but I probably don't really want to mutate it, right? Like if I accidentally modify my symbol table during code generation, that might be bad because it might introduce behavior I didn't expect. So what can I do to prevent this from happening? Well, one trick you might do is that you might say, well, all right, I'll make the symbol table private to the analysis phase. And when I need it in code generation, I'll expose a public getter method, like def symbol table, that'll fetch the table and create an immutable copy of it. So is that immutable? Well, I said it is, but I lied. This doesn't actually work. I can actually go and mutate. I can't mutate the table, but I can mutate the things that the table points to, the procedures, by reading through the table, asking for the procedure for Mang, and then modifying a field of it. And that's kind of bad. It's like, oops. And the problem is that while we created an immutable map, we created an immutable map mapping strings to mutable procedure objects. So that's kind of bad because we can still mutate values that were transitively reachable from the map, the symbol table. So to solve this, people discussed and introduced this notion of reference immutability. And what's reference immutability? Well, the idea behind reference immutability is that A, references can be marked read-only, and read-only references can only be read from naturally, hence the name read-only. But the one nice benefit of reference immutability and the nice novel idea is that references read from read-only references are themselves read-only. This viewpoint adapts references to ensure transitive immutability. So in this previous example, if I made this reference, if I made symbol table return a reference, a mutable reference, then I can't modify locals because I read it through reference immutable reference. So as a few examples, if I had here's a few Scala-like examples, because this doesn't actually exist in Scala, but I know how to write Scala. Like, given a reference to a regular mutable object, given a regular mutable reference to an object, I can mutate it. If I had a marker or a type qualifier for reference immutable references or read-only references, well, obviously I can't modify y here because it's marked read-only, but I can't modify y.first in this next example because, well, y is a read-only reference. Therefore, when I read y.first, I get a read-only reference to another pair. So there's a long line of work here, starting from about 2005. Java RI did this for Java, and there was immutability generic Java, and Ream for Java. Colin Gordon in the back worked on a really cool system for doing reference immutability in C#. And recently, I think in eCoop, Vladimir Dort and my advisor Andre Lotak worked on a reference immutability scheme for Dot, for Scala. And there's a long line of languages with reference immutability, D, Rust, for example. But formalizations have been challenging. So today, what are we going to do? I'm going to talk about some simple operational semantics for modeling transitively immutable references. And I'll hopefully give a simple polymorphic type system with subtyping, because we love subtyping, for modeling references given an immutable type. Now, how do you protect someone from tampering with an object? Well, if you're an Asian grocery store or my hotel, you wrap them up in saran wrap. You put lots of plastic up, and you wrap your object up, and you're like, hey, no one can modify that. And this is the sort of intuition we'll take here. We're going to start with the untyped lambda calculus with records, for which, for the purposes of this talk and me, records are collections of mutable references. And we're going to add a new syntactic form, seal, which will wrap records, like saran wrap, but pass through other values. And when you get a sealed record, you can't write to it. And when you read from a sealed record, you return some sealed value, which may pass through or may remain sealed if it's a record or not. Seals capture this notion of viewpoint adaptation at runtime. The seals viewpoint adapt references at runtime to ensure transitive immutability. And so, for example, if I have a record and my reduction semantics are over a pair of term and store, well, you know, when I construct a record, I reduce the record to a record of labels mapping, something mapping labels to addresses, and where the value goes in the store. And, well, like, if it's an unsealed record, I can just modify it. So here, I construct a record with x equals 10. I put 10 in the store at location 1, and I set it to 5 so that, well, my semantics, I need to return something. So I return 10, but I update the store to have 5. So that's OK. But it also prevents bad things from happening, like seal of x at 10.x equals 5. I can't modify a sealed record. I set up my semantics so it gets stuck. And transitive sealing enforces transitive immutability. So when I have a record that's nested, and I read a reference from it, I get back a sealed reference. So when I read from y, I get back a sealed x. And that guarantees transitive safety. So with this, we can show that the only way that seals affect reduction is in getting terms stuck. If you have two equivalent terms, one with no seals and one with more seals, then you can show with the setup that they'll actually reduce to equivalent terms, or one will get stuck, and there's nothing else that can happen. And if you want some math, because I love math, you can define how you'd prove this is you would count the number of seals in a term, and you'd show that if you have two equivalent terms, or one has more seals than the other, then either they reduce the same way, or if the one with more seals will take a step and stay equivalent to the other term before it reduced, but you lose a seal. So, OK, nice lemmas. So seals don't affect reduction except in getting things stuck. Now let's talk about a type system so you can actually prove that you actually reduce. So types for sealed references, we're going to start with system f sub for polymorphism and subtyping, because I like polymorphism. And really, you want subtyping because immutable references are a supertype of mutable references. How do we model making references immutable, though, at the type level? So we have this notion of seals making term references immutable, so we'll kind of reflect that into the type system and add a type level operator read-only for turning a type into a read-only type as well, too. So there are some small technical details here which aren't really small and aren't really small or really small, depending on your perspective. It's kind of obvious that read-only string, read-only string, so on and so forth, are all really equivalent types, right? But that's kind of hard to actually prove if you want to actually discharge its equivalence, especially in a formal theorem prover. So what we end up doing is we show that every type has a normal form with at most one top-level read-only that's equivalent to it. Since we model records with intersection types, this is actually kind of messy, so the details are in the paper. So with all that said, I can flash this slide, which is like, probably you see the slide all the time at a PL conference, which is progress and preservation. You can show that terms don't get stuck, and terms, when they reduce to the same thing, reduce to the same type. So that's good. This calculus I just talked about is sound, but what does that matter? Every reasonable calculus is sound. So what does this buy you? But this is where those equivalence lemmas I talked about actually come in really handy. Using progress and preservation, we already get for free that well-typed programs with sealed references to immutable records won't get stuck. And since writing to sealed forms gets you stuck, well-typed programs won't write to sealed references or references marked immutable at the term level. But there's a little catch here, which is how about references marked immutable only at the type level? References that are typed immutable, typed read-only, but aren't sealed. Can we say anything about them? But this is where those equivalence lemmas I talked about earlier come back. We have that programs that are equivalent modulo seals reduce in the same way, or the one with more seals will get stuck. So using those equivalence lemmas, references typed read-only can be transparently sealed without affecting typing, because you can add a seal there. If it's typed read-only T, you can add a seal, it'll still be typed read-only T. And progress and preservation ensure that the modified term will reduce and not get stuck. And with those handy-dandy equivalence lemmas back here, the equivalence lemmas ensure that the modified program and the original program reduce the same way, while modulo extra seals. So you actually get a guarantee here that in this setup, programs that have references that are typed immutable but aren't sealed aren't written to. And that's kind of cool. So that's my talk. Thank you for your time. And if you have any questions, I'm happy to answer them.
Okay, we have plenty of time for questions. Please come to the aisles if you have a question.
Thank you for your very interesting presentation. I'm Clément Blodeau, PhD candidate. What you said made me think a lot about private types of OCaml. So in OCaml, you can have private types where you said that the actual implementation is something like integers, but you can, once you've you can take a private type and look at the value as if it were an integer, but you cannot rebuild the value back in if you've modified it. Does the read-only construct that you have in types correspond in some way to the private type construct?
I'm not that familiar with OCaml, but I'm happy to talk about this after and think about it, because yeah, I unfortunately haven't thought about that question too much in detail, but I'd be happy to talk about it later.
Hi, over here. So can you have mutable references that alias mutable references?
So in reference immutability, yes. This isn't, we don't talk, in this setup, we don't care about linearity or ownership.
Good, right.
Yes.
So instead of asking a question, I'm just going to address the whole room and say, can we please stop calling read-only reference immutability? Because I think it's a lie. I mean, it feels, many times you drop the word reference from reference immutability, and you talked about transitive immutability of objects, and they aren't really immutable, right?
Right.
If you have a mutable pointer to them, you can change them.
So
we used to call this a read-only reference, but I think reference immutability, that's fancy, and it sort of has a nicer property, but it doesn't, right? Because they aren't immutable.
Right, for sure.
So this is the term that needs to die.
So James has told me the same. James Noble has told me the same thing. So
good. Good for James.
I'm happy to look. I'm just using what's in the literature. I'm happy to change.
Yeah. But there's other literature that uses read-only.
Right.
So please, also cite those papers.
For sure.
Thank you.
Okay. Okay, so I had a question. Sorry. Did this language have higher order functions also?
Yes, it's system F sub.
So then how does the read-only interact with the higher order function?
So that's the entire thing with subtyping and read-only, because you will get types like read-only, 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 read-only T. So that's in the paper, but you have to actually work a little bit to show that. And it's obvious that read-only, read-only, read-only is the same as read-only, right? But you actually have to in the paper in our cock proof, which is available as an artifact accompanying the paper, we actually worked pretty hard to show that types come in a normal form with one outermost read-only. And you can always show that like a term gets typed, can be given a normal type, and then that allows us to actually do inversion limits so we can get progress and preservation.
Okay. And I couldn't help but notice the property that you proved, this equivalence lemma.
Yes.
It seemed very similar to a property that we prove in gradually typed languages.
It's also true. It's also really so. Like this is actually. I was thinking about where I got inspiration for seals, and I did my undergrad at Waterloo, where we talk about racket and racket contracts.
Yeah.
So this is like you can view like sealing and all these equivalence lemmas as like as a form of like rackets, I guess. Rackets, not imposter. It's a
chaperone?
Chaperone contracts, yeah. That's right. So they're a form of rackets chaperone contracts. And in the paper, we actually show that you can actually model reference immutability in racket with chaperone contracts as a little nice little thing in the related work.
Great. Okay. Well, if there's no more questions, let's thank Edward. We're a little ahead of schedule, so we might want to wait a couple minutes in case people are coming from the other session. Yeah.
Say again? You want to do that?
See? So next we have Andreas talk about mutually iso-recursive subtyping. Thank you.
Yeah, thank you very much. So I'm glad to be able to present a talk that is like purely about type system stuff and does not mention WebAssembly at all, except on the first slide. Just as motivation, why do I care? So we recently extended WebAssembly with support for garbage collection, and that required extending the type system with things like subtyping and type recursion. And doing that, of course, since this is like inside a VM, so this involves runtime type checks and everything, it was important that this is like performant, right? So these checks that we have to perform on types have to be fast. They also have to be structural for modularity reasons. I won't go into that here. But yeah, so that meant we had to do something. And to give you like a little example, here's like a stupid structure that is recursive and just some pseudocode language. So you can see that C is recursive with itself. And you would lower that to like a more type theoretic recursive type that looks like, oops, sorry, that looks like this. What's going on here? Yeah, like this. So I'm writing a sort of record here with curly braces, but it's really just a tuple. I erase the labels just so make it a bit more readable. So, and you see that we have this mu types here. You probably have all seen that, and the alpha refers to the type itself from the inside. So that's how we write recursive types. But what does that mean, right? And literature has two different semantics, roughly speaking, for recursive types. The first is like the equirecursive semantics, where a recursive type is always equivalent to its unrolling, like in every context. So this is just like a universal rule. And what that implies usually in the common interpretation is that this is like a co-inductive equivalence relation. So you get the largest fixed point of your equivalence rules with this rule. And also in practical languages that employ this, semantics usually keep the recursion between types implicit. So you just have equations essentially. So in a way, this is like a nice semantics because it's the most permissive you can find. It's the largest fixed point, right? So in a way, it's a canonical choice. Unfortunately, it has a number of downsides which have to do with the complexity of the meta theory, and in our case specifically, with the algorithmic complexity, because the algorithms we care about, like equivalence and subtyping and canonicalization, they are actually equivalent to similar algorithms on deterministic finite state automaton. So these are like not at all linear algorithms. So this is not really an option for something you want to do in a runtime. Believe me, we tried. It's way too expensive. So the other option then is isorecursive types. So we looked into this. So isorecursion differs in that you have explicit term level introduction and elimination forms for this mu type. So you have to use them in the right places. And there's no implicit unrolling anywhere. You only unroll through these operators. And that is nice because it actually provides an inductive semantics, at least in the common interpretation of these. For types, you just have inductive terms, and that results in the smallest fixed point. But you also have to make recursion explicit usually. So this is less permissive, but just as a side remark, there's an interesting result by Abadi and Fiori from the 90s that shows that you can actually encode every derivation in a system with echo-recursive types if you're willing to pay the price of pretty expensive conversions for every use of subsumption. But yeah, the upshot is all the algorithms we care about are like mostly linear. Not truly, but in the first approximation. So this is nice. So let's go back to our example. I showed you this. Let's change it a little bit. So this is just like a single type that's recursive, but now let's consider a variation where we have two types that are mutually recursive with each other. So we would want to lower the first type like I showed before. It would result in something like this, where inside we have D, right? And if we do the same independently with D, then we get something like this there. And the problem now is that, of course, they kind of refer to each other, so there's no closed form for either of them, right? So what do? Well, the usual thing you want to do is you break the recursion by substituting one into the other, but since they're both closed, you can't do that directly. The thing you have to do is you substitute D in there, but you also have to modify it so that its occurrence of C is replaced by the recursive variable alpha C there. This way you get a closed form, and you can put that into D, and both are in closed form. Note there that, yeah, I had to modify the type. So this is actually a different type that I've inserted there, right? So it's syntactically different, and that under the isorecursive semantics means it's actually a different type. But this looked okay so far, but let's try to scale it. So here are three mutually recursive types. We translate them like this, starting like this, and now we want to substitute backwards, essentially. So these are the three places that are forward references. So let's start with the middle one with C. We did what we did before, and now we have to go on from there and substitute B into A, and that goes like this. And then we also have to do the same thing for C, and that goes like this. And once you stare at this a bit more and think about what this does in general, you simply quickly see that this is exponential, right? And also, all the occurrences of the recursive types, they are all different, right? So it's really exponential. You can't even share the representations. So this is kind of a bummer, right? Like all the literature, like assuming, oh yeah, these isorecursive types are nice because we have this linear algorithms. But when you actually want to encode practical type definitions, you have an exponential encoding. So that kind of breaks the whole promise that they have. So what do we do? So one folklore solution is to go to higher kinds, specifically introduce tuples of types, so tuples at the type level, and then lift the mu operator to tuple kinds. And that, for example, is the thing that has been used in the Harper-Stone semantics, the type theoretic account of standard ML. And if we do that here, the way you would encode this is now as a single mu over a type tuple, right, of these three different types. And then you project from them. So the alpha is actually the triple of all, and the first, second, and third projection are the individual types, and you can define abbreviations to get like the original ones. And that is linear in size, right? So Problem solved, supposedly. That's what I thought. But we also have subtyping. And subtyping is not actually simple, this contrary to common belief. So it breaks everything. So this encoding does not actually work with subtyping. Let's see why. So let's switch to a slightly more practical example, like a tree we model as like two types. One is the forest of its children. So they are mutually recursive, and the forest is modeled as a linked list, essentially. So we would lower it as before, as this combined thing, and the two projections from that. Easy so far. But now assume we are in an object-oriented world where we have subtyping, and under object-oriented ideology, of course, I should always be able to extend any given type to a subtype, right? So I should be able to define something like this that adds a field to, say, tree, which records the size of the thing. And note that this is not actually a recursive type at all, right? So we can lower it, or should be able to lower it, encode it completely independently to something like this, which looks fine. And just for uniformity, I introduce a mu there, although it's not actually recursive, but it doesn't really harm. But, okay, that's an encoding, but we also want this to be a subtype, right? So we want this to hold. That's kind of the main thing we want to achieve here. Well, does this hold? To understand if it does or not, we have to look at the subtyping relation, how that's usually defined. So for mu types, what you usually employ is the so-called Ember rule, because it was first used in the 80s by Cadelli in his experimental Ember language. And that says that two mu types are in a subtype if their bodies are assuming the variables are, right? So that's kind of like a straightforward rule. The other thing we have to look at is how you subtype tuples of types, and you can do the straightforward thing here, which is like pointwise. So in this case, I actually require them to be the same arity. You could also add width subtyping if you wanted. But turns out that doesn't actually help because we can't, given these rules, we can't prove this, right? It's not possible, and there's no way you can tweak these rules to make that work. So there have been various generalizations of isorecursion mentioned in the literature, and the ones that might be relevant here are a paper by Ligatti and others a few years back who generalized this subtyping rule for mu's to basically unroll on both sides. This is a bit more powerful. It turns out this is actually just a special case of something that was already suggested by Zhong Shao 20 years earlier, which is just to have a general unrolling rule for mu types. So you have this unrolling equivalence everywhere. But if you stare at this, or if you try to work through some example, you immediately recognize, well, this is all nice, but now we are back in actually co-inductive territory, because this rule is like no different from the equirecursion unrolling rule, except that you keep the mu around, right? But you have all the same cost with respect to algorithms. So in a way, this is kind of useless, right? So what do we do? What these extensions have in common is that they try to enrich subtyping, right? So they try to basically infer a larger, richer relation from at the use sites by extending or generalizing the definition of subsumption and subtyping. What if we went the other way around? We look at the declaration side where we form these terms and require to declare something there. So we move from the use side to the definition side of subtypes, vaguely speaking, intuitively. What do I mean by that? Really, it turns out that you can boil this down to a very simple idea, which is we put upper bounds on mu types. So instead of having this, I propose we have this. And this is kind of a very natural thing to do if you're in a system with quantifiers and subtyping, right? So we have all these other bounded quantifiers, so we just say mu looks like the same thing. But that is just syntax. What does it mean? What does it mean? So, okay, let's first assume we have the usual subtyping rules like reflexivity and transitivity. So what's our rule for mu now? And it becomes a very simple rule. We just read it off. So the only direct supertype of mu other than the reflexive case is what we actually have written as a bound. And there's no premise here. We just vacuously assume this to hold because that's what we declared. So that is a bit strange. Obviously, that can't be all, right? So we have to check something. But the thing we check now, that moves to the formation rule now. So it's only OK to form such a type in the first place if there's something that holds. So of course, both the types in there have to be well formed, but also they have to be in a suitable subtyping relation. So the body T2 has to be a subtype of the unrolling of its bound. What's the unrolling? Simple thing. So there are two cases. Either the bound could be top, and then it's just unrolling to itself, or it's actually another mu type, and then it's the usual thing for unrolling a recursive type. So this way we check that kind of the bound, the type and its bound are actually in a suitable relation. So let's look at an example if we use this. So we could now encode this as follows, and this is almost the same as before, except that we now have this bound there with a pair of two top types. So this case is not particularly interesting. We only have top as a super type, but where it gets interesting is here, because this now has a non-trivial bound, which is tree, right? Because that's what we want to achieve. So does that work? Well, first of all, we wanted to have the subtyping relation to hold, and well, that is kind of trivial now. We can just read it off, right? We declared that it's holding. But of course, we also have to check that this is actually a well-formed type. So there are two things we have to check there. The first is that, well, the body is well-formed, and that is kind of straightforward here because it's not even recursive. So assuming forest is already well-formed, that is trivial. And the more interesting thing is we have to prove this. And if we perform like apply the unrolling function, it gives us this. So that is the body of the tree forest type with all the alphas substituted by tree forest itself. And using these abbreviations we have, we can kind of simplify to that. And then we can apply some type level beta equivalents for the projection there, which gives us this. And that is just plain record subtyping. So this works. Yeah, this is actually just, that's the basic idea. That's all I wanted to show. In the paper, of course, I go quite a bit more general. So I generalize this to a full higher order subtyping calculus. So you can have lambdas as bounds, which allows you to encode subtyping between generic types. So it's actually doing the full F omega subcalculus, basically being a minimal extension to that calculus. And I do all the soundness and decidability proofs for that based on the work by Pearson, Steffen, and Compagnoni from the 90s. Long proofs, but yeah, it all works out fine. There's also somewhat of an extension in there that you need a little bit of extra thing when you want to have recursion or subtyping within a recursion, like between different types that are defined in a recursion. You do need to do a bit more, unless you actually add F-bounded quantification. So this system does not have F-bounded quantification. I just left it out because it's mostly orthogonal. Another thing I do in the paper, I show that you can actually encode the subtyping of relation of featherweight Java into this. Featherweight Java minus F-bounded quantification, because we left that out, and prove that this is a correct embedding. And then I define a fragment of this calculus, because like the full higher order calculus is still pretty expensive. When you check subtyping, you have to do all sorts of substitutions, deep substitutions deeply into terms, right, into type terms. And that's not something you want to do in an engine, for example. So you want something similar. So I define a syntactic fragment of the type language, which ensures that all substitutions that you have to perform for subtype checks are actually shallow. So you never have to go inside a mu, actually. And when you stare at that, what you realize is we have basically reconstructed what nominal subclassing does, except that we still have a structural type language here. So when you have two mu types that are structurally the same, they're still equivalent, despite, but at the same time, if you were to canonicalize all the types in your program, like make all the equivalent types the same, after that you can treat it as if it was just nominal subtyping. So it's behaving like nominal subtyping up to this canonicalization step you do before. And the upshot of that is that you can use all the nice efficient implementation techniques for nominal type checking, including nominal runtime type checks, right? The implementation techniques that you have in a language like Java, without losing structural typing. Yeah, and that's all I have. Thank you very much.
Okay, thank you, Andreas. If we have any questions. Where is Ishan for the next talk? Yeah. No? Oh. So is this being added to WebAssembly?
Yeah, so this is basically the type theoretic foundation for the GC extension, if you want.
And this is the kind of subtyping that WebAssembly has? Is the simple record subtyping? That's what you're supporting?
Yeah, record subtyping, contravariant function subtyping.
Okay.
What you would expect.
Yeah. Okay.
Looks like I made it look too simple.
Okay. Well, if there's no more questions, thank Andrea. Okay.
Second.
Okay. So now Ishan will tell us about constraint-based type inference error messages.
Yes. Can I get it to full screen? Huh? F5. Nope. 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 Can't get it to full screen, but that's fine, I guess.
Can you advance the slide? You can advance the slides from there.
Sorry?
Oh, go ahead.
Go ahead. Yeah. Okay. Good afternoon. I'll be talking about getting into the flow towards better type error messages for constraint-based type inference. And I'm Ishan, and my co-authors, David and Jonathan, are in the audience, and my advisor, Lionel, is not present here. And I'll start with that. So I mentioned a lot of jargon, but I'll try to explain it as I go on. So firstly, what is a type error? I'm sure a lot of people here are familiar, but I'll just walk through it. Most statically typed programming languages assign types to program expressions, and when that type gets used in a place that expects something else, we get a type error. And this OCaml program has a type error. I encourage you to just eyeball it and see if you can find it. So, so if we give it to the OCaml compiler, it does tell us what's going wrong, and it's saying that there's something wrong at line 9 at the app info expression. It's expecting an expression that has type string star string, but it's getting something that's string star float, and that's it. That's helpful, but can we do better? I think we can. So this is where our work presents data flow style error messages. It presents the same information, but a lot more, and helps the programmer with a lot more context in understanding how things are going wrong. So firstly, the first line is just the same. It says that a float does not match type string. It gives a kind of summary of what's going on, that a float is somehow flowing into a location that's expecting a string. Then it shows where the type float is coming from. It comes from line 4, and the 1.5 in the expression is where the float comes from. And then it flows into the argument to the process function where we assume a type variable, and then the argument gets applied to the parse version function, and the parse version function expects a string. So this is much more helpful and shows the full context on how we're getting the error. So this is the hypothesis that data flow style error messages are better, and that's what we started with. Our goals for this project were to formalize a practical type system that can identify erroneous data flows, then to categorize these data flows and create helpful error messages from them, and finally to check if those error messages are helpful or not. So just to now we'll try to derive a data flow and intuitively do it and then see how it's done in the type system. This is again a small program that has something going wrong. Let's see the data flow being derived here. It starts from the 2 and flows into the name binding x. The x is used in the then expression, and the then expression returns the type to the for the if then else expression, the whole thing. But there's also a flow here where the string x flows from the else expression to the if then else expression. We have 2 data flows here converging at a type variable. The type variable is the type of the if then else expression, and we can see that the data flow also has the sequence of source code locations that we then use to later present a beautiful error message. But where is this data flow coming from? So data flows come from constraints. And here our type system is using algebraic subtyping constraints. And this is the key insight. This is the main insight or the take-home learning from this presentation, is that we can interpret algebraic subtyping as a producer-consumer relationship. You can read this as there's a type A introduced at location or produced at location P0, and it's being consumed at a location P1, which expects a type T. How do we get these constraints? So I'll walk you through one typing rule to show you how we get these constraints. So to walk you through the rule, I need to introduce some notation. We have a location L, which is the program location or the coordinate for an expression, like a line and span for that expression. We have provenances. Provenances are sequences of program locations. There can be 0, 1, or more locations as provenance. We have primitive types like integers, strings, and type variables. And when we annotate those types with provenances, we get a full type. And then we have some typing state. The typing state stores all the relationships, all the data flow or the constrained relationships between types and different type variables. So I'll walk you through the if-then-else typing rule, because that's the example we saw. Now, to type it, we start with some typing state sigma 0. We have some context, and we try to type the if-then-else expression, which has E1, E2, and E3. And firstly, just regularly we type E1 to type T1, E2 to type T2. Notice that the context, notice that the state is flowing through the rules and collecting the constraints. After we've typed the expressions, we introduce the constraint. So we know that the conditional type, the type of the condition must be a Boolean, which means that type T1 is a subtype of Boolean. Here we introduce a constraint. But notice that this terminates the data flow, because T1 flows into Boolean. That's it. It terminates there. On the other hand, the type for the then expression and the type for the else expression flow into the type for the if then else expression, which is a fresh type variable. And that's the type we return after typing this whole thing. So we see that we introduce 2 types of constraints. We introduce a lot of constraints here. Some of them terminate, some of them flow into type variables, which can be further constrained. And that's why this is not the complete story, because the actual type system introduces a lot more constraints and type variables. In fact, each name binding introduces a new type variable. Notice that 2 flows into X, and X has we introduce a new type variable A let, which flows into the type variable A then, which flows into the type variable A if then else. And it's the job of the constraint solver to propagate all the locations into a final form which cannot be propagated further. So the 4 constraint thing that you see gets compressed, translated, or canonicalized into the second constraint that you see, which has all the locations for that particular data flow. And from this data flow, we can now create a complete data flow for this expression. Here you see that an integer is flowing into an A or a type variable, and a string is flowing into it as well. Now, if we could leave it here, because languages that support subtyping, like TypeScript, this would be a valid type. But what we want to do is our type system should also support languages that have unification. And that's the second key insight, that we do a second unification pass where we replace the subtyping constraints with equality or unification constraints. And here we find that there's a conflict. The integer is equal to a type variable, which is also equal to a string. And when we see this, we can use all the information we had collected beforehand to present the beautiful error messages that you saw. So just to complete this example, we get a string flowing into an int. We see the highlight, and we see where the string is coming from. We see where does it collide as such, and we can see what it collides with and where it's coming from. This is actually a level 1 data flow. So this is where we do the categorization, and we introduce a category of errors, a category of data flows. You notice that int flows into a type variable and string also flows there, but these are coming from 2 different directions. There is one change in direction. That's why we call it a level 1 error. And on the right-hand side, you can see an error with 2 changes in directions, and we call this a level 2 error. And if you notice, if you think of it carefully, then all unification errors can be represented in this way, from level 0 to level n, and it is one measure of the complexity of the error. So this is a tool that we give so that people who are constructing compilers can tune their error messages differently for different complexity of errors. That's how we constructed the error message, but is it useful or is it helpful? To prove that or to find that out, we had to do a user survey, and our user survey was done based on 1 user, 1 system, 10 programs. The programs we selected from a pool of easy, medium, hard that we had categorized, and then they were asked 3 questions. For our survey, we were using 3 systems. Helium is a Haskell compiler, an educational Haskell compiler, which gives good error messages for beginners to learn from. OCaml is the standard OCaml compiler, and HMLock is the system we implemented. And the questions we asked them were, did the error message help them understand the error? Did it help them locate the error? What is the problem? Did they understand what the problem is? And finally, after all of that, a free-form question of, what do they think about this whole thing? Well, the quantitative results, we could not show that our error messages were better. In fact, all 3 systems performed comparably well. In this graph, you see that without any significant variation, all systems performed. There was no significant variation across all the systems. And future studies can consider a mix of different problems or different textual error message layouts. More of this is discussed in the paper itself. But the qualitative results were much more insightful, and they gave us a much more positive indication that our error messages are actually helpful. Some of the comments, for example, the green boxes are for our system. So some of them said that it actually helps, and it's much more detailed, and it helps with subtle errors or long or difficult problems. On the other hand, some of them said that, it's not helpful. And on the other hand, some people from OCaml said that they would really like it if they could see where the types are coming from. So it's somewhat conflicting, but still there is a general need for errors that explain where the conflicts are coming from. So what are the recommendations we have from this? That we should support more language features. Our type system supports quite a few features of OCaml, but we can support more. And can we improve the textual representation of error messages? Is there an ideal representation? Can there be an interactive system for debugging, for understanding type errors? And finally, are there other applications for data flows, for example, semantic code search, which is a very interesting problem. Finally, this work is not done in isolation. There are, of course, prior work for this. Although the prior work is more orthogonal to our target, our question of explaining the error, prior work is more focused on error localization or finding a specific expression that's a likely source or the likely fix. And there are two different schools of thought, data-driven techniques or using algorithmic techniques to find that expression. But the most related, the most close related work that we had was from Holger Gast in 2005, which introduces a very similar concept of data flows. But our system is like a more practical version of it, proved by the fact that we actually have an implementation, and it also captures complex types like products, functions, and records, and it defines a proper mechanism to report errors and also supports lead polymorphism. So the goals we started with, we did accomplish some of that. A practical type system is implemented and available. We do categorize data flows and create helpful error messages, although that's still in contention. There are more user surveys needed to find out if it's actually helpful or new directions that we can go from here. And finally, that's my talk. Thank you.
Okay.
Hello. It's interesting how if you look at it from a certain perspective, you are doing type inference and checking that the type that you will infer is the type that you find. Can you expand on the connection between your work and type inference?
This is type inference, but we additionally, firstly, we don't eagerly cut the type inference in case a constraint is not satisfied. And secondly, we collect provenance information while we are doing type inference so that we can show how we reached a certain constraint. It is type inference with additional features built in to display better error messages.
So yeah, it's a very nice work and interesting. So not a criticism, but I have a problem that every SE reviewer will have. So regarding your user study, you only consider like one participant. So why not 10 participants?
No, it was one. So we had 120 participants. It was one participant, one system. I think that wasn't clear from my...
So it's not really just one participant?
No. Okay. There were 120 participants.
Yeah, but I think that's a bit misleading because...
Yeah.
Sorry.
I think I phrased it incorrectly. 120 participants were totally actually completed the survey. It was one participant was allotted randomly to a particular system. Okay. That's how it worked.
Yes, so can you say more about, like, you say you include some of the OCaml features, so what kind of features are not considered yet?
So it should support, actually OCaml, it should support most of OCaml features, but more complex features like occurs check or gadgets or type classes, these are things that are not supported. Yeah.
Okay, thank you.
Hi, Apurva from University of Iowa. I think you kind of answered my question. My question was going to be about language features that introduce kind of local assumptions. Yeah. It seems that your system may be able to incorporate it. Have you thought about it? Or have you just said that it's future work?
Occurs check is something that we can add, and it's like I've thought of it. I can add it in, but adding this for type classes or traits is more difficult. Maybe it's a good question to consider. And any other type?
JDTs or existential types?
That's future work. Again, good question, but we haven't really thought of how to integrate it in. Yeah.
Cool. Thank you.
Okay, so I think my question is slightly related to the previous one. In your presentation, you only showed examples where the path is linear, right? There's one single path from one access to, one usage to one declaration with a few direction shifts. But in case a variable is used more often, you typically get these more tree-shaped like things. Can your system deal with that, or are you planning to expand to that?
So that's a question that I've gotten before. it actually won't form a tree, it will form a layer, and I have that slide in the background here. So just check the slide here. That flow in the example that I shared does not directly flow to the location, to the version argument. It flows into a tuple type, which is applied to process, which gets tree structured. So it can flow through complex constructors, but it won't form trees. It won't form trees, but it can flow through complex constructors. Does that answer my question?
Slightly. So there's a bit of background. What I usually discover is in, type checkers that have type inference, if you don't take precautionary measures, it depends a lot on the order in which equality constraints are solved, where the error eventually ends up, right?
Yes.
And so you need, in case there's a conflict, you need to do some pruning. Can your system support that? Or should we perhaps take this discussion offline?
Yeah, we should, because I don't think I've encountered a situation where that will be needed. So,
okay.
I'll allow one last one. You promised to be fast.
So you had 120 participants and you didn't see a significant result. So was it because of high variance, or do you think there's only a small impact?
Can you repeat the question? 120 participants?
Yeah, so if you had 120 participants and didn't see a significant result,
yes,
then either the size of the difference is very small or 0, or the variance was very high. Can you say which you think it was?
There wasn't significant variation in, like, most people seem to find it equally useful, or find it difference in usefulness wasn't
so
too
if
large.
if there was a difference, it was small. So then the sort of follow-up research question is this as good as it gets? Are we done doing this research? Or is there a lot more to do and we just don't know what to do?
There seems to be, like, the indication here is that there's a lot more to do, because the qualitative results clearly indicate that, and not just the qualitative results, but even during the other discussions with people, clearly these kinds of errors are super helpful. So there's more, we do need more research on this, specific textual error message layout, maybe surveys in a different context, maybe live coding. This wasn't live coding, maybe a live coding context. So yes, more directions are there in terms of user surveys or specific layouts.
Okay, thank you.
Okay, so let's thank Ishan again. Okay. Now we have another coffee break and we resume at the top of the hour.
Welcome to the session about effect systems. Just before we start, there's going to be a sponsored talk right after the technical paper. So at 5:30, when all the talks are done, there's going to be one more talk that's not in the program from our sponsor. All right, and with that, I pass the word to Magnus Madsen, who's giving the first talk on Boolean unification.
Okay, hello. Nice to see you all. So there's been many talks today about type systems, effect systems. We also heard about inference. But something we don't hear too much about is the performance of type inference, perhaps because it's not always a problem. But in this work, I'll talk about how it became a problem for us working with Boolean unification. So this is a joint work with Jaakko and Troels. So I work on the Flix programming language. So it's a functional, imperative, and logic programming language. And in Flix, we can write pure functions. It looks something like this, saying here the addition function, adding x and y, doesn't have any side effects. We can also write impure functions, in this case, say hello. So this function prints to the console and it has an I/O effect. We can write functions that are effect polymorphic. So that's functions where whether the result of applying the function has an effect depends on its function argument. So for example, if you have map and you apply it with a pure function, then that application is pure. If you apply it with an effectful function, well, then it has that effect. Now, a bit more interesting and specific to this work is that if we have function composition, so if I have two functions, f and g, I want to compose them to get a new function, well, then we get the combination of their effects. And so in Flix, the way we express the language of effects is as Boolean formulas. So actually, you can think of pure as being true, I/O as being false, and then EF1 and EF2, well, that's just a conjunction. Okay, so this was already presented at Uppsala during COVID. Again, the brief idea is Boolean formulas is the language of effects. And so we would like to have complete inference, and we have that using Boolean unification. So that's nice. We implemented it, and it's working. But as we've been extending the library since then, actually tripling its size, the compiler was getting slower and slower. And so if you're building like a real system, it's really frustrating to see when performance is just falling off all the time. And so we needed to do something, and that's what this talk is about. So let's first look a little bit at what is Boolean unification. So in the Flix standard library, actually, somewhere deep inside type inference, this constraint arises. So here we want to unify x and y and z with x and w. Now, if you look at this equation, I'm sure you can find solutions. For example, if we set all the variables to true, that's a solution. Another solution is we could set all the variables to false. We could also be more sophisticated and see it's actually OK if we set just x to false. Then we can choose the rest freely. In fact, it seems there are many solutions. We could also set y to w or z to w and can come up with many solutions. So normally this can be a challenge for type inference because, which solution should we choose? Now, fortunately, in the case of Boolean unification, there is a best one, if you will, or a most general one. And this substitution captures all of the other substitutions. So it captures all the other solutions. In this case, it's this one, this substitution here. OK, good. So if I have such a Boolean unification query, I want to unify this side or that side, well, how do I do it? So actually, this problem has been studied for a long time. So there are two algorithms, go back more than 100 years. One is Boole's algorithm, and the other is Löwenheim's method. Boole's algorithm is also called SVE, for successive variable elimination. And it's not too hard to see that Boolean unification is a generalization of set, if one of the sides was true, for example. So Boolean unification is a computationally hard problem. Okay. So in general, we're not going to be able to solve it efficiently in the complexity sense. Now, the problem is, if we run Boole's algorithm on the previous query, this is the solution we get. Now, it's the same solution, or rather, it is equally most general to the other solution. The other solution was this small one down here. So we can obtain one from the other via substitution. But unfortunately, if you just implement the algorithm and run it, this is what we get. Now, what happens in type inference is that you're not solving one unification problem, you're solving a series of unification problems. So you solve one problem, and now you have the substitution. You apply it, and then you have to solve more Boolean unification problems. And now these formulas completely get out of control. And so this is the root cause of performance degrading. Okay, so in the original paper, what did we do about this? Well, the library wasn't as big, so we just had some ad hoc rules, like x and true can be rewritten to x and x can be rewritten to x, and so on. But now the library is much larger, and we have more richer effects. We have regions, for example, user-defined effects. So this doesn't work anymore. And if we try to type check the library with what we had back then, even with a very large computer, taking a lunch break, it doesn't terminate. Okay, so what do we do? Well, we need a line of attack. And so the idea is that, hey, let's look at these queries that arise during type inference and see if we can learn some information about their structure. And then if there's some structure, well, maybe we can exploit that and choose better data structures or algorithms. But of course, no matter what we do, the problem remains NP hard. So we will be looking at heuristics. So we considered several resource questions. I'll not go into a lot of detail, but just first of all, how many variables are actually in the queries? Do queries repeat? So there's good reason to believe they repeat because many functions sort of treat effects in similar ways. And is there any structure to the queries? So as a test subject, we use the Flix standard library. So this library, I think, is quite large for a library that's subject to an effect system at least. We have like 35,000 lines of code, 3,000 functions. There's a whole data log solver written in it, which includes a JIT and sort of data log optimizations. So we run the Flix compiler on the standard library, plus a large suite of test cases, and then we record all the queries we see. And we see queries at 2 times, during type inference and later during monomorphization. So in total, we recorded about 50,000 queries. And we find that most queries involve very few variables. Now, this actually makes sense because we usually have variables when we have higher order functions. So for example, list append, well, that doesn't have any effect variables. List.map would have 1 effect variable, and so on. So if you think about how code is written, usually functions are not, in general, that higher order. Moreover, we find that many queries repeat. So in fact, that we only see 380 syntactically unique queries. And of those, only 89 are semantically unique. So this number is kind of like, you can think of it as how many different ways are effects used throughout the standard library. Okay, so given this knowledge, what can we do? So we came up with a sequence of strategies as follows. So the first strategy is just the original baseline from the paper. Then the second strategy is that, well, we know there are a few variables in play. So we actually pre-compute a table that for every Boolean formula of 4 variables or less tells us its minimal representation. So you give me some large Boolean formula, but if it has 3 variables, I can compute its function profile and look it up in the table and get a minimal representation. Then we take the table, we add caching. So if we've seen the query before, then we just use that answer. And finally, we add something even faster than caching. We hard-code a few special cases that repeat a lot. So this is kind of what we're doing sort of in the years after, and I would call this sort of we have to do something, it doesn't work, so let's keep adding a lot of hacks and see if we can get it to work, right? Then at some point, it's like, okay, maybe we need to go for heavier technology. So let's switch to binary decision diagrams. So this is an efficient way of representing Boolean formulas. But then there's this issue that we have a very large compiler, and so we can't really, BDDs have a tendency to be infectious, but we can't really keep BDDs throughout the compiler, so we still need a way to get a minimal representation and then translate it back into an explicit form. And so here we did something naive. Then on top of that, we add this QMC algorithm. So that's a heuristic for we can use to turn BDDs back into small formulas. Then on top of that, we add back the caches, add back the special cases. And then the last strategy, we have everything where if the query involves 4 variables or less, then we use the tabling. Otherwise, we use BDDs. OK, so these are kind of the results in one slide. So this is the throughput of the compiler. The first strategy doesn't work, so there's no column at all. And for the other strategy, we can see that as we go up sort of down the strategies, performance improves. In particular, we can see the strategy 7, the kitchen sink, if you will, is the one that achieves the best performance. And that's because we're doing software engineering here, right? So we've now designed an implementation that really squeezes out as much performance as possible. And so with strategy 7, we are able to reduce the overhead spent down to 7%. So of the total compilation time, we only spend 7% on Boolean unification. Just briefly, so the tabling, I think I explained it already, but the idea is to pre-compute a table that for every formula with less than 4 variables has its minimal representation. And then you ship that with the compiler. We can compress it down to this. And then we use that table to look up in. And here you can see that, well, it was 95 as we saw on the previous slide. This is the distribution of queries and how many variables they have. So there's really just a long tail of a few queries that have many variables. Most of the queries have very few, even 0. That's like true and false, pure and impure functions. Okay, so that explains why tabling works. So what about caching? Why does caching work? So this graph here shows the ratio of unique queries. So we see for queries with few variables, we see them many, many, many times. So it makes sense to cache them. Whereas, for example, there's just one single query with 7 variables, so we only see it once. So caching wouldn't really help us there. Okay, so putting all this together, this is kind of an overview of the algorithm. So we get a Boolean unification problem like this. We look at how many variables there are. Less than 4, less than equal 4, we look in the syntactic cache. If it's not in the cache, then we run this Boole's algorithm, SVE, and where we use tabling to keep the formula small, and that gives us the unifying substitution. If there are more than 4 variables, then we're in kind of one of these tail cases that are much more complex to handle. Then we look in a BDD cache we have, and then we run SVE with BDDs if it's not in the cache, and then we have the unifying substitution. Okay, so that was a lot of stuff, right? If you're building your own compiler, what would be the takeaway from this? So a few lessons we learned, I would say. So first of all, if you do Boolean unification and you think you can simplify the formulas by hand, I don't think that will work. You need more sophisticated technology. Second, switching to BDDs actually made everything tractable again, but there's a very high overhead. And so we speculate that this is because BDD libraries, and we tried, I think, 4, they are very much optimized for big problems. So think like n queens or something like this, right? So for example, one BDD library would start n threads per query. But of course, starting 32 threads is kind of expensive when you're just solving a very small thing. So BDD libraries do make it tractable, and we find this PJ BDD to be the best one. There's a paper about it too. But then going further than the BDDs to really get a significant increase in performance, we exploit the fact that queries are simple and have few variables, so that allow us to have special cases, caching, and to use tabling. And so sort of in summary, the idea is we have this hybrid approach where based on how many variables there are, we will use one or the other strategy. So here at the end, a few questions that I invite everyone to consider is, could we maybe use different variable orderings in SVE to compute smaller unifiers? So without going into details, this is not about the BDD variable ordering, which is kind of a well-known thing that's been studied. This is about the ordering that is used inside the Boolean unification algorithm. There's another ordering you can choose there, and it has a huge impact on performance, but it's impossible for me currently to predict which one is better. The other thing is sometimes we actually know several of the queries up front, so could we solve them in a different order and increase performance? Right now, interestingly, it's like the syntax-directed order works best. So kind of descending into the AST and then starting from the roots and up. And finally, all of this has been done for Boolean formulas, but what about other Boolean algebras, for example, set formulas? So if you're interested in these things, come help make Boolean unification fast. So in summary, Flix is a functional imperative logic programming language. We have a Hindley-Milner type system. We have an effect system in there. Effects are modeled as Boolean formulas. I showed you very briefly, pure functions are true, impure functions have I/O, but it's actually a bit richer than that explained in the paper because we also have region effects, and they are modeled as these rigid variables. We use Boolean unification. The way we got it to work and scale is that we switched from things that were completely ad hoc to modern technology, so BDDs, but also then we added a lot of extra infrastructure just to catch the common cases and make them really fast. And also we have empirical evidence that sort of each addition actually gives you some performance. And that's it. Thank you for your attention.
Please, if you want to ask a question, step up to the microphones on either side of the room.
So I was wondering, have you considered the ergonomics of the effect system with Boolean some Boolean operations. So I mean, so there are some optimization or the Boolean unification, but is there any guarantee? Well, for example, they infer a simple effect type for the term, or is there any metric to show which one is more simple?
Right. So that's a good question. That's a good point. So I talked about performance because you want the compiler to be fast, but also you don't want the user to hover over an expression and then they are told this is the effect of that expression. So that's a big usability concern also, and the reason we want to have kind of minimal representations.
Hi, thanks for the talk. I guess one question is, you mentioned that I guess initially you need like even with 512 gigabytes and a long lunch break, you couldn't compile the standard library.
Yeah.
So with these changes, how long and how much memory do you need? Can you compile it in like 5 minutes, or is it still several hours?
So compiling the standard library, and you need test cases because otherwise it's dead code and it's eliminated. So 35,000 lines of standard library plus 30,000 lines of test cases, so 65,000 lines of code can be compiled in like 1 minute.
Oh, okay, that's cool. And also, is it, you mentioned that the underlying problem is NP hard. Is it the case that like you're fully exploring that NP hard problem, or is it, is the encoding actually some subset that might be easier?
No, it's not a
tackle?
subset. You can, I mean, if you take one step and you have this substitution, and so you get all the connectives and you have to, but I think it may answer a slightly different question. I think in type systems and programs, we have the hypothesis that types will be small. So for example, even for ordinary Hindley-Milner, it's possible to write this counterexample with this lead ladder and the types become exponential. And for effects, it's also the case in Flix that there are small effect formulas. So the problem is computing them.
Right.
Your turn?
I think I might have just figured out the answer to my question by sitting in this line, but just to be sure, when you say you pre-compute the result for up to 4 variables, if the same variable appears multiple times, it counts several times, right?
No, it just counts once.
Okay, then aren't there infinitely many 4-variable Boolean formulas?
Yes, there are. But you take any formula, it could be very long, right? But if you consider the truth table of it, it only has at most 4 variables. Then you can find the rightmost column by evaluating it for all valuations, but there are only at most 4 variables. And so you take that column, right, and that's the index into the table. And there you find the minimal pre-computed representation.
Okay, let's thank the speaker. The next talk's about compiling effect handlers.
Hello, everyone. My name is Jonathan. I'll be talking about our work to compile the effect language, which has support for effect handlers. So this is joint work with my amazing co-authors. Marius is also here at the conference and will also speak tomorrow about some other work which is related to this. So let me give you a little bit of context that motivated our work, which I present here. So a lot of our work is in the context of our programming language Effect. Effect was initially developed around 2020, and we presented it at Uppsala back then. And well, the basic idea is that we trick imperative programmers in accidentally doing functional programming. So we want them to feel at home, but still follow good principles, right? And to do so, effect systems are very important, and Magnus already talked a little bit about that. And I think here at Uppsala, SPLASH, we have heard also a lot about effect systems and why maybe sometimes you want to have them. But effect systems come with sometimes with some significant overhead and cognitive load and complexity. So we noticed that, well, if we look at a small subset of programs that have higher order functions, but not first-class functions, then we can provide users with a very concise effect system and very concise types. And we call this notion of polymorphism contextual effect polymorphism. So effect is, just to give you a brief overview of the language, is a language with the standard features of functional programming, like data types and higher order functions, and also standard features of imperative languages like co-data and tail calls. So co-data you would typically recognize as objects and tail calls as local control flow. But also, of course, local mutable state. But what makes it a little bit unique is that we also have some other features like resources, tracking of resources via co-effects,
and stack allocated regions, and for this talk, most importantly, handlers and contextual effect polymorphism, effect handlers. Sadly, I won't introduce you to effect handlers here, but let's briefly look at a very small example, right? Can somebody tell me what is the value of this free variable n in this example? Any guesses? It's not a trick question. Yes, it's actually 1. And it's good that you know that because, well, this is lexical scoping, right? This is not very surprising, and we might want to do a refactoring like this, and sometimes we do this as compiler authors, right? That's called optimizations, inlining. The question is a little bit more difficult if we look at effect handlers, or you can think of them as exception handlers for this talk here. Here we raise an exception, and the question is now, can we apply the same reasoning or not? Will this handler here be the handler for this exception or not? And the answer is not that simple because, well, in some languages like JavaScript, for instance, you could accidentally handle this exception in the higher order function map here. You could maybe even bundle a function, return it out of this try and force it on the outside somewhere. So it's not immediately clear where this exception will be handled. In our case, actually, this is what users write in our language, and under the hood, as a compilation step, we translate it to this, and this way we establish this lexical scoping again that you have seen on the slide before, right? So we can actually apply inlining to a certain degree in our language here, and users can also write this program if they want to make that intent explicit. So naming capabilities here also as a compiler technique establishes lexical scoping in our work. There's some dispute in the community whether we should call it lexical scoping, but let's go with this for this talk. So this is our work from 2020, but also other people apply very similar techniques. So there's the work by Izhou Zhang and Andrew Myers, and also Darek Bernatsky and his co-authors apply very similar notions of some form of naming of effects or lexical scoping. So we're not alone there. The question arises now, this is maybe a nice form of reasoning about effects. Let's assume this as a premise here. Now the question is, how do we implement lexical effect handlers? And we can note one thing, that originally, if you look at the literature on effect handlers, traditionally, it was very early noted that you can easily use existing control operators. There's a whole bunch, product line of control operators out there. One of them is shift 0, which was, I think, first mentioned by Olivier Danvy in some appendix. And Sam is also here today. They noted quite early in the Handlers in Action paper that it's somewhat straightforward to implement effect handlers in terms of shift 0. Okay? And very similarly, lexical effect handlers can be implemented quite straightforwardly using multi-prompt delimited control. This is a different kind of control, but it gives you names, so this makes the connection somewhat more clear through lexical handlers, right? If you can give names, then it might be simple, or at least possible to implement lexical handlers. What's not so easy, but Dan and Ningning managed, is to implement dynamic or traditional handlers in terms of multi-prompt delimited control. There's some work on that. And our focus here in this talk is how can you implement lexical handlers in terms of shift 0. Seems a little bit like a theoretical exercise, right? So why should we ever do this? I mean, there's a perfectly valid implementation already with multi-prompt delimited control, so why bother at all? Well, shift 0, as opposed to multi-prompt delimited control, has a very nice and well-studied translation into the CPS hierarchy. And now we have seen already that we could apply this inlining trick because we have this lexical scoping, right? So we can just inline our handlers. And now let's combine these two things. We inline the handlers, then we have just a term in CPS, which is system F. And then we can apply all the existing work on optimizing system F programs and get optimizations for free without actually looking at effect handlers. How can we have effect handler specific optimizations? And that's very attractive for me because I like to import existing work instead of doing it myself again. And we conjectured in 2020 that might be possible, and we already had some good evidence about that, but we never actually finished implementing a full compiler for a language from the start to the end. And the results back then were very promising. I said, okay, we should actually spend some more time on this. Like 2 orders of magnitude speed up sometimes, right? So that was very tempting to us to work on this. So the overall goal here is we want to translate lexical effect handlers to shift 0 in order to enable the compilation to iterated continuation passing style and then perform a lot of optimizations. So let me give you a quick overview of what we want to achieve. So on the left-hand side, you can see an example with 1 exception, and it should be handled by the corresponding handler in blue. Right. Now we translate this, and we translate it to something along the lines of the result on the right-hand side, where we have 1 delimiter reset, and we have shift 0, the operator by d'Envie, and it should be delimited by the reset. Right. So now if there is an additional handler in between the one that we actually want to go to, want to transfer the control flow to, well, we translate this to the following. So we still have these 2 resets that correspond to the 2 handlers, but now we need to jump over 1. Okay? So this is now shift 1 in the CPS hierarchy. And the number actually, like all good computer scientists, we start by 0. And the number is like, how many resets do we need to skip in order to find the correct handler? That's the intuition. And many more. I mean, the CPS hierarchy is dynamic. There can be multiple, or the one that we use. So there can be as many resets as you want at runtime, actually. So how do we do this? How do we translate effect programs from source to iterated continuation passing style? Well, in 2020, we already performed one translation from effect, which has an effect system, to system Xi, which relies heavily on second classiness and lexical scoping. And then in PLDI 22, we had a paper where we say, okay, if you have a region-based calculus, we call that a big lambda cap, you can translate that to, using CPS to system F. And both showed that, yeah, there's typability preserving and so on. So, but what was missing was this step in the middle, right? So we wanted to somehow go now from system Xi to big lambda cap, and this is what we fill in here. So if you would now compose all these titles that we had, you would end up with something like this. So today I'm presenting a typed CPS translation from effect escapabilities to regions. Right? So the part in violet is the one from today. So what's the idea here? If we slightly extend this example, we now have a local function f that closes over this capability. How do we translate this? Well, f, at the point of definition, we don't know yet exactly where f will be called. Right? So in this example, actually, f will be called under 1 additional handler. We don't know that at the definition side. So we abstract over the distance between the definition side and the call side. Here, this offset. We sometimes also call that evidence for reasons that become obvious in a few seconds, I hope. So this is the definition side here of f. This is the call side. And then we pass this evidence, which eventually is the distance between f's definition side and its call side under additional handler. So the key insight of this talk here is that evidence, or this distance, or the offset, measures the distance between the definition side and the call side, and I will show you briefly how we come up with the correct distance here. So how do we do this? Well, this is the same example, but we just renamed the handlers to inner and outer because now they fit on the slide. So what we want to achieve is that raise actually raises to the outer handler. And we start our translation now. We start in a region. So this translation that we perform actually is a typed translation in a calculus with explicit type-level regions and sub-regioning evidence, which you will see in a second. So we start in the top-level region, and now we enter the first handler. And the handler not only binds the capability here, but it also introduces a fresh type-level region, R outer, and evidence that everything on the top level on the outside can now be used also in this new region. Okay, this is term-level evidence, and you can think of it as number 1. So this is the current lexical region. It now changed to outer, and here we bind a mapping from the capabilities that we have in scope to the distance to how they could be used, right? So right now it's a number 0. Now we enter the inner handler, which also introduces a fresh region and evidence that now the inner handler is nested in the outer handler. And you might notice that we have adapted the translation context, so all of the existing bindings are now composed with this additional evidence that we have. We can build a transitive, we can compose them transitively, right? So before there was 0, and 0 plus R inner, F inner is F inner here in this case. And now we also entered the current region. And you can imagine, read F inner here in this case as the number 1. In CPS, actually, this is a very complicated CPS term denotationally, but here for you it's the number 1. And the last question is, okay, if we are now outer arrays, how can we know where to go to? Well, we need evidence that R inner is nested in R outer, but we already have this evidence mapped here, and we just look it up. Okay. So evidence measures the distance between the definition side and the call side. In the more general case, if we now look at the local function f again, we see, okay, we abstract now over this evidence. F also introduces a fresh region. It's a little bit more complicated. Full details are in the paper, but you can see we pass evidence. Function abstracts over it. At the call side, we instantiate the region and pass evidence. So having implemented now finally a compiler, right, the whole pipeline, we ran benchmarks, and we were, to be honest, very happy about the benchmarks, because we could observe quite a few speedups, and these speedups are always, you can't see the next best one, always compared to the next best one. So we compared against the F language, which performs some optimizations, OCaml, which has very good support for exceptions in particular, and the Coca language. And we could observe speedups from 1.6 to 23 times on community-maintained benchmarks. But we could also see some slowdowns. 2 points here or 2 of these benchmarks, where we could see slowdowns, actually amount to the runtime difference of Milton, which we use to compile and run our programs, and OCaml. And the other one is just the reason that OCaml is very, very fast with respect to exceptions, and we couldn't beat that. So the takeaway is, and this is taken from the paper, this formalism evidence measures the distance between the definition side and the call side. And in the paper, we have more of these formalizations, and we have a full typed translation of a calculus with second-class capabilities into regions. We show that the translation is type and semantics preserving. We support more advanced features and also show the benchmarks, of course. And I want to insert a small plug here to another talk, because we've just seen how to go to CPS. Right? On Friday, we see how to go back to direct style. This is Marius who will give a talk on how we can define an inverse translation to the CPS translation. So in conclusion, I've showed the compiler pipeline, an example, the benchmarks, and I thank you for your attention.
Please step up to the microphones again to ask questions. Can you say a little bit about how this translation is dependent on the internals of effect, maybe even those things of effect that are kind of orthogonal to effect handling?
I think most of the features are orthogonal to the translation. So if you have name binding constructs, that's of course important because we use the lexical scoping. We do distinguish between values and computation, following the school of Paul Levy and fine-grained call by value and call by push value. We only have to do this translation for computation, actually. So capabilities, they correspond to computation. And we distinguish between these two binders. So this evidence and accounting only needs to be performed for computation. So you could add arbitrary value bindings, and you don't even need to do our translation there. But for computation, you need to do this.
Hi.
Hi, Ken.
Hi. So when the evidence is passed, a number, or it's evidence that a number is smaller than another number, right? But to turn that number into like a shift operation, there's a loop, there's some loop somewhere, right? That says, lambda n times or something. And the lambda is just skipping over the, Is that loop like a compile time on-road loop, or is there like a runtime?
It's a very good question. Easy answer is no. 0 is the identity function. 1 is a crazy CPS term that corresponds to lifting a program that runs in a scope with 1 continuation into one that has 1 additional continuation. And then a composition of 2 evidence is function composition. So we can assign denotational meaning to these evidence terms. You don't need to do that to actually translate numbers into something. I just use that for presentation. In the compiler, we use CPS.
So like the loop I'm describing is sort of deforested away at like. Okay,
yes, it's a little bit like church numbers.
Yeah.
But in CPS.
I have a maybe slightly silly question. You should be able to implement shift 0 using your effect handlers as well. I know that's not the purpose of your translation here, but have you seen what happens if you apply the translation, I don't know, twice? If you translate into shift 0 and then go back to your effect handlers and again,
No.
would you end up with a sort of explosion in the size of your generated code, or would you reach a fixed point?
Most likely explosion, I would say. I'm not sure. So it's not a reflection or something, if you get at that. No, I've not looked into that. I mean, we can talk about this. Sounds like a crazy thing to do.
Thank you very much.
Thank you.
We stay on effect handlers now with gradual typing.
Okay. So can everyone hear me? Okay. So hi, everyone. I'm Eric Giovannini, and today I'll be discussing our work on gradual typing for effect handlers. This is joint work with my advisor, Max New, and Daniel Licata, and we would like to thank the NSF for their support of this work. So we're in an effects session, so I'm going to assume that we all appreciate effects and handlers. Unfortunately, effects in mainstream languages are still relatively new, but progress is happening. For example, OCaml 5 introduces effects and handlers into the language. But progress is incremental, so OCaml currently lacks an effect typing system. That is a system that tracks the effects a given part of the program may raise. And given that much of the interesting work on effects is related to effect typing systems, in order to bring that research to bear on an actual implementation, we would need to add effect typing system on top of the existing type system for OCaml. So before continuing, I just want to mention some important terminology that I'll use in the remainder of this talk. So a checked or tracked effect system is a type system which tracks the effects a given part of a program may raise, whereas an unchecked or untracked system, the type system only cares about the input and output types of effects. So going back to our motivating question, of retrofitting an effect typing system, this is certainly a non-trivial task, and we want to do this in a way that doesn't require programs to be rewritten from scratch in the new language. So in particular, we want interoperability between programs written in the original unchecked language and programs written in the new effect type system augmented language. And we want programmers to be able to incrementally migrate their code piece by piece from unchecked to checked style. And equally importantly, though, we want the parts of the code that do utilize the checked effect typing to enjoy the benefits of reasoning principles that this typing information gives us. So, we want the equations that we expect for effects and handlers to hold for the portions of the code base where the effects are checked. So to study this question, in this work we present Greph, a gradually typed language with effects and handlers. And we design a syntax for Greph and axiomatize the desired behavior in the form of an equational theory. And from these first principles, we derive an operational semantics, and then we prove the soundness of the theory, which shows that Greph does satisfy the desired properties. So to further motivate the utility of gradual effect typing and demonstrate how Greph works, let's consider a simple example involving a thread scheduler that can handle computations that may raise effects. So there are three modules here: operations, which declares the effects, and then scheduler defines a simple thread scheduling function, and then main imports the effects in the scheduler and runs the scheduler on a simple computation. So so first we'll look at a version of this where there's no effect tracking. And so in the operations module, you can see we declare the print, yield, and fork effects. And then in the scheduler module, we import print and fork, and we define a scheduler function that takes a thunk, which may itself fork, and interleaves the computation of the resulting thunks to produce a final string result. Now, we note importantly that the scheduler function does not handle the yield effect. As for example, say the programmer forgot to implement the handler for yield. So then in the main module, we import the effect, operations, and the scheduler, and then we declare these two thunks, letters and numbers. Numbers prints out a number and then forks with letters as the continuation, and letters prints A and then yields. And then at the end, we call scheduler passing in numbers as the continuation. But so remember that the scheduler only handles fork and print, and so when we run this program, we're going to get an unhandled effect because letters will raise yield, but the scheduler didn't handle it, so it'll get propagated to the top of the call stack, and the program will be stuck. So the programmer, will likely have a tough time figuring out why the program is stuck, and this is where more precise effect tracking can help us. So now let's see what happens when we make part of the program more precise. So we're going to make the scheduler more precise, but leave operations and main modules imprecise. And we can do this because the language is gradual. So you can see that in operations, the only thing that changed is that we added this question mark on the function passed to fork, and this just indicates that we're not tracking what effects that it could raise. And so this is a sort of, we call this a dynamic effect type. Now in scheduler, we do specify that the function passed to the scheduler may be able to fork or print, and that scheduler itself will not raise any effects. Now main is the same, except that note that we import scheduler, we keep that imprecise. So when we import it, we keep it as dynamic, and then the letters, numbers, and main functions are the same, and now we get a runtime error. So the scheduler's argument yielded, but we can only accept fork and print, the definition of scheduler. So this is more helpful for the programmer to know, okay, what went wrong here. And then finally, we can make the main module fully static. We can say that it expects the scheduler to handle fork, yield, and print. And then we also specify that main has an empty effect type, which means that no uncalled effects will be propagated out of main. Now, when we do this, we'll actually get a compile time error here because now the compiler knows, okay, you tried to import this, the scheduler with this type, but this is not allowed according to the definition in the other module because it can only fork and print. So observe that, as we did this, we migrated gradually from fully unchecked to fully checked in an incremental fashion. And doing so did not alter the meaning of the program, except that, we caught the error, more quickly by transforming it from an implicit error, then to a runtime error, and finally to a compile time error. And furthermore, throughout this process, the fully tracked, fully untracked, and mixed modules were able to interoperate with one another at all times. So, now that we've seen kind of an example of what we want out of a gradually typed language for effects, I want to say a few words about gradual typing itself, more generally. So, gradually typed languages allow the programmer to combine static and dynamic typing disciplines in the same code base, and they support incremental gradual migration of a code base from dynamic to static style. Now, I should say in this general sense that, static and dynamic don't literally have to mean static and dynamic typing, like Java versus Python, say. But, the static and dynamic here is more general, and in fact, in our case, they're both statically typed languages in the usual sense. It's just that dynamic here means it lacks checked effects. So that's gradual typing. And then on top of that, sound gradually typed languages offer us type-based reasoning principles for the statically typed portions of the code base. Right. So now let's discuss the design of greph a bit more. So greph consists of two pieces, a module language where we can declare, import, and export effects, and then a expression language where we can raise and handle those effects. And our syntax is designed loosely following the methodology of the abstracting gradual typing from Garcia, Clark, and Tanter, and it's a mix of the Seek, Taha, and Tobin, Hochstadt, Fleisen typed racket styles. And our notable features for greph include subtyping, and it uses deep handlers. So I'd like to mention now like an important design decision, interesting question that we kind of were thinking about when we designed greph. So let's say we have a module A here that exports an effect, my effect, with request int and response type bool. And then we have a module B which imports that at a less precise type here for the request, and then calls my effect, raises it with hello as the argument, and then handles it, as you see at the bottom. Now the question here is, should this code raise an error? And actually both answers are compatible with the criteria that we initially set out for our language, but we argue that it should be no, that this should not err, because basically we feel that this is more in line with the spirit of independent migration of a code base with gradual typing, and if provided that all the kind of the handling happens locally within module B, so if no one in module A is around to observe this typing violation, then we say that it's actually not a violation. So now I'll switch gears and give an overview of the meta theory of greph. So greph, what we've been calling greph is more properly called, I guess, surface greph. So this is elaborated to a cast calculus, as is common in gradual typing. And then we formulate an equational and inequational theory for core graph, consisting of axioms that model the desired properties of the language. And then from these axioms, we can derive an operational semantics. And then we prove that the theory is sound with respect to this semantics via the logical relations model. So let's discuss core graph. So unlike the surface language, core graph has explicit value and effect typecasts, as shown here. So here on the left are the value casts, up and down casts, and then the effect casts, up and down. So these casts are inserted as needed by the elaboration process. And then, in addition, there are actually no effect declarations. There's just a fixed signature, global signature of effect names, which is determined at elaboration time. And lastly, there's a term representing runtime type error shown here. So now let's talk about the axioms. So in formulating the axioms, there were two kind of relations that we want to model here. First of all, we have the usual contextual equivalence for programs, which we're going to use to model reasoning principles for handlers in terms of optimizations. But we also want to model the situation where one term behaves the same as the other, except that it might err more. And in gradual typing, this is formalized as a syntactic ordering called term precision, which I'll discuss more on the next slide. And now from these axioms, we derive an operational semantics in the sense that we can prove the following theorem, which says that if m steps to n in the operational semantics, then m is provably equivalent to n via our axioms. And so this, in a sense, means that the reduction rules are determined by the axioms, because any observably different semantics would not satisfy this theorem, and then thus any different semantics must violate one of our equational principles. So I'll talk now about term precision. So this is a syntactic relation between terms m and n, and we say that m is more precise than n if the types in m are more precise than the types in n. So intuitively, this is intended to model the notion that m behaves the same as n, except that m may err more. And to axiomatize this, we follow the prior work of New, Licata, and Ahmed. And then we additionally include axioms specifying the relation between subtyping and casts. And then, you can see these and the rest of our equational theory in the paper. Just to show an example of an axiom that we include, this is a very simple one, but it just says that error is the most precise term. And this makes sense because term precision models the situation where one term errors more than the other, and as error always errors, it makes sense that then error should be, syntactically less than any term n. So then equivalence is intended to represent the usual program equalities we expect to hold. For example, beta and eta laws for function types. And for handlers, we have beta rules for handling a value, which you see here, and then also for handling arrays of a value. And then we also have an eta principle for handlers, shown below, which says that a term m that raises effects epsilon 1 to epsilon n is equivalent to a handle of m, where in each case we immediately re-raise the respective effect with the given argument. And this is an example of a useful optimization principle by which compilers can remove unnecessary handlers. So here I'll just show, these are two of the, these are the rules basically for downcasting of, with effect casts of arrays. And I won't get into the details of these, but I will just say that deriving the correctness of these rules actually follows from a result that we were able to show from the axioms, which says that of all effect casts are equivalent to a handler. So now that we've shown that operational reduction implies equivalence, we want to show sort of the converse to this. That is, we want to verify that the operational rules validate all of our equational principles. And we do this both for program equivalence, which is soundness, and then graduality, which says that if m is more precise than m prime, then either m errors or m and m prime behave the same. And we do this through a binary step index logical relation, extending prior work to handle subtyping and effect handlers. And here's the graduality result. So if m is more precise than m prime, then either m errors, which is case 1, or cases 2 through 4, they behave the same. So currently we want to add support for the following features: polymorphic types, which will follow by adapting prior work on gradual typing and Hindley-Milner type systems. Recursive effect types and dynamic generation of effect names seem feasible. And then there's a question of the performance cost of strong gradual typing, which is an empirical question to be addressed in future work. And we would like, obviously, to have an implementation of GRIF so we can address such empirical questions. So to summarize, in this work we present GREF, gradually typed language with effects. We derive an operational semantics from first principles, and we prove soundness and graduality, which achieves our desired goals for the language. So thanks for listening, and I'm happy to take any questions.
Thanks for the talk. Have you thought about the feasibility of implementing this on top of OCaml 5? I mean, I guess obviously you need to deal with polymorphism, but...
Yeah, so polymorphism is one of the, I guess, big questions, and then, but I think first we want to get like a working implementation just of Graph itself, and then we can think about how this would work in terms of OCaml.
Okay.
Actually, a comment on that last one, it occurs to me that if you don't have polymorphism implemented, you can use graduality to get around it.
Oh.
Anyway, my real question was that you motivated this work from introducing effects into OCaml, but right. I wonder if it might be useful in the long term too, because some people don't like the overhead of describing exception effects in Java. So maybe maybe this would be something used by the community for a long time. I wonder if you have a comment or if thought about issues like that.
Sorry, could you repeat the?
Yeah, sorry. Maybe some people will really want to have effects in the static type system OCaml, and maybe some people will indefinitely not want to use effect types, and so they will benefit. They might they benefit from the graduality of your system in the longer term, not just in transition from one to the other.
Yeah, that's interesting. So I think that the nice thing is that our system is sort of opt-in in that you can choose not to annotate at all, and it'll be equivalent to sort of the original OCaml without the effect typing system. I don't know if that answers.
Please join me in thanking the speaker again.
Thanks.
I'd like to remind you that after we have 2 more technical talks, and then we have a talk from one of our sponsors right after in this room. And with this, when does concurrency matter?
Yep. Cool. Hey, I'm Luke Cheeseman, and I'm going to talk to you today about behavior-oriented concurrency. This is a joint work between Imperial College, Uppsala University, and Microsoft Research. But before I get into the what of BOC, let's get into the why of BOC. So central to concurrency are 2 mechanisms: parallelism and coordination. Parallelism is executing tasks at the same time, so you can think threads, tasks, coroutines. And coordination is restricting access to data for an unforeseeable schedule. We believe there's an interdependence of the 2 mechanisms that should be recognized and controlled through a single powerful primitive. But why? Well, if you're building an async runtime, then relying on synchronization primitives can block your threads and you may screw up your runtime. On the other hand, if you're increasing threads to improve performance, you may harm scalability as threads start to race for resources. We're certainly not the first to recognize this. Primitives should exist. An early advocate for this was actors. But actors have a serious pain point, which we aim to address. So what do we want? We want isolation. Behaviors execute as if no other behavior is executing at the same time. You want parallelism. The behaviors that don't have dependencies on one another can execute at the same time. You want ordering. That the programmer's written order of their program influences the order in which behaviors are executed. And you want deadlock freedom. But actors have all that, but actors really struggle at one thing: when you have atomic operations over multiple actors. So consider the transfer here. You have 2 accounts represented by actors, and you're trying to transfer money from the source into the dest. An actor can only influence its own state, so how do you influence 2 states at one time and don't see a partial transaction? I'm going to show you how we do it. Oh, sorry. On top of that, if you want to order multiple atomic operations, it becomes way worse. So here we're doing the transfer. We have 4 actors: the teller, the source, the dest, and the manager. The teller tells the source it wants to acquire it. The source says it's acquired. It tells the teller it's been acquired. The teller repeats that with dest. The teller sends a debit and a credit message to each of the actors, telling the manager that's going to coordinate the transfer. Those 2 actors tell it it's now going to stash and it's not going to enter any other transaction. The teller can now release those and start so they can take more messages. The 2 actors tell the manager that they can do the transaction. There is enough funds. They are not in any other transaction. The manager tells it to commit, and that those updates should become permanent and complete. That's a lot of messages. You build your own synchronization mechanism on top of a concurrency paradigm. So what's the box solution? It's that simple. You just do a when on the source and the dest, and then you can access and update them atomically. That's amazing, right? But I didn't explain what any of that meant. So in a nutshell, BOC is composed of 3 things. You have cones, or concurrent owners, and these are protect pieces of separated data. It's a single entry point into them. You have behaviors, which are units of concurrent execution. They modify your cones. And you have when, which is this single powerful primitive, which ties the 2 together. You spawn a behavior with a set of required cones, and then you can modify those cones. So you can think of cones and behaviors as resources and tasks, or locks and lock guards, whatever sort of makes sense for you, but the whole thing for us is BOC. So coming back to these points of what do we want for a concurrency mechanism, let's look at this example. We have a behavior which executes on source and dest and source dest, and we have some logging in between. So there's clearly some intention here with the program. When we say we want isolation, we want credit and transfer not to happen at the same time. They both use the source cone. When we want parallelism, credit and freeze don't affect the same cone, they can execute at the same time. We want ordering that credit uses the source cone and so does transfer. So one should come before the other because the program has written down this way. But here we actually want a deeper notion of ordering. So credit came before transfer, so we want the logging of the credit to come before the logging of the transfer. We want deadlock freedom, and I'm going to add one more property here. We want flexible coordination. We want to fix the multi-actor update problem, and this is the bit on line 9. So how do we get that with Bok? To answer that, I'm going to walk through an abstract execution of a Bok program and show that we get all that. So on the left here, we have the program that we're currently executing, and on the right, we're going to start building up a DAG of behaviors. So here, we spawn the credit behavior. It gets into the DAG. It's pending, so it's red. We now spawn the freeze behavior. There's no dependency between credit and freeze, so there's no edge in the DAG. We spawn the transfer. And so here we have the flexible coordination. We're spawning over the 2 cones, and we can enter the DAG. We have ordering. The credit uses the same cone as the transfer. The freeze uses the same cone as the transfer. We're going to execute this DAG from top to bottom, so we're going to get that credit and freeze happen before transfer. And we have deadlock freedom. We're building a DAG of operations, so we can't enter a cycle that ends us in no progress. So we start executing the program. We execute the credit behavior. And we can also execute the freeze behavior. So we have parallelism. Behaviors with no dependencies can execute at the same time. Okay, we terminate the credit and the freeze, and we start executing transfer and the log C. So we have isolation. The transfer used the same cone as the credit, so we couldn't run them at the same time. It's one then the other. And also, we have this deeper ordering that I mentioned earlier. So you see that because credit came before transfer, we get that the log comes before the log T. So log C and log F will come before log T. So coming back to those properties that we wanted, we have isolation, we have parallelism, we have ordering, we have deadlock freedom, and we have flexible coordination. So we got all the things that we asked for. But how can you use that? So we have developed a formal concurrent semantics. This is the semantics. This is all the semantics. It's truly just these 4 rules. It's very succinct. And we make it this succinct by building on top of an abstract underlying programming language. We don't add when to a simply typed lambda calculus. And by doing this, we can then let any other language that fulfills the properties of that underlying language adopt Bok. Coming back to how can you use it, we've also built a C# implementation, which backs onto a C++ runtime, which can act as the library for other languages. So let's look at that C++ runtime. So we've added that flexibility. We've got something great. Has there been a cost? Did we screw it all up? How do we measure that? Well, does Bok work in practice? Does it pay this horrible cost? And does Bok address the multiple actor update problem? So to answer that first question, we built Savina, the actor model benchmark suite in Bok, and we compared it against Savina in Pony. So we've done this for 2 reasons. Pony's been shown to be as good as other actor languages or best in the Savina benchmark suite. So if we compare against Pony, we feel it's reasonable to say that we're comparable to the rest of the actor model languages. We do it against actors because there's a very trivial transformation from actors into Bok. And so if we don't have an overhead there, we think it's fair to say there's no overhead introduced. So in this graph here, there's the benchmarks in the leftmost column. And then green means there's more than a 20% speed up from when we build it in Bok. The squiggles is we're roughly the same. And the red plus is there's a bit of a slowdown in Bok. And as you can see, tons of green. So we think it's fair to say the flexible coordination came without an added overhead. To demonstrate that the flexible coordination scales, we took one of those Savina benchmark suites, the banking example, and we changed it in the way that I showed you before. We removed all the communication overhead that had to exist in the actor model and just did the when over the multiple cones whenever we needed to. And we can see that when there's substantial amounts of work to be done, as we scale the hardware threads, We see this nice curve coming down. So we feel that the flexible coordination scales. So coming back to those things I asked about evaluating, we think it works in practice. You don't have a horrible overhead, and it answers the multiple actor update problem. It scales nicely. So I hope I've sparked an interest in behavior-oriented concurrency, and I know you're going to go and read the paper. So what can you find when you go and read it? There's a lot more. There's a high-level description of BOC. We walk through the features of BOC, by example, introducing it slowly. We build that semantic model that I showed you just before, and we talk about the properties that are required of an underlying language and how you get certain guarantees. There's more details of the C++ implementation, how we build that DAG, how we ensure that the runtime doesn't introduce deadlock, and a lot more. And there's a thorough investigation of the evaluation that's shown just now, plus a few more details. So examples of why sometimes we're worse than Pony, why we improve other ways. So, in conclusion, we think that when is a simple, intuitive, and expressive mechanism. It provides a single mechanism for both parallelism and coordination. It addresses the multiple actor update problem and performs comparably with existing actor languages. Now, this work is much more than just my own. It's been the collaboration between all these people who work at Imperial and Microsoft and Uppsala. And BOC is more than just an independent project. It's part of Project Verona, which is a programming language aimed at building cloud infrastructure. Another part of that is Reggio, a talk which was presented earlier by Ellen, which builds the language that serves as the underlying language to BOC. So I'm going to leave you there. I hope you've enjoyed the talk, and I'll take questions. And I'm graduating early next year and would love jobs.
Hello. So in the, let's say, core slide, when you show that you use your when between two actors instead of the manual coordination, how that work? Like, is it something like, is the semantic like, I am sending a message to both actors, and so a single thread of execution is...
So you're thinking of it like actors, right? So actors have message queues. In behavior-oriented concurrency, we separate the message queue and we separate the behavior and the state. So you don't send a message to the cone. You sort of create, as I said, the DAG. And once you've built that DAG, you can just execute because you know that there's no race.
Okay.
You sound unconvinced.
No, I understand. You can also visualize it as one actor sending its data to the other actor and then having the data back or something like that?
But that would come with a runtime overhead.
Sure.
Yep.
So this might be related, but it might also be an earlier question. I'm a little bit confused about why you posed this in the framework of actors at all, because I don't see any actors in your solution. It just looks like concurrent imperative code.
Interesting.
Okay, so can you resolve my confusion?
Of how it's like actors, how it's unlike actors, or both?
Yes, I mean, maybe it isn't, but I assume it is because you presented it that way.
Yeah. So in the way of actors, it's all asynchronous spawning behaviors that execute all over the place, right? So when you take that, like behaviors are, it looks like imperative code, but it's not blocking in place. Every spawn is an asynchronous behavior that will execute asynchronously. So you're not like walking through the behaviors one by one, like typical imperative. It's not like locks and lock guards, if that makes sense. That's where it moves away from being that kind of imperative code. Does that make sense?
You're certainly blocking until you get the resources for a when, right?
No. So sorry. When you do a when, you just spawn, you put them in the work queue, and you move on straight away. You don't block in place.
Okay, so if there's something afterwards, it can continue even when that when is waiting.
Yeah.
Interesting. Okay, thank you.
Over here.
Hello.
Can you say something about what went wrong with Civ?
What went wrong with SIFT?
You had the Civ, the benchmark that had 2 red blobs next to it.
We can't see your slides anymore.
Sorry.
Yeah.
What went wrong with Civ? What went wrong with Civ? Normally, it's one of 2 things. It's that Pony is a much more mature runtime, and so it does things like backpropagation, which stops you. Yes. Okay. This was ridiculous. Pony, for some reason, generated it in 32 division, and we didn't, and that was the whole difference. If you just manually change the binary to do it in 32 division, it fixed the whole benchmark.
Let's thank the speaker again. All right, so the last technical talk before our sponsorship talk is about introducing effect handlers into WebAssembly.
Okay, great. My name is Luna Phipps-Costin. This is Continuing WebAssembly with Effect Handlers, and this is joint work with the people whose names are on this slide. So I'll introduce WebAssembly. It's a programming language intended to express programs in a number of different languages, and it is designed to be executed quickly in a portable sandbox with predictable performance. So I'll give a quick overview of what it actually looks like. It has flat stack-based instructions, and it has structure control flow. It has a type system that can enforce the stack shape and the type of operators. And we have function pointers, but functions don't capture their environment, so we don't have closures. And it's designed to not require garbage collection at all. So here's an example of what WebAssembly looks like. Each of these, this is just a sequence of 3 instructions. The first 2 push to the data stack, and then this add instruction pops values off the data stack, adds, and pushes a result. So these reduce to the expression on the right. And we can type these instructions, capturing the intuition that the constant pushes an integer on the stack, and the add expects to on the stack pops them and pushes a 3rd integer. The structure control flow can be a little bit confusing, but it's going to be relevant, so let me introduce it. This loop instruction is not a loop. Both the block and the loop are semantically equivalent to their contents, which is a sequence of instructions, with the exception that they each introduce a label. When we use the BR instruction targeting a label, control moves to a location depending on the nature of that label. In the case of a block, control moves to the end of the block, this right pink parenthesis. In the case of a loop, control moves to the beginning of the loop, so the left parenthesis. So now that we know what WebAssembly is like, sort of, let me talk about an issue for WebAssembly, which is that a number of programming languages that are popular and that care about WebAssembly have some sort of non-local control flow that's central to their identity. Things like lightweight threads, like iterators, like async and await. And by the nature of these control flow features, they're not trivially expressible using WebAssembly's call and local control. So the current popular solution is to do some kind of transformation on programs to resemble continuation passing style. And to reduce engineering burden, we can do this at the WebAssembly level, so we can share a single tool called Asyncify from Alan Zakai and the Emscripten team. Because of the constraints of WebAssembly, this requires doing things like splitting locals to memory and branching on calls. And so there's some cost to this, both in time and program size, and also just kind of the engineering burden of using this large tool. So we look to Plotkin and Pretner's effect handlers for inspiration for a different solution. And it turns out that effect handlers fit extremely well for this use case. So, we know they're very well researched. We just heard a bunch of talks about them. They're expressive enough to express all of the control that we've just talked about. All of the operations of effect handlers can be effectively typed in the WebAssembly stack-based type system. And recent work has shown that it can admit performant implementations. And we also just saw more of that. I want to briefly point out run and def control because our effect handlers are very similar. We have typed control tags and thus effect forwarding. That's the main difference. And also that despite all the discussion of type and effect systems so far, we don't extend the WebAssembly type system. We don't want to extend it, so we have no effect system. So let me capture the intuition of what it's like to implement non-local control. So imagine that we want to implement, for example, lightweight threads in some interpreter. Well, to do so, the obvious thing to do would be to modify the interpreter to capture any information relevant to a given lightweight thread. This would be the current control, maybe any thread local state that's necessary, and reify this into some object. Maybe we'll call it a context, and maintain a queue of these contexts. And then we can do simple round-robin scheduling, dequeuing contexts, passing control to that context, and then in some way pulling out and continuing to schedule. And what's captured in that explanation is that what we're doing is reasoning with, capturing, and resuming suspended computations. And these are continuations. So what we want to do is provide faculties so that we can implement this control flow as a library. So, implementers of non-local control for a language that targets WebAssembly can implement this control flow in the runtime of their language, which is compiled to or written in WebAssembly. And so okay, if we want to do that, provide system stacks, right? And we can access the stack pointer maybe, or set jump and long jump. But WebAssembly isn't intended to be portable. This is not portable, and it's gratuitously unsafe. So we want to provide some alternative to these low-level primitives. And so effect handlers are what we do. And I will bring up two kind of ways of understanding this because I haven't actually been kind of explained semantically yet today. So one is that handlers can allow us to dynamically assign a semantics to operations. Like we might have an operation to yield a value for a generator, or an operation to defer to the scheduler for lightweight threads. And so we can dynamically assign a semantics to those as a library. And then the other one that tends to help is people are familiar with exceptions. We're familiar with having a handler for some particular class of exception that's somewhere in our dynamic extent, and when we throw control passes to the handler. But of course, the main difference is that we can then resume one of these exceptions, and we can even store away that resumption for later. So we extend WebAssembly, and we call this WASMFX. And the extension is fairly minimal. The things I'll point out is that we can declare control tags, which represent an operation. And we have 3 core instructions that allow us to work with that. Cont new accepts a function pointer and allocates a continuation. Resume accepts a continuation, installs a handler, and passes control to the continuation. Suspend suspends to a given operation the nearest handler for said operation, and also passes the current continuation. And even though the syntax is a little bit weird, it's also a little bit different because we can't rely on garbage collection and closures from what we might be used to. So I think the best way to get into this is actually an example. On the left, we define a reschedule operation. And this is just a name that I've chosen. There's no reschedule syntax in WASMFX. But then we can use that in a process. So I've written this function that prints 1, and then performs the reschedule operation, and then prints 2. And that's all I've written. So we need to actually assign a semantics to reschedule in order to run this function. And we can do that in our scheduler. So on the right, we have a scheduler. And please bear with the WebAssembly syntax for a minute. This actually is fairly simple and resembles just a simple round-robin scheduler. So the highlighted part is just entering a loop and dequeuing a continuation representing a thread off of the queue. And then we can resume that continuation, passing control to that continuation. And so if we imagine that that continuation is representing our process, control passes to that process and now prints 1. And when we perform the reschedule operation, control will pass to a handler that we installed. And actually, when we resumed, we associated the reschedule operation with these 4 lines that I've highlighted. So now control passes to our handler for reschedule, and it also passes the current continuation. So our semantics that we're going to assign to reschedule is that we're simply going to enqueue the remaining continuation of that thread back to our round robin queue, and then loop to continue another thread. And so after we've run some more threads, we might come to this process thread again in our queue. And when we resume, because we enqueued the remaining continuation, control is going to pass to the printing of 2. And when this function returns, we can execute our return handler, which simply continues with the next thread. And so spawning this process is as simple as allocating a continuation representing it and then enqueuing it. So I'll go into the 2 most interesting instructions in a little bit more detail. So this resume instruction is syntactically a little bit weird. In a bytecode, we prefer non-nesting instructions for a number of reasons. And so rather than include blocks within resume, we associate tags or operations with labels. And those labels represent our handlers. And because of how blocks and branching work in WebAssembly, what I've written here actually associates the final line as the handler for the T operation, because it's the end of the handler block. And when we return, control passes directly after the resume instruction. So we can think of our return handler as simply following the resume instruction. That's highlighted as well. We also have this continue instruction. And people who are familiar with the traditional treatment might also wonder, why don't we allocate a continuation when we, for example, install a handler? Well, we want predictable performance characteristics. So with this treatment, we know that any use of continue allocates a continuation and nowhere else does. And it also makes sense ergonomically because we can't use a block or a closure because we can't allocate closures in WebAssembly. And we also want to be able to install handlers on existing continuations. So resume accepts a continuation as an argument. And the other thing that I want to point out is that we do have one-shot continuations. This is, again, because we don't want to be able to create cycles. We don't want to require a garbage collector. And the good thing is that we can express all of the non-local control that we are concerned with one-shot continuations. And this is enforced dynamically. I'll talk briefly about our prototype implementation and preliminary results. So we do have an implementation in a production WebAssembly implementation, and we do use real system stacks to represent the continuations. So we have a complete implementation, but it is experimental and unoptimized. For example, we take on the cost of using existing library functions to perform non-local control. We have 2 benchmarks. One is a benchmark measuring raw task switching throughput. It's written in C. And this is a particularly hard benchmark against Asyncify because while we're measuring switching between stacks, Asyncify is simply representing this with branches and calls. And we also have a code size benchmark, which compiles Go programs, both using Asyncify and using WASM-FX. So here are our preliminary results. WASM-FX performs within an order of magnitude of Asyncify on raw task switching throughput. And these are initial numbers. We hope to do more optimization and see that be caught up on. We also see in code size that WASM-FX consistently outperforms Asyncify. And this best case example is a handwritten version of the control flow. So I've talked about what WebAssembly is, why it needs non-local control flow. I've talked about how effect handlers fits in this need and how we adapt effect handlers to WebAssembly. I've shown that it can express the needed control flow constructs, and most of the other control flow you might need is in the paper. And I've shown that we can implement it effectively. So thanks for coming to and listening to the talk, and I would be happy to answer any questions if you have any.
Thanks for the nice talk. Are these, I think I know the answer, but I just want to be sure. Are these shallow or deep handlers?
They're actually sheep handlers.
I was afraid.
They're shallow in the sense that the handler is not automatically reinstalled. However, we only install handlers when we use the resume instruction. The resume instruction installs handlers and passes control. So this has like performance benefits.
Okay, thank you.
I'm wondering, what is the path to standardization or adoption for this feature? Like, are you getting any pushback either on the feature as a whole or for alternative implementations of, alternative representations of this to implement the same kinds of high-level language features? What does that look like?
There's lots of appetite.
Fantastic.
I have maybe a naive implementation question, but so you say one-shot continuations, but in most of these effect handler languages, that you can use the continuation many times and implement these weird control flow and coin flips where you evaluate it multiple times, right? So can I actually use this to implement those kind of effect handlers efficiently, or do I still need to do the same kind of stuff that Asyncify does?
So you're not going to be able to do probabilistic programming, but all of the control flow that like languages care about that we have in our paper can be done with one shot.
Okay.
Go ahead.
No, you go ahead.
So maybe just a follow up to Will's question, but there is a standardization process, right? Is this in the standardization process, or is like interest in maybe creating the standardization process in the future?
Sorry, I should have been more explicit, but I don't want to bore you all. There is appetite as standardization is in progress, but there is politics and controversy.
Yeah, okay. Is it at a particular stage?
Stage one.
Okay, good. Awesome.
More than 0.
A quick question, technical. Can continuations close over things?
Yes, so because they're one shot, it's actually really easy to provide a value to them. So we have a cont.bind instruction.
Oh, that's cool. So WebAssembly doesn't have closures, right?
That's right.
Can I encode one-shot closures by misusing continuations as well?
Absolutely.
Beautiful. Thank you.
That's really interesting. Okay, so this is maybe a more speculative question, which is why I left it till last. But do you have a sense for how much performance is left? Right? Is the technique you're using fundamentally more difficult for this benchmark than the one you compared to, or do you expect you'll be able to get close to the continuation passing style version?
This may be like my personal opinion. Beyond like really the like very cool tricks that we just heard about, I think there's still going to be a gap with Asyncify on raw task switching, because Asyncify is essentially like cheating on that benchmark by just like being able to switch its own internal state and boom, you've switched task. But I think for like actual benchmarks, there's a lot of performance to be had and to be gained.
Fair enough, thank you.
Without support for garbage collection, is there a way for a continuation that you are not invoking to clean up any resources it might have allocated?
Yes, so we have an instruction for that. It's called resume throw, and it just resumes and immediately throws an exception.
Thanks.
All right, let's thank the speaker.
All right, test. Okay. All right, we're going to switch gears to sponsorship session. You ready? He'll switch when it's time. Okay. When you like. When you like. That's fine. Okay. Do you want to get started just so that you don't lose more people? All right, thanks. Welcome to the last session here of the sponsorship session. So I'm really happy to introduce Professor Dan Giekop, who we all know is a member of the programming languages community, but here he's speaking as the director of the Programming Language Laboratory at Huawei Research. Of course, we're very happy and gracious for the sponsorship that helps us support lower student registrations and to make essentially this event possible. So thank you.
Thank you. Thanks. I'm very happy to see so many of you here. My name is Dan Giekop. I'm still a member of the programming language community because this is a programming language lab. It's an industry programming language lab. And the reason why we're sponsoring UPSLA and a bunch of other conferences is because I want, and we want people to be aware that we are doing quite a lot of programming language. Okay, how do I change it?
It's on your machine that you're showing.
It's a I need to make them mirrored, I guess. Okay, thanks, Conrad. Right, so I just want to tell you some of the things that we do at Huawei in general, and particularly at the Programming Languages Laboratory in Edinburgh. So just a few words about Huawei first, a company that you may have heard of from news and so on. One of the ways that Huawei is very well known is as a telecom. I think the origins of the DNA of the company is in the telecom industry. Here is a 5G base station. Huawei is one of the leading providers of 5G worldwide. Also, you may know Huawei as provider of consumer products, particularly high-end mobile phone. This is a foldable version of the newest mobile flagship. So these are maybe the two things that you know Huawei about. But Huawei is doing a lot more than that. So, for example, you may not know, but in China, Huawei is selling an EV vehicle, which is quite successful. Is selling a whole line of consumer products, such as tablets, laptops, and so on. It is a major provider not just of cloud infrastructure, but also of cloud services. So this is a cloud blade made by Huawei, and all sorts of things, including some of the largest ports in China are automated by Huawei. So they're like smart ports, so IoT, IIoT, and a lot of other things that I could just go on and on enumerating. So Huawei is a very large company, technology, very active. It invests a huge amounts of money in research and developments, and in various rankings is consistently listed in some of the top companies in the world in terms of R&D spending, and also other metrics such as patents files, open source activity, and so on. So if you look at these things that I had on the previous slide, a lot of them have software at their heart. And Huawei produces not one stack, but several full stacks going from processors, from silicon design, such as mobile processor, the Kirin brand, GPU and AI processors, the Ascend brand, the Kunpeng processors for data processing in the cloud, also specialized processors for modems in base stations and in mobile devices, and so on. So there's a lot of silicon produced by design. And then at the next level, operating systems such as Harmony OS. It's a very widely distributed open source operating system, particularly targeted at mobile devices and IoT. And going further up the stacks, compilers and runtimes. So Bishengxi is a C compiler used internally by Huawei, also open sourced. And also it's a test bed for experimenting with various ways of improving the C programming language. Rust is, as you may know, Huawei is one of the 5 founding members of the Rust Foundation, so there is a huge interest in Rust in the company, and a lot of, I would say, both grassroots appeal and also interest of the leadership of the company in Rust. But there are also other numerous runtimes. For example, there's a cloud computing runtime called Yuanrong, which is used by the cloud service provision unit of Huawei. And then all the way going up to end user applications, along with the mobile phones. Huawei provides a large variety of applications, such as the health monitor that connects to smartwatches and stuff like this, IoT devices, a big range of IoT devices, as I said, cloud software, automotive software, which is actually not just for the Huawei cars, but it's also in collaborations with other car brands. They use Huawei automotive software, and also enterprise software at all scales. So the one thing that binds together this stack, and it gives you opportunities for vertical integration, is programming languages. Programming languages are relevant at all these levels. Everything here needs programming language to operate. And the fact that the whole stack is authored and controlled by a single company gives a lot of opportunities for vertical integration and for making these various sections of the stack work nice with each other via programming language. The interesting programming language is relatively new, so a lot of this is work in progress, and there is a very long and very exciting journey ahead of us to try to bring all these things together via programming languages. So what do we mean by programming languages? We have certain concrete topics that we are interested in. Right now, we are investing a lot of effort in effect handlers. We had a paper at last year's UPSLA. We have Daniel here, who is a co-author of a paper that was just presented just before me. And in fact, the previous session was extremely interesting to see all this activity and effect handlers. We're also interested in actor-oriented programming, and again, we've seen recently talks on actor-oriented programming. Ownership types is something that is, of course, is established in Rust, but I think I was extremely impressed by the workshop on ownership types, because I'm becoming more and more convinced that it's going to be very difficult for a programming language in the future to avoid ownership types. It seems to be a very important and pressing feature at all levels of programming languages. previous couple of years, we did a lot of work on automatic differentiation at the level of intermediate representation. We're also interested in a variety of DSLs, for example, for DSLs for doing high-level synthesis for hardware design. And this is just some of the topics that we have been interested in Edinburgh, where we have a team of about 20 people. But Edinburgh is not the only team that is interested in programming languages. So the things that I would say these topics are the things that unite all these diverse topics is, number one, is the fact that we are actually very industry-oriented. All the topics that we address is topics that we address with a very immediate expectation that they can be integrated in industry strength products that are going to be used initially internally by our own product teams and eventually externally. So the barrier for introducing innovation is quite high. It has to be a very strong motivation. We don't really do like experimental prototyping, kind of throwaway prototyping, like do something and give it out there, see if people use it. In some sense, we need to know ahead of time that there is a need that is going to be served by our developments. Performance is extremely important, and also simplicity of use. Huawei is a very large company. It employs literally hundreds of thousands of people, many of them developers. And even though usually the company hires people at a very high level of expertise, it is still important to have programming languages that are in some sense accessible. Even Rust itself is kind of considered maybe at the highest level of what you can expect a programmer to handle in terms of conceptual complexity. And maybe this is going to change as Rust becomes more and more mainstream. And the absolutely excellent talk earlier today about instrumenting the online book on Rust so that it gives a better it helps you more interactively to understand Rust. Hopefully that will help. But a lot of the people in my team, including myself, we have a academic background and we have research interests. So we want to use principal techniques in making this kind of development. So we're very interested in semantic-directed approaches, various kinds of semantics. But we don't want to just kind of hack it. We really want to produce principled work. And we have the papers that we publish. I'm not going to list them, but the papers that we published many of them are in kind of theoretically oriented conference. We have some interest in concurrency theory. So we have people who work on concurrency theory. Glyn Winskell is one of the members of our team. You might know him as a longtime contributor to concurrency theory via Petri nets and game semantics. We don't do a lot of stuff. He's kind of special in our team by engaging in mainly theoretical work. But we're also interested at practical application of category theory, in particular string diagrams. So we have, for example, formulated automatic differentiation via string diagrams, and we proved the correctness of the very popular Perlmutter Siskind automatic differentiation algorithm using string diagrams. And that was something that hadn't been done before because the original term-based formulation of the algorithm is very intricate, but using string diagrams, you get a certain degree of streamlining that makes the proof of correctness tractable. And these are kind of theoretical work that comes almost incidentally out of the more practical and implementation-oriented work that we are doing. So we are also interested in formulation and formalization and even mechanization. We haven't produced any work on mechanization, but actually internally we have developed mechanical like cock formalizations of some of our intermediate languages and intermediate representations that we're operating with. But probably the last two things that I want to mention, I'm not going to take a lot of your time, but we are extremely interested in academic collaborations. We have a framework agreement with the University of Edinburgh, so we have a lot of collaborations with University of Edinburgh, both in terms of consultancy, but also as just cooperation where Huawei gives money to people in the university for open-ended research. We also accept a fairly high number of interns, and we have the framework in place for also accepting postdocs. Interns we accept for mainly from the UK, but also from the European Union. And in fact, also our presence is a European Union presence. So everything that I said in terms of academic collaborations is applicable. It's more convenient for UK, but it's also applicable to the European Union in general. There is a possibility to collaborate, especially if on these topics of interest that I have listed. As I said, the presence of Huawei in European Union in general is very high. There's more than 30 research centers of Huawei around the European Union, but that covers the entire spectrum. We focus on programming languages. So this is it. This covers this one slide covers our rationale, the main topics, and kind of the spirit in which we want to collaborate. And of course, if you want to discuss more, I'll be very happy to meet with you after this. Thank you.
All right. And Dan? Does anyone have a question for Dan about the Programming Languages Laboratory at Huawei?
Yes, Sophia?
Postdocs, do you usually expect them to come with an idea, or they come with an expertise and then you tell them what to do?
We have.
Or you suggest they could do?
Yeah. We have many. We have kind of several frameworks for postdocs. I think for the most research-oriented postdocs, we have an agreement with the University of Edinburgh in which they would work half the time in the university, where they would be engaging in normal open research, and then half the time in the company, which is also in Edinburgh, where they would mostly engage in something like technology transfer of the ideas that they worked on into something that would be more of more interest to the company. These are usually 1-year contracts, but they're renewable.
Question? Okay. All right. All right.
Do you have another question?
Maybe give.
Okay.
So you said that the center is interested in actors, ownership types, automatic differentiation. Does it mean it works on all of them, or does it mean some of those technologies it has adopted and?
I think everything that is there. So automatic differentiation is somewhat in the past. Ownership types is somewhat in the future. But we are working right now very intensely on effect handlers and actors, for example. But all these topics are topics that I would say are main topics of interest for us.
Thank you.
All right. Well, Dan is around, so let's thank him. And
thank you.